Carl Sagan gave us the pale blue dot when he asked NASA to turn Voyager's camera back towards Earth and capture a fleeting glimpse from 6 billion kilometers away back in February of 1990. In that iconic image, our entire planet is but a tiny, fuzzy, pale blue dot, unremarkable and insignificant against the vast and deep blue background. Carl reminded us that on this pale blue dot, every single human being who ever was lived out their lives. In the 300,000 years of modern human beings on Earth, our presence has been marked in the fossil record and our tools and abodes unearthed in the trenches of archaeologists. In more recent times, our forebears left their marks on cave walls and ultimately artists' canvases, and finally through language and the written word. Great civilizations have come and gone, empires have risen and fallen, and human migration has spread our species across the entire globe. And yet through all those hundreds of thousands of years, humanity has not altered the Earth's environment in any appreciable manner that could be noticed by its inhabitants or detected from outer space, nor have any meaningful impact on our long-term sustainability as a species. In climate terms, the great dynasties of China, zero impact. The ancient Greeks, zero impact. The Roman Empire, zero impact. The Dark Ages and Renaissance, zero impact. And then came the Industrial Revolution and the harnessing of fossil fuels, not for heat and light, but for energy to run our factories, turn our machines, drive our automobiles, and bring us to the dawn of the age of technology. In just the last 100 years, human activity has altered our environment in unprecedented ways, leaving a technosignature in our atmosphere in the rapid and potentially catastrophic buildup of greenhouse gases, a signature that would be visible to civilizations observing our world from distant planetary systems. Climate change is here and is manifest through obvious and visceral changes in weather, with rising temperatures, devastating storms of increasing intensity, fires and floods, droughts, and coastal inundation. Where climate change is concerned, the new normal is that things are likely to get worse before they get better. So is it too late for us? Are we indeed at a crossroads? Today, we're going to explore this topic of climate change through the lens of planetary science, astrobiology, and the search for life and intelligence beyond Earth, or SETI. My name is Bill Diamond, CEO of the SETI Institute in Mountain View, California. We're delighted and honored to be co-hosting this event with Georgetown University in Washington, D.C. We've assembled, virtually at least, a truly extraordinary group of journalists, scientists, scholars, and educators to ask, can the study of other worlds help us save this one? So I'd like to introduce my co-conspirators, Professor Dagmar de Groot and Sarah Johnson from Georgetown University, and conceptual artist and experimental philosopher Jonathan Keats, and ask them to say a few words before we get underway. Dagmar?
Yeah, thank you so much, Bill. I had the idea for this event a while back as I was working on my next book, and I realized that the search for life on other worlds has been for hundreds of years driven by the question not only of what causes life to appear, but also what causes it to disappear. And this is a question, of course, that could not be more urgent for us today as we confront overlapping environmental crises, most importantly, the climate crisis that threaten our continued existence. Given the growing urgency of these crises and the rising prospect that we may soon learn whether life has emerged beyond Earth, the time seemed right for a conference devoted to the environmental dimensions of the search for life, especially intelligent life, on other worlds. So I'm really excited to be doing this and grateful to have worked with incredible partners at Georgetown and SETI, especially the SETI comms team led by Rebecca McDonald and, of course, my co-organizers, Bill, Sarah, and Jonathan. We have an incredible lineup for you, and I hope you all enjoy it.
Great. Thank you, Dagmar. Sarah.
Welcome, everyone. This is so tremendously exciting. I'm just looking at the chat and seeing people from all over the country, all over the world. So I'm an astrobiologist. My work focuses on biosignatures or traces of life and how we might recognize signs of life on Mars and ocean worlds, the moons of the outer solar system, and not just life as we know it, but potentially life that doesn't even share the same molecular framework. And some days it can feel like trying to imagine a color we've never seen. But just from my perch as sort of a planetary scientist and many of the people that you'll hear from today, you know, for those of us that are spending so much time staring into these distant worlds, just feeling transfixed by their just total foreignness, and especially thinking about these very vast scales, tremendous scales of time and space, geologic epochs, millions and millions of miles, there's just no way that you can see our planet as anything but just tremendously precious. And here we are, we have a moment. It's just a moment. And this is our moment to act and to save this incredibly wonderful world that we have. And so I'm just so hopeful that this viewpoint, this sort of perspective, this way of looking, this angle on this problem may bring some new light to bear on some solutions. But we're just so happy to have you. And I'll pass it along to Jonathan.
I'm delighted to be here and delighted to see all of you here. It has, in my life as an experimental philosopher, been one of the great challenges to figure out how we can recontextualize our sense of ourselves and our world. And this has only become more urgent as our worlds become more fraught. And speaking with Dagmar initially, and then opening up the conversation with Bill and Sarah and Dagmar, I think that what we've come to recognize is that the L variable, habitability, the great silence, and potentially whether there's a great filter, that all of these are ways in which we can see ourselves from another perspective, much as Carl Sagan challenged us to do with the Voyager records. And so what I would urge all of you to do as you listen to these remarkable panels is to think about SETI and what sort of application SETI might have here on Earth, whether applied SETI might be a way in which to inform policy and our everyday activities. So I'm going to turn it back over to Bill and look forward to today's discussions.
Great. Thank you, Jonathan. And again, welcome everybody. And it's wonderful to see in the chat people joining us truly from all over the world. Very exciting and wonderful to have this reach. And before we get underway, I just want to let people know that we will at the towards the end of each of our 5 panels today have an opportunity to take questions from the audience. And so there's a Q&A feature that you should see at the bottom of your screen in Zoom that you can use to post questions. We'll be selecting a few of them. We probably won't be able to get to all of them, but we will be asking panelists questions at the end of each session. So please join in and be part of the conversation. And without further ado, we're going to start our first panel, the L variable, with our moderator, Nadia Drake. And we have a little video film to set the stage for us and provide some context. So we're going to roll that film now and turn this over to Nadia. Lee, go ahead.
60 years ago, Frank Drake, Carl Sagan, and a handful of other scholars gathered at the request of the National Science Foundation to discuss the scientific merits of SETI, the search for extraterrestrial intelligence. Could a case be made to look for life and for intelligence beyond Earth? And if so, what were the crucial parameters? It was Frank's job to craft the agenda for the meeting, and as he thought about how to organize the discussions, he ended up sketching out the key scientific questions he'd need to answer if he were going to figure out how common alien technology is in the Milky Way galaxy. These were questions like, what is the birth rate of sun-like stars? What fraction of those stars have planets? How many of those worlds might be habitable, at least by our standards? And what fraction of those habitable worlds might go on to develop life, intelligent species, and ultimately, detectable technologies? Perhaps most importantly, he felt, was the question of how long civilizations would remain detectable before they evolved beyond their noisy technologies or disappeared altogether. Frank realized that his list of questions could be expressed as a series of independent variables, and that if those variables were multiplied together, they'd produce the number of detectable technological civilizations in our own galaxy. His formula soon became known as the Drake equation, and today it is among the most famous and recognizable equations in all of science, perhaps second only to Einstein's E equals mc squared. The Drake equation now serves as a roadmap for the field of astrobiology, the study of life in the universe, as well as life's origins here on our home planet. And so, not surprisingly, the single most important laboratory we have for astrobiology is Earth. But just as planet Earth informs the study of alien life, so too does astrobiology inform a better understanding of life here, how it began, the conditions necessary for life forms to evolve and thrive, and the consequences of Earth's most advanced species on its long-term habitability. The last variable in the Drake equation is represented by the letter L, which signifies the longevity of detectable civilizations, L is arguably the most intriguing and the most vexing of the variables in the Drake equation. Today, we explore the topic of climate change through the lens of astrobiology and planetary science. Can these fields offer important perspectives on a crisis that is testing our own L variable? Can examining climate change at a planetary scale bring greater awareness to the magnitude of this challenge? And might that help accelerate more decisive action? These are the questions we seek to address today. Welcome, everybody. I am Nadia Drake. I'm a contributing writer with National Geographic, and I'm also related to the Drake of the Drake equation, who happens to be my father, Frank. As the video said, this panel is on the L variable, which is the last variable in the equation. It's the one that asks us to think about how long, on average, technological civilizations remain detectable. Dad says that L is the most vexing variable in the equation, and it's the one that's the least knowable in advance, meaning that it's tough to reason your way to an answer without any data points. There are actually many intricacies and nuances that go into the L variable, including the issue of who's asking the question and what kinds of detection capabilities they have. But for now, I think we can keep it simple and consider humanity's L, the longevity of our own technosignatures, and the factors such as climate change that affect that longevity, as well as what that means more broadly for us as a civilization. So we have three panelists, each of whom appear to be on other worlds, and each of whom will briefly introduce their perspective on the L variable and what it means for humanity. Mike Wong is an astrobiologist and postdoctoral fellow at the Carnegie Institution for Science. Anne-Marie Cody is an astronomer at the SETI Institute. And Natalie Cabral is an astrobiologist and director of the SETI Institute's Carl Sagan Center for the Study of Life in the Universe. Toward the end of the hour, we will be taking questions from the audience. So please do put those in the Q&A that's at the bottom of the Zoom screen. And okay, Mike, you are up now.
Hi, yeah. So people who know me well know that I'm, in addition to being a scientist, a really big Star Trek fan. So I'll begin by setting the stage by showing this slide that I generally show when I give public science talks. And when I tell the story of how ever since Star Trek's inception, the creator of the show, Gene Roddenberry, wanted science to be at its core. So he actually wrote about the Drake equation in his 1964 proposal to NBC Studios for his new science fiction show concept. And that's what you see on the top line there. Thing is, in 1964, you couldn't just Google what Drake's equation was. And Gene Roddenberry, in fact, had no idea what Drake's equation looked like. So under the time pressure of the studio to submit his proposal on time, he just scribbled something random on a piece of paper and sent it in. And that's what you see on the bottom line here. It's an absolutely nonsensical equation. Luckily, the studio had no idea what Drake's equation looked like either, and Star Trek was accepted and approved. Now, many years later, Professor Drake actually came aboard the set of Star Trek, I believe Star Trek Voyager, as a technical consultant. And when he was on the set, he was shown this fake Drake equation that Gene Roddenberry had penned in his name. And when he saw it, he just laughed and he said, "Oh, Gene, don't you know that raising something to the first power is simply itself? Like, why would you do that?" So I'm an astrobiologist, and all of the terms in the Drake equation are really intriguing to me. The ones that I think about the most in my work are probably N sub E, so the number of Earth-like, or the number of habitable planets out there. Today, we have the understanding that to be habitable is not necessarily to be exactly Earth-like. You can potentially be habitable as an icy ocean world like Europa, or with a completely different atmosphere from Earth like Titan, or indeed the early Earth. And I also like thinking about F sub L. So that's the fraction of planets in which life emerges. So the origin of life, which is a huge open question in our field. Needless to say, the further you go down to the right-hand side of this equation, the more speculative you get. So I really look forward to speculating with you all about the nature of the L variable. But just to bring things full circle for my opening remarks here, people say that science fiction is at its best when it uses faraway worlds and fanciful adventures to talk about issues that are very real and very close to home. And I think the same is true of astrobiology. We can't ask about the origin of life without asking, what is life? What are we? And we can't talk about the habitability of other worlds without considering how we are altering the habitability of our own. And we can't think about exploring the cosmos without remembering how our ancestors explored this globe, oftentimes for greed and exploitation and colonization and domination. So, this is a wonderful paradox that looking outwards and towards the future also means looking inwards at our own selves and our history on this planet. And I think it's this paradox that brings us all together today for the fascinating discussions that we'll have.
Thank you so much, Mike. Anne-Marie. I think you're going to have to unmute. Yes.
Okay, I'm unmuted now. Thank you.
Yes.
Let me share this. Perfect. Oh. Okay, so I'm an astronomer at the SETI Institute, and oh, that's still not coming on. Sorry about that, guys. Okay, here we go. I'm an astronomer at the SETI Institute, and I too have been involved with search for planets around other stars, and very interested in what we're going to find in terms of life that's out there. And the question when we come to this L variable that has already been mentioned is, are we going to find advanced life? Most of the astronomical technology being used today is focused on finding molecular signatures, things that could be any form of life, from single-celled organisms to something very advanced. And so one question that intrigues me and many other scientists at SETI who have been using radio telescopes to search for signals of life, signs of life elsewhere for decades, is how would we find something very advanced? And one schematic that can offer guidance is shown here. This is a hypothetical idea of what would happen when civilizations and such as ours on Earth evolve past the energy capabilities of their home planet. We use a certain amount of energy here on Earth now. And if we extrapolate far into the future, eventually we will exceed what is available to us. And so this idea by Kardashev some decades ago shows that perhaps very advanced civilizations beyond us might actually build structures around their host stars to harvest energy and send it back to their planet. Eventually, there may be something on a whole galaxy scale. As an astronomer, I've been using space telescopes for the past decade to monitor the brightness of stars out there. These space telescopes are many of the telescopes that have been used to find planets around other stars, but we can do other things too. And specifically, if there are structures in orbit around other stars that are being used for energy purposes or even communication, we might actually be able to detect those as they pass in front of the parent star. And so that's what's shown on the bottom here. The brightness of the star may fluctuate in time in a way that does not match with known astrophysical phenomenon. So that's actually what I'm working on right now using space telescopes. Here is the Transiting Exoplanet Survey Satellite, or TESS for short, to look at literally tens of millions of stars to see if we can find any signs of a very advanced civilization. Will we find something? Time will tell. And this is just going to be very exciting. If we don't find anything, what will that mean in terms of the survival of life elsewhere in the galaxy? That may be interesting as well. Thank you.
Thank you, Anne-Marie. I agree that both outcomes of that search are equally intriguing. And I think we will get there in the discussion in a bit. But first, Natalie.
Good morning, Nadia. It's a great pleasure to be here. I am an astrobiologist, as you say, so very much like Sarah Johnson introducing herself. I am interested by the development of life and the survival of life on other planets. And I am doing a lot of field work in terrestrial analogs, which means that I'm trying to understand what kind of habitability, what kind of habitats, and also what kind of life is surviving in environments that are analogous to those that we're finding in the solar system. And so the parameter of the Drake equation I am really interested in, of course, are the ones with the origins of life and the one that relate to habitability. But what I'd like to say about the L factor, and this is for my other hat, the one from the director of the Carl Sagan Center. There is the empirical side of me and the theoretical side of me. I like to question questions. And the L factor in the Drake equation is everywhere. From the time when life appears on this planet, species are going to meet their L factor. But what is really fascinating about ours is that throughout the evolution, we have a natural course of coevolution of life and environment, which means that, well, species adapt or disappear, right? But today, we are really the first species who is capable of altering that course. And we have a really important impact on, our own duration, the environment that's favorable to us. So these are really the aspects of the Drake equation that I'm fascinated about, and I really hope that we are going to talk about that today.
We will definitely talk about that. Thank you all. I really appreciate it. I guess the first question, just to kind of set the groundwork for the rest of the discussion, is when we think about humanity's L, the length of time for which we have been detectable, what is the answer to that question now? What are we thinking about our longevity as a detectable civilization? And what are some of the factors that can have an impact on that? And this is for the entire panel, so whoever wants to jump in.
Okay, so probably go after it. In terms of humanity, life actually, well, before the humanity, I mean, life in itself has a footprint on this planet. And it started really, our first visibility as a planet that was alive is really with a change in the composition of our atmosphere. That's 2 billion years ago. All of a sudden, life transforms everything. And maybe there is a message there already, because it's already a complete disaster, ecological disaster that kills about all of the life that's there. So maybe we inherited that ability to actually kill life by transforming ourselves. But the L factor of whatever life was before that time all of a sudden became very short. As far as humanity comes, definitely the beginning of the industrial era is where things started to change and accelerate. Bill mentioned that a little bit earlier on about the impact of the industrial times. What is really interesting, and I'd like us and the panel in general to come back to that notion, which is critical for the L factor, is all of a sudden this awareness that we are in the system. So for the longest time, there were fewer humans in the first place, and we were working with the planet. Whereas now we are putting into this system other things, whatever gas we are putting into. And for the longest time, we didn't realize that there was any impact to it. But the problem with the system is there are feedback mechanism, and they are going to come back. And the more you put in, the more at some point they are going to show up. And this is what's happening now. The issue for our L factor is that all of a sudden, the increment is not linear anymore. It starts to become exponential. And this is what we are seeing right now. So the L factor is, our duration is reducing by the year at this point in time. There is no norm to the change in the environment that we are seeing. Next year is not going to be like this year. The change is exponential.
Yeah, I think it's interesting because when I first started writing about the Drake equation, we would say things like humanity has been detectable for somewhere on the order of a century, since military radar started squawking quite loudly at the beginning of the 1900s. But then when you do consider that we are a species that has the capability to change our environment in observable ways, I think we can start to consider that RL, we've been detectable for much longer than we think, again, beginning with the Industrial Revolution. And so, Mike, I'm curious because I know that you're working with biosignatures and thinking about what biosignatures might look like on other planets. What are your thoughts here? I saw you nodding quite a bit as Natalie was talking.
Yeah, that's just because I thought Natalie's answer was so brilliant and really encompassing of the whole problem of how we think about L. It definitely is very tied into who we're thinking about is observing us, right? Because depending on their telescopic technology, they may be sensitive to trace gases in our atmosphere, or they may be even able to observe changes over time in our atmosphere, or even look at Earth's surface and understand that life has been present due to photosynthetic pigments on our surface, and then even see like the impact of humanity spreading across our world. I think maybe the only other thing that I would add to this is that oftentimes, we think about L as a single number in the Drake equation, right? But I think that to me, what L represents is sort of just a statistical function, the way that we would think of maybe how temperature relates to the kinetic velocity of gases in our room. You can assign one single number to the temperature of the air in the room that you're in right now, but that represents a whole distribution of different velocities. And maybe the deeper question is, obviously humanity's L really matters to all of us on a personal level, but maybe the deeper question, cosmologically speaking, is, what is the distribution of L? And what is its shape? What is its peak? How narrow or spread out is it? And perhaps the biggest question of all is, can we derive what that should be using the laws of nature, the way that you can derive the Maxwell-Boltzmann distribution of the velocity of gas molecules from first principles? So that's obviously a big open question, but it's something that I think is worth thinking about.
I was thinking about that in the context of the megastructures that Anne-Marie mentioned that she's looking for. And so I know we kind of teased at the fact that if you find evidence for some of those megastructures, it will obviously be transformative. But the other side of that coin is, what if you don't find anything at all? What does that mean? And does it actually tell us something informative about longevity, about surviving the path that we're on right now?
Yeah, I think it's a really interesting question. If we look at 100 million stars and we don't find anything, it's not necessarily a nail in the coffin that there's nothing out there. It's we're still limited by humans' imagination and where we think our own civilization is going. We're consuming energy at a rapid rate, but it's possible that civilizations become much more efficient, that they realize that they never need to build such structures. We're certainly nowhere near having the capabilities of doing that ourselves. So in that sense, if other beings in the galaxy are looking for structures around our sun, well, they wouldn't find any, even though we're here and we might argue we're somewhat technologically advanced. So right now, I think we'd just be detectable possibly at radio wavelengths for a few decades. And the other thing one needs to keep in mind is, assuming we understand basic physics, there's sort of some signal travel time. So if there's a civilization all the way on our other side of a galaxy, it's going to take thousands of years for either us to detect their technology or them to detect us, simply because light doesn't travel instantaneously. So it's going to be interesting to see, especially with the projects that I'm involved in. We're probably most likely not to find anything, but ultimately we're going to figure out exactly what that limit tells us about, could there still be stars with megastructures, and we just didn't look at enough.
Yeah, it's totally fair. I think it's interesting that when we talk about L, I think there's this assumption, and maybe this is just me and nobody else, but there's this assumption that having a larger L is in some way better, right? That being detectable or having detectable technologies for longer in some way is equated with survival or with success, and that having a shorter L could be equated with failure. But I'm not sure that's the case. I think we can build technologies that outlive us, or we could become a society that doesn't emit any technosignatures. And so I'm curious about your thoughts there, because I do think there tends to be this idea that bigger L is better, and that's what we should be working toward.
Nadia, can I share my screen again?
Sure.
All right. I'd like to go back to that slide that I just showed very rapidly earlier on, because this is illustrating a little bit what you're saying.
Mm-hmm.
I don't think that the size of L means, anything in particular. I mean, the shorter L, as long as it's because you're surviving, it's probably a very good thing. Here in the Drake equation that's to the left, you see L to me is a point in time, a very important point in time for a civilization, because it's a time of awareness of its position in the system as a coevolution. Then you have to make a decision whether you ignore that you are in the system, and then your L might be very short. I mean, look at us from the time of the Industrial Revolution to now, it's 150 years, and we are at the tipping point climatically, where we might be just actually killing the environment that's favorable to us, which is also where I would like to, add a footnote. The planet itself is in no danger whatsoever, okay? Life has, the Earth has been changing throughout the eons and will continue to do so. It will reset to a new equilibrium where humanity doesn't have a place in it, or if it has a place in it, will be not as good as it is right now for quite some time. So it really depends on what you do with the awareness you have. Either you ignore it, you are going to follow the red path, or you are paying attention to it. And then there are a number of different paths. I don't mean that, there are only two, but one is exactly what you said. It is that all of a sudden, a civilization becomes invisible because it is so well in symbiosis with its environment that it isn't detectable from anything else. And this may happen sooner rather than later. So I don't think that the L factor is something. If tomorrow we realize that we need to get in tune with our environment, and we start developing the technology to do that, we might disappear from visibility within 100 years. I don't know, I would hope so. And we might disappear as well because also willingly, we are developing technologies. We are geoengineering our planet so that we are becoming invisible. Or all of a sudden, we are so advanced and we have so much knowledge of the universe that we discover a new physics that makes us disappear from the radar screen, so to speak, et cetera, et cetera. So I am going to unshare my screen and leave the discussion open here. But there are a number of reasons why I don't think the size of L is really what matters, is what we really do with L, where the awareness goes. We can just ignore everything and the planet is not going to ignore us. Or we can all of a sudden eco-engineer our planet and become invisible for very, very good reasons.
I'll also offer a comment or maybe a caution about equating L, the length of L, with our survival, because it really depends on what you mean by survival. Life, the history of life, the history of evolution of life is all about change and flux and transcendence into new scales and levels of biological organization. And I think we are in the midst of a major transition right now as we see this pace of change accelerating faster and faster. And you just have to look at our technology, which is omnipresent in our lives today. Our portable computers, our smartphones in our pockets, that binds people across the world in a digital web of information that just like that organizational structure of information flow had never existed in the history of our planet before. And I think as technology grows around us, we may end up becoming subsumed in it. I mean, we already are I spend all of my day looking at a screen, whether for work or for play, especially in the pandemic when all of the social interactions were over Zoom too. And so maybe humanity doesn't survive the way we imagine it to survive in the future. Maybe we become engulfed in our technology. Maybe in an analogy to the endosymbiosis between a bacterium and an archaean that created this complex cell structure in the mitochondria that enables us to be around. Maybe our own inventions in the technology that we create end up subsuming us. And you can turn to sci-fi now for imaginings of this happening, whether it's the Matrix or the Borg from Star Trek. But I think this is a very real possibility, and one that we again, the consciousness and the awareness and the self-determination that Natalie brought up, this is all wrapped into that and our definition of what L and survival means.
I think it's interesting that kind of inherent to this discussion, I've heard it from Anne-Marie and from Bill in his introduction, and also Mike in the conversations that we were having, that energy usage and demand seems to be kind of the crux that's going to tell us where we're going. That's what we have to make some choices around. And so, Mike, when we were speaking earlier, we had talked about some ideas about there being kind of generalizable laws, basically, of metabolism, for biology that maybe you can scale up to cities or societies. And so I'm wondering if maybe we can just kind of go back to that discussion, because I think it's interesting, and it could tell us something about the path that we're on, and how much of a choice we actually have, if this is something that's escapable or not.
Yeah, absolutely. So when I think about the L variable, I first think about some work from Geoffrey West and colleagues. Geoffrey West has been thinking about scaling laws for life, these universal laws that describe things like biological metabolism. And he and his colleagues have shown that the pace of life actually grows slower as the organism grows in size. So you can look at how heart rate changes between something the size of a mouse to something the size of an elephant. And then you can also try to apply these scaling laws to describe cities as biological, sociological, technological organisms of their own. And what you find is that, converse to the way biological metabolism works, the larger a city grows, the more return you get, the greater its GDP, the people earn higher wages, the more patents are produced per capita. People even walk faster in larger cities. And so when you have a law of increasing return like this with size, you actually start growing in a very unbounded way. And so you can see this in how human population has become basically exponential. It's skyrocketing faster and faster with time. And so this work has shown that cities actually have growth trajectories that head towards singularities, which is basically where you increase towards infinite population in a finite amount of time. And this places an extreme demand on energy resources. West and colleagues claim that we can sort of sidestep these catastrophes that we're heading towards by resetting the initial conditions, by innovating. And we see this with innovations throughout human history since the Industrial Revolution. And the catch is, though, that the singularities come faster and faster and faster. So we sidestep one, we're on the trajectory for a singularity in the slightly distant future, but then the one that comes after that, after we sidestep that one, comes at an even shorter pace. So our frequency of innovations must increase to keep up. And so again, we see plenty of examples of this in this blinding speed of technological innovation. And I think that what I was saying earlier about how technology binds the world together through social interactions that are now completely sidestepping the physical barriers between human beings, the very fact that we can have a conference like this over Zoom with people around the globe, I think sort of indicates that the world as a whole is kind of like a big city now. And maybe our civilization is heading towards a trajectory that is going towards one of these catastrophic singularities where we will soon run out of energy to supply all of the computational and social demands of our way of life. And so I think that we have this very narrow window of time between when we can have the cognitive ability to realize and model the physical trajectory that we are on and the energy demands that it requires, and when we reach that collapse. And that is our sliver of time to, again, make that conscious decision to maybe try to reprioritize at a very fundamental level the dynamics of our civilization, away from hyper-capitalistic, exploitative resource gathering and unbounded growth and expansion and productivity and, optimizing GDP, to maybe optimizing something else like homeostasis or well-being. And when I told my friend Dr. Stuart Bartlett about this idea the other day, he basically said, okay, so Mike, you're saying all the alien civilizations are either dead because they reached this collapse point and fell over, or they're all just Buddhist monks meditating to prioritize mental well-being. And I think that pretty much sums it up. Maybe this is an answer to the quote unquote Fermi paradox. Maybe this is an answer to what L is, that civilizations either reach this breaking point or they decide consciously to reprioritize what they're optimizing and, in a sense, no longer expand unboundedly into the universe. And that's why we don't see anyone.
That's a very interesting point, Mike, because that goes back to the notion of coevolution of life and its environment, except that, this is a system that fights entropy. But at the same time, if you're becoming a Buddhist monk, there is some sort of, immobilization. So it's just like, we'll have to figure out a balance between the two. But we are at this point. And this is exactly what you're saying. L, maybe it's awareness of our trajectory. The different colored arrows that we are seeing.
And Marie, I'm curious about your thoughts as well here, because we are talking. Yeah, I'm curious.
Yeah, I think I wanted to go back to what Michael said earlier, that, L might not be a fixed number, and, there might be a range. And in terms of an astronomer who's out there, looking for things out there, I wonder if there's a way to sort of find those Buddhist monks, right? Like, can we find the civilizations that have the large L? And if so, how do we do that? Is there something specific we should look for? Or is there some signal that will show us the difference between a civilization that's hitting that tipping point and going to disappear, or something that has lasted long enough? Or are the ones that last long enough the ones that are hiding from us because we're just not very intelligent at this point? So many questions that we don't have answers to, obviously, but I think it's important to keep looking and to keep enlarging our sample size as much as possible, so that potentially, we can learn something for ourselves as well. If we find something, what can we figure out about how those long-lasting, those large L civilizations, what have they done differently from what we're doing now on Earth? And are we intelligent enough on Earth to actually, learn from that and make a change? I think that's one of the most challenging parts.
Yeah, that makes me think of something that Natalie had pointed out when we were talking, which was that if you look at the Drake equation, the variables toward the left-hand side, life is just kind of a passive passenger. Like, we don't have a lot to say about the birth rate of stars or how many habitable planets there are in a system. But that as you move toward the right-hand side, we start having the ability to make choices. We can, in a sense, determine, our own L. We can think about whether we want to make technologies that announce our presence, which we've obviously already done. And so I think when I was speaking with Natalie, she was saying that L is actually empowering. It's a variable that we have control over. And I'm curious, before we open it up to audience Q&A, what do each of you think our options are at this point? When you think about the decision tree that we're looking at, what's left? What can we do?
Well, I'll take a quick answer to that. I think that we see every single year the difference it makes to the fact that we're doing nothing. At this point in time, there is enough energy in the system that it's building up on its own if we are not removing it. So it means that within it's not going to happen in 100 years. It's going to come at us a lot faster than that. It's not a matter of the next generation, and we don't care because the children of our children are going to have to deal with it. We are going to have to deal with it in a lifetime. We already have to deal with it. And what I'm talking about is the fact that some of our favorite activities won't be necessarily possible anymore because the temperature is too hot most of the year to do things safely, for instance. And this is probably when it's going to hit people, that they cannot go and see their favorite soccer game or football game at some period of the year just because it's too hot or too unsafe for players to be playing. Unfortunately, it's going when people are being hit in the things they like. Right now, it seems that they don't care. They still can use their car, etc. Oh yes, it's a little warmer in November. Fine, we have spring temperature in November. This is, that's nice. It's a lot better than to be freezing, but it's not normal. So I'm going to leave it here. But what we need to do, we need to do it yesterday. And I think that all of us here, we have, working with space and planetary sciences, we didn't talk so much about this, but there are many of the instruments and the technology that we are using to very, very fast, reach objectives to understand how a planet behave or what is the habitability of a planet, etc. There is a lot of that technology that we can use to look back at our own planet and support the effort to monitor that change and forecast it and help humanity.
Mm-hmm. Mm-hmm.
Yeah, I'll just leap onto something that Natalie said that was very brilliant. She mentioned the word entropy, and I hope not to get too technical with this, but I think that when we use resources internal to our own planetary system, such as fossil fuels, this chemical gradient that we utilize will raise the entropy of our own system when we dissipate that gradient. So that means that the disorder and the heat of our planet is going to increase. We do, however, have a source of low entropy coming at us from our star. So solar energy is external to the planetary system of Earth. And if we utilize that, that will not necessarily raise the disorder of our own world to the degree that burning fossil fuels will. So I'll just throw out a pitch there that we should be really taking solar energy a lot more seriously than we are right now and expanding into that as a green energy source.
Agreed. Anne-Marie?
Yeah, I also think, it's a different area, but, we need more time to kind of let our own species evolve. Where we tend to operate as individuals on short time scales. We live in an era of cheap thrills. What do I want to do? I'm gonna drive my car today because I feel like it, rather than thinking long term. And so in some sense, I've always thought, we need to buy more time somehow. I think if ultimately we're able to find or even make contact with other civilizations out there, it's just going to be this incredible transition. But the question now is, are we actually going to last long enough to make it there? And so in some sense, we need to figure out a way for human brains to evolve to the point where they have slightly different priorities. And then, we make the discoveries and suddenly something sets in that, we need to change the course of humanity. But yeah, the question is, are we going to get there?
Well, Mary, you point a great, you're saying something great here, is that we need to change our first priorities to need to change our priority from individualistic to thinking of ourselves as, excuse me, as an organism, as one. We are, that goes back to the Carl Sagan pale blue dot. We are all of this, together, and we need to respond together to this crisis because, just like the pandemic, if a quarter or half of the population is not doing it, then you know what it is worth it. I mean, we don't react for many reasons, socioculturals and you know, because of boundaries, etc. We tend to react as nations, as individuals, instead of thinking as planetary citizens. And I think that how we are going to evolve towards L is this awareness of our planetary citizenship, and we're not there yet.
Bill, I don't know if you've been monitoring the Q&A. I see Jill has her hand raised, so maybe we'll start with Jill, and then if there are questions you want to throw in from the Q&A, we can go there next. I don't know how much time we have left. So
I have. So we're going to, because we had the technical delay at the front end, we're going to go ahead for another 10 or 12 minutes. And I do have some great questions, but I also noted Jill's hand up. So why don't we let Jill start, and then we'll go ahead with some audience Q&A.
So thanks, Nadia. Thanks, Bill.
Sure.
I've always wondered, we think about the distribution of L out there, and we think about it as the number of civilizations with a particular L, and we think about it as monotonic. But what if it's bimodal? And what if the thing that determines whether you are in the large number of short-lived civilizations or you make it over to the cluster of long-lived technologies is whether or not you detect the presence of other technological civilizations?
that's cool. Who wants to respond to that?
That's an interesting, you know, case study that goes back as, you know, how many of us are out there. So then you have to think about, you know, it's an enormous question, Jill, because you have to go back, you know, the distribution of life, and then if are we synchronous in space and time? Is the apparition of life the kind with which we can communicate? Is it generational? Some people say there is no reason it should be generational because the stuff that makes us has been being produced by stars a long time ago, but also because of its long history, maybe there are many filters, and maybe we are all coming together at this point in time where life is evolved enough that we are getting to the point of being technologically sentient. But so if that's the case, and we are all at the same level in the universe, then it's a little difficult. Then you have more chances to have a regular bell-shaped curve. If you have very old civilization, that's a very different thing. Maybe ET landing on the White House lawn is going to make a huge difference. You know, oftentimes these days, I'm really hoping for this to happen because we need some help. But again, you know, let's not go there, because I think that we really need to help ourselves first and not wait for ET to bring the solution. But yeah, no, it's a loaded question because it depends so much on, you know, how many of us are out there and what are the different stages we are in. If we are all of the same age, then it's going to be a different question.
I'll just say that, Jill, I love that thought. It never occurred to me before that, you know, discovering other instances of technological civilizations out there would so greatly impact the probability that you wind up having a very long L. I guess I often think about instead the similar question about the discovery of, say, microbial life on other worlds, perhaps in our solar system, or evidence of its presence through the metabolic gases it puts out on an exoplanet that we can detect using telescopes, and how that will change the fabric of our society and the way that we see ourselves and our place in the universe. And I think you're absolutely right that if we end up discovering another technological civilization out there, it will change our mental state as a civilization and influence the trajectory that we're on, hopefully. How it influences exactly is I won't dare comment on, but I think the plausibility of the argument that you laid out is quite high.
Great. Thank you, Michael and Natalie. And Nadia, I'll go ahead and start with some of the audience questions, if that works.
Sure. Yeah.
And actually, Michael's comment just now was a good segue into the first question that came in, which are, what are some of the signatures of non-human life what are some of the signatures we might look for that might not be technological in nature that are part of the SETI and astrobiology endeavor?
I can take this one if you want to. I was mentioning the very first one was really the change in our atmosphere and the oxygenation of the atmosphere of Earth that's directly related to cyanobacteria. That was an immense change in what was happening before before life was able to take some of the carbon from the atmosphere and produce oxygen. I think that life was not so visible, but all of a sudden, 2 million years ago, you have this immense flux of oxygen, and our atmosphere has changed forever. So if anybody had been watching the Earth at that point from afar, they would have started to ask questions about what's going on, because there is a massive disequilibrium all of a sudden that you have to explain. And this is, one of the main things that we are looking for, disequilibria in a planetary environment. That would be one of the things. And disequilibria can be related to many things. Can be related to environmental change. It can be related to biology. But this amount of oxygen in our atmosphere in this amount of time, they would have had to look for a good reason for it.
Right. Yep, absolutely. And of course, in the field of astrobiology, as all of our speakers know, is constantly looking for a means of identifying biosignatures. In other words, how does biology impart a fingerprint that could be detected, for example, on its planetary atmosphere or in other ways manifest in such a manner that we could detect it from great distances without necessarily having instrumentation on those worlds. So that's definitely related. I have a specific question here from Ryan, and I think this is really addressed to Anne-Marie. And that is, how distinctive is the transit of an alien megastructure for energy collecting, for example, on its star's light curve? I mean, how does one observe a phenomena like that and come to the conclusion that this might be an alien megastructure of some sort?
Yes, so it really depends on how big that structure is and whether it's in a distinctive shape. So it's certainly possible to have structures that would be difficult to distinguish from, say, transiting planets. But what we're envisioning now is something that's large enough that it seems like it could be too big to be a planet, or something that is not circular at all. So for example, we have a student in my group who's running simulations of all kinds of strange shapes, like a series of triangles, for example. And what would that look like? So the shape of a transiting planet is pretty distinctive. It has an ingress and egress and then kind of a flatter bottom. Triangle wouldn't quite look like that. And so we have to use very high precision facilities to be able to distinguish those shapes, often space telescopes. But yeah, again, it really depends on the nature of the structure. The sort of original canonical Dyson sphere would be something that's almost surrounding the entire star to use up to collect so much energy. If you surround the entire star, you don't see anything at all, right? Do you have a Dyson swarm, numerous panels going around? That might also be distinguishable from a single planet. But right now, we're kind of limited by our own imagination. So time will tell, or not.
And we can also be challenged by toddler meltdown at sometimes, which is something that even our most advanced technology can't really deal with.
Apologies for background sound. It's early.
What makes us human. Anyway, Ryan goes on to ask about what kind of limits will a non-detection place on the existence and scale of such structures. And I think that segues into a point that David Grinspoon makes, where he notes that if we don't find such structures, it might just mean that intelligent civilizations find a way to balance energy consumption with energy renewal and don't need such structures, or put differently, that intelligent species may behave intelligently. What are the comments on that? What are our hopes of behaving intelligent?
That makes me think of what Michael was talking about, the two endpoints. So maybe you want to take that one.
Yeah, sure. I think that's a great point, David. It plays into the hypothesis that I put forward, again, very, very speculative, of course, that maybe civilizations do end up either not learning how to strike that balance, that homeostasis between energy consumption and energy intake and usage, or they do, and then they don't require this grand expansion out into space, reaching type 2 or type 3 civilizations, and that's why we haven't seen evidence of extraterrestrial life visiting Earth yet. So I think that's a really good way of phrasing it.
Wonderful. So another question or comment and question that came up brings up an interesting point, and that is that if younger generations are a little bit more, say, aware of and focused on sustainable energy, responsible technologies, for example, potentially bringing us back into balance with our ecosystem. If we continue on this path, do we think we continue on this path? Does that give us more optimism on our L variable, for example? What are the comments and thoughts on the outlook?
Who wants to pick up the 8 ball?
I don't see anybody like over brimming with optimism here, but certainly I think it's if anybody's going to help us move in the right direction, certainly it's the younger generations.
Yeah,
right,
I think we have to help ourselves, Bill. There is this myth where aliens show up with great wisdom and all of a sudden show us the light. It's at some point, I tend to compare our civilization to a teenager, with enough brain to develop interesting tools, but not enough to understand the consequences of, what can happen when you're playing with them. And unfortunately, I would say that bad experiences is part of the experience. This is how you learn. But the problem with L is really, how much time do you have to learn when you are dealing with a planetary system? And so I think it is time for us not to wait for granddaddy to show up and, tell us what to do with our planet, but a way to be sustainable in the future with great expectancies of L duration is really to learn how our planet behaves and how we should behave with our planet.
Wonderful. So Catherine Denning noted that human civilizations have historically seemed to wobble between cycles of partial collapse and then resilience and then rebuilding. So it's not as though we've had this sort of continuous trajectory of progression, right? And so she wonders if societies can in fact wobble for a long time without fully solving their problems or threatening their L variable. Although she notes that sometimes if this wobble happens with increasing instability, things get a little more dicey. Any thoughts on this cycling between, collapse, resilience, and rebuilding?
I guess I'll take that one. So yes, indeed, there are certain parameters or metrics of civilization that go up and down with time. But I think that the ones that are really important in terms of, say, the population of the globe as a whole, and therefore the energy demand and the resource demand that we as a civilization require to keep going, is just monotonically increasing and accelerating at an ever faster pace. I'll just go back and cite some of Jeffrey Russ's work again, where he shows that cities actually do kind of just stick around forever. There have been very few cities that have died or disappeared from the face of the earth. Even if the nation states or the governments or the people in charge come and go, cities have stuck around for a long time. And this is mainly due to the fact that they have this superlinear scaling where they have increasing return with increasing size. That's autocatalytic feedback. It's a positive feedback that keeps them going. And so we may be, again, reaching a state where we can see our global civilization as one big city. And then what does that mean for our trajectory? It could lead to some kind of collapse unless we make that conscious shift in the fabric of our society.
Wonderful. Thank you, Michael. So we'll close with one question and ask maybe each of you to opine on this very, very quickly so we can keep on track here. But that is, how can we make politicians aware of the L variable and what the L variable has to offer in terms of bringing a different context and perspective to this question of climate change? Is there any hope? Well, one way might be to invite the politicians to the spring event that we're going to have to continue this conversation.
I guess, you know, it's politicians are going to be, they are worse than most of people because it's only when they won't be able to do anything else that they are going to react. Right now, we're seeing some goodwill with different organizations and committees and climate, and people are speaking louder and louder. The problem is the distribution of power, and until that we cannot fight the power of money with fossil fuels and other things, and the power that's related by, you know, having your hands on these resources that make the world go round at this point in time, is going to be really difficult. But you know, I think it's a matter of raising the awareness of more and more people. It's a grassroots, you know, work, and but it has to happen fast. In terms of politics, we need to do the things that we're doing right now. Scientists need to speak out. Politicians, we're already seeing the light, needs to speak out. We need to educate the young kids because they are coming as a blank page. If we're telling them to use in the future green resources, to behave like planetary citizens instead of individualistic, you know, entities, then we can change everything very, very quickly. And it starts with the children.
Great. Well, I think that's a wonderful way to wrap up this discussion. I will say that, I hope I'm going to pronounce this right, but Sivara Makrishna has noted that the B-deloid rotifer survives for 24,000 years frozen in Siberia. So maybe there are some lessons we can learn from B-deloid rotifer going forward. But in the meantime, I want to thank Nadia and Michael and Natalie and Anne-Marie. Wonderful panel, great discussion, great questions from the audience. Over the next 30 minutes, I think we're going to have a really interesting and exciting student panel from Georgetown University. So I'll be turning the podium over for that. And then we'll be having the next panel at about 1:45 coming up. So with that, thank you again, panelists. Thank you, audience, and Georgetown, take it away.
Thank you.
Thank you.
All right, welcome everyone. We represent a group of Georgetown students who are interested in space. We'll be presenting our next panel, which is Planetary Protection, a Student Perspective. So you might be wondering, what is planetary protection? To give you the basics, it concerns the protection of the Earth and other celestial bodies from biological cross-contamination. So to introduce ourselves, hello, my name is Clara Ma. I'll be your moderator today. I'm a senior at Georgetown. I'm studying science, technology, and international affairs, and I represent the Astronomical Society. I'll pass it over to Mia.
Hi, everybody. My name is Mia Kushner. I'm a junior also at Georgetown. I'm studying international politics and economics, and I am on our GU Astronomical Society as well.
I'm Owen. I'm a freshman studying science, technology, international affairs. I'm on the board of the Astronomy Society and also the Space Initiative.
Hi, everyone. I'm Zach. I am also a freshman studying science, technology, and international affairs. And I'm also in the Georgetown Astronomical Society and Space Initiative.
All right, thank you to all our panelists. We have a lot of questions prepared, so we're just gonna dive right in. The first question is on the commercial side. So for context, during the Apollo mission, NASA was really concerned that the moon rock samples it was gonna bring back to the Earth might carry living organisms, which could spread disease. And to counter this, they built the Lunar Sample Receiving Laboratory, which cost over $9 million at the time, which is over $7 million today. So knowing that, is it reasonable to burden developing space companies and countries today with the high cost required to disinfect spacecraft?
I believe the policy regime is already recognizing the overburdening of planetary protection on space companies and space programs around the world. We've already seen NASA recategorize the moon as a Category 2 planetary protection site, which allows much lower planetary protection regimes to take place, only requiring documentation of organics on the vehicle. I think that regime can be extended to Mars and beyond in order to allow for a more sustainable exploration that takes into account not only the importance of furthering our search for life to contextualize ourselves within the universe, but also to allow commercial companies to explore and really take part in this new space era.
We are watching the rise of a new space race globally, with many countries and companies trying to get a head start into the industry. And everybody wants access to space, but that is precisely why we have to be cautious about our approach to life on this world and life on other worlds as well. While I believe regulation and protocol can be taken too far, we should err on the side of caution if our ultimate goal is to protect the life that exists here and on other worlds. Yes, it may be expensive and laborious to maintain protective guidelines, but the effort itself is what will set a precedent for ethical space exploration. And reducing our footprint before we understand the environments we deal with is the key to moving forward properly.
I agree, Zach. I think erring on the side of caution is important. And I think the United States already has a lot of regulations and policies in place. So this could just be a facet of continuing those policies and moving forward. I think where we run into some contention, though, is bringing this onto the international scale, especially for these emerging companies, these emerging countries in the space industry. We don't want to deter them from advancing, developing, exploring because of the increased costs or extra steps that this would incur. So I think while on the domestic side, we could easily be taking more precautions and putting these regulations in place, I think it becomes harder to do so on the international scale.
All right, thank you to all our panelists for your very wise answers. Next, we'll be asking a question on the medical side of things. Again, for context, in 1969, Michael Crichton, who's the author of Jurassic Park, he published a novel named The Andromeda Strain, and it was about a disease outbreak of an alien microbe that was brought back to Earth in a spacecraft that was not properly decontaminated. So my question for you today is, should a quarantine be required for all passengers who travel to space without landing on another planet or moon? Or should it be required only for those who do land on another planet or moon and then come back? And if so, what level of quarantine? How stringent should it be?
So the issue with planetary protection, the threat may be minimal, but the stakes are astronomical. On Apollo 7, 3 astronauts contracted severe colds and had severe congestion that was worsened by the effects of microgravity. When it comes to protecting humankind, it is necessary to be cautious through quarantine, especially coming out of a global pandemic. We know this to be true. We should take every measure necessary to ensure that there is no backward contamination here on Earth until we understand life and its nature on other celestial bodies. If that means prolonged quarantine is necessary, then that is what we should pursue. If we know an environment is sterile, say like the moon or in a vacuum of space, then we can adjust accordingly. But until we know for sure, we have to take those precautions to protect life.
I think it's interesting as well how you link this to the current situation with COVID, because I know a lot of countries have had a decrease in tourism. Granted, they do have the domestic restrictions, but I know quarantines have also caused people to turn away from this tourism. So as we have the rise of the private sector, especially looking for these space tourism ventures where they're going to send people out into space, I think it's fascinating to try to decipher how quarantines are going to impact that, as we've seen them directly impact travel here on Earth.
That's a very good answer. And actually, to follow up on that, Mia, I'd like to ask you, in light of the pandemic specifically, should we consider planetary protection and biological contamination for extraterrestrial sources a national security priority?
I think it really comes down to the likelihood of two factors. So I think first, the likelihood of us finding something that is equivalent to the current pandemic that we are facing. We don't necessarily know what's out there, and we don't know that the magnitude of something is going to match what we've seen in the past. I guess, year and a half, 2 years now with COVID-19. I think the second thing this comes down to is what the international community is doing, because while the United States can take as many efforts as they would like to ensure planetary protection and proper sanitization, if the rest of the world isn't going to be doing this, we are not going to see the same impacts that we would if we were able to get a group consensus and some amount of standardization of these practices. So I think it really comes down to the two of those, because if one country brings back one small microbe, organism, any bit of bacteria, I mean, that could really impact the entire world.
All right, thank you, Mia. So in light of all our panelists' opinions here, I'm going to ask you guys, should Congress or the UN or another national or transnational organization enforce the requirement for all nations and companies launching spacecraft to disinfect their spacecraft?
So the legal backing for planetary protection is found in Article 9 of the Outer Space Treaty, which says to conduct exploration of them, being planetary bodies, to avoid their harmful contamination and also adverse changes in the environment of the Earth. So there's already international law on the subject, but the issue, again, with all international agreements is in enforcement of the issue. Norms have obviously been degraded, as we've seen just in the past week with the Russian ASAT test, which put the International Space Station in threat. Norms are extremely important in the space field, and therefore the US should take a lead in enforcing norms in the international arena. It's an easy way for the United States to show its leadership in science and also encourage exploration of space under a cooperative banner, because planetary protection is one of the easiest things to agree on. So by using its facilities and its technological know-how, the United States can encourage cooperation with even competitors like China, because planetary protection benefits us all and shouldn't be controversial.
I agree. I like that you brought up those international agreements that we do have, because I think while we do have those agreements, it's incredibly hard to enforce because not all countries are part of every agreement that's out there. I think, however, you bring up a really good point as to how the United States could use this to their strategic advantage. So the United States is able to promote our values internationally and work on more collaboration with these measures. And I think there are three major advantages to this if the United States is to go out and engage in knowledge sharing and engage in collaboration. I think the first is that the United States is going to promote responsible use of space internationally, which is going to set a better world order moving forward, where we've got all this competition that's going on, which is great for industry and development, but we need to be doing so responsibly. I think second, the United States benefits from having the continuity and even interoperability with foreign countries in terms of going to space and our missions. And I think third, in terms of great power competition that's going on in the world right now, it's good that the United States is promoting our values and gaining allies.
All right, thank you both. So moving on to questions that are more from the environmental side of things, specifically on planetary science and ethics. I'm going to ask all of you here, how would you address the impact we have on other worlds and the life that might exist there? Again, planetary protection is important because it concerns our own safety from biological contamination reasons, but also for the delicateness of our environment and that of other planets. So again, I'll ask you, how would you address the impact we have on other worlds and the life that might exist there?
I think that one of the fundamental contradictions of planetary protection is that we have to look for life and signs of life without altering and affecting the life that may potentially exist. You can see that with searching for life on Europa and Enceladus, where missions like Europa Clipper fly through the plumes of cryovolcanoes on these moons, because we can't really get into the subsurface oceans without affecting the life that may be down there. And the same with Mars. If we want to explore life on Mars, we have to be extremely careful about searching ice deposits that may lead to subsurface pockets of liquid water, or affecting life that might exist in free-flowing water on the Martian surface. We also have to look forward to manned missions on Mars and other bodies, because currently under current COSPAR planetary protection guidelines, there is no room for manned exploration under these guidelines. So there is a need for new planetary protection guidelines that are forward-looking and can take things like Starship and the Moon to Mars program into account to help us not only search for life and achieve all the science goals, but also achieve a robust in-space economy.
Astrobiology has taught us that life exists in the most extreme environments. It is hardy, it perseveres, and it endures. Evidence points to the fact that on Mars, life likely exists in subterranean environments. And as we send robots and humans to search for life on Mars, we search for life living on the edge. Until we discover, though, what that looks like and what the nature of those environments are, how we would interact with them as humankind, we have to lessen our impact as much as possible. Yesterday, with the National Academy of Sciences, Elon Musk addressed planetary protection and discussed having limited zones in which we operate on celestial bodies like the moon or Mars. It is these kinds of methods that will allow us to approach life properly, microbial or not. And then once we discover what life looks like, we can address the larger philosophical questions of our place in the universe and how we interact with and protect life on other worlds.
I think if we're looking at our impacts on life on other planets or anywhere within the space that we have, I think it comes down to this really interesting discussion of how our biological impacts are also in line with our kinetic impacts. And by kinetic impacts, I'm talking about if there is anti-satellite efforts that are going to scatter space debris or anything else that is going to leave that debris and the actual physical pieces that could potentially harm another form of life. So I think as we have a lot of focus right now on these kinetic aspects of our activity in space, and we're working to prevent space debris, I think the biological aspects of our space travel should also be looped into this discussion. So our impact on other worlds cannot just be limited to these physical aspects, but also to the biological. And I think as our space exploration does move away from manned systems to more technological and robotic systems, I think as this becomes increasingly automated, the human impact is being removed, and thus it becomes potentially even easier to sterilize equipment. So I think the way that this question shapes itself as we progress and as we move towards more technology, and as we are having these two different areas running parallel in terms of our impacts on other planets, I think this is really going to be what shapes planetary protection moving forward and the questions that we're asking.
Thank you both. I'd like to add, I think it's interesting to consider the implications of planetary protection when we've moved to this stage where we have human settlements on Mars. For example, what we do with waste disposal, what we would do with growing food, but we'll think about that later. So to get into the larger picture scope of things, I'd like to ask everyone here, what do you think is the biggest threat to planetary protection, knowing about national security concerns, biological concerns, environmental concerns, and habitability and environmental concerns? I'm going to ask you, what should we do about planetary protection?
I think as my fellow panelists and I have really hit on, planetary protection is hard. It's difficult, time-consuming, and often extremely expensive, but it's also really important to how we view space and how we're going to participate in space as we move forward into a spacefaring civilization. So I think it's key that we really agree on space planetary protection and agree and move forward to address these issues united, because that can then be a base for future understanding and cooperation on larger issues, as Mia mentioned, regarding security and relations. It also represents a new phase in our search for life. As we launch the James Webb Space Telescope, we undertake moon missions under the Artemis program. We're really reaching an inflection point, I think, in our both governmental and commercial aspects of space exploration. So regulators need to take into account the growing size of the space economy, the growing participants in space, and use that to create a coherent regulatory framework to allow for sustainable space development. And just to kind of end off, I feel like if we treat the potential for extraterrestrial life, the number is 1 in 10,000 of chance of impacting extraterrestrial life, I feel like that leaves us a lesson for life back here on Earth. If we're so careful about potential life on other planets, then what does that say about how we treat life here on our own? And I think that's one of the values of space exploration in informing pictures of our own planet. Thank you.
I agree, Owen. I really like the point you bring up about international agreement. I think the biggest threat that we are currently facing in terms of planetary protection is negligence, especially in such a wake of competition. I think if we are having countries or companies that are working just to develop and move quickly and are not taking the proper procedures to work collaboratively with other nations, share this knowledge, share our information about how we can best protect life here on Earth, I think that's definitely going to be the biggest threat moving forward. I think we find negligence in a few different aspects as well. I think we have negligence in the competitive sense of we race to space and we race to go do all these advancements, but we're not necessarily taking the time to break down the risks and work with our international partners to best evaluate and address these risks. I think we find negligence in being proactive as well. I think if we really want to become a multi-planetary species or establish these permanent bases or even temporary bases on other planets, I think this is an issue that we're going to need to begin to address internationally, and we're going to need to start developing norms and standards for. If we truly want to be proactive and prepared, we need to have these international understandings rather than having to be reactive. This is exactly going back to the conversation we had previously about the COVID-19 pandemic. This is the exact issue that we ran into, was we had to be completely reactive and we weren't able to have systems in place, have agreements in place, and work together to actually fix the problems that we're facing. Additionally, I think if we are talking about this, and maybe this is going on a small amount of a tangent, but if we're talking about this idea of these permanent bases, I think we also need to discuss how we're going to introduce interaction with other forms of life and how we keep from creating a biological threat when we are meshing into these different ecosystems.
The threat of forward and backward contamination is a looming threat that we have yet to fully address as we figure out what space exploration will look like in the coming decades. And because of this risk, we need to prioritize ethical space exploration and the protection of life in all of its forms across the universe. And that will take place through the policies that we create within the coming years. To collect our thoughts, ultimately, planetary protection in all of its facets will allow us to reap back benefits for those on Earth. Everything that we learn at the frontier will be used to benefit us and benefit the global welfare of those who live here. In our shared mission in Georgetown to increase space awareness on campus and to promote space here on campus, we believe planetary protection is a way to support Earth and humanity through an interdisciplinary approach. We can create a future of space exploration that protects life as we know it and life that we have yet to discover.
Thank you all, and especially thank you, Zach, for that very profound answer. To wrap this panel up, I think this touches on a pretty good set of things that have been happening recently. To let everyone know, all the panelists here are students of varying backgrounds at Georgetown University who all have their own perspectives, but who all agree that planetary protection and habitability are important issues we should address. And given that we are so young and only university students, again, we represent people who have medical backgrounds, policy backgrounds, and defense backgrounds. We also represent two clubs here on campus, which are the Georgetown University Astronomical Society and the Georgetown University Space Initiative, both of which are really passionate about space. And we're so happy to have been able to bring you this panel here today. Again, we would like to thank the SETI Institute for providing us this opportunity. And now I'd like to pass it on to our wonderful, actually, Bill, looks like you're about to speak. Would you like to say a few things before we go into Q&A?
Oh, yes, if you have time to go to Q&A, let's do that first, and then I'll pop on, particularly on the subject of planetary protection. So why don't you do some Q&A? We've got about 10 more minutes total, so or just under.
Yeah, thank you so much, Bill.
You bet.
I'd like to pass on now to our wonderful professor and mentor, Dagmar DeGroo, without which we could not have made this panel or this event happen today. So Professor DeGroo, I'm now handing it over to you to ask some interesting questions from the Q&A to our student panelists.
Hey, thank you so much, Clara, and what a fantastic panel you guys have organized. We do have a few questions. One is about the USSR's Venera probes that they sent to Venus. These probes, Bob Hranek argues, were not sterilized before launch. So if we do really detect life in the upper atmosphere of Venus, we won't be able to be 100% sure it did not arrive from Earth. So this is a problem that affects Venus as well. I wonder if you could comment a little bit more on forward contamination, maybe some issues that we should be thinking about, some worlds that we should be particularly protective of.
Yeah, so there's already a categorization system where worlds like Enceladus and Europa with their subsurface oceans and geothermal activity are some of the highest, they have some of the highest standards for protecting payloads that are sent there. Venus is much lower on the list, but especially that layer in the upper atmosphere is a very crucial zone for Venus's activities. And now that we're sending 2 missions to Venus in the near future, we need to really be aware of the threats, as you said, of life on Venus and affecting it. So much more stringent planetary protection measures should obviously be undertaken for probes entering Venus's upper atmosphere due to the phosphine discovery and the potentials of life that we've now discovered there.
Mia and Zach, Claire, do you have something to add to that, or should we move on?
International guidelines matter. For example, quarantine looks much different for the Russians than it does for us, and procedure changes depending on the space agency, on the company even. So what really will matter, especially when it comes to the search for life, especially on Venus, on Mars, what will matter is creating guidelines that everyone adheres to, which is the hard part, but ensuring that everyone is disinfecting, is going through the proper precautions to make sure that we don't have data that is affected by organisms or microbials that have persisted on a spacecraft in any sense of the matter.
So, Clara, you mentioned the Lunar Receiving Laboratory. This is this large complex that was set up during the Apollo program, of course, to protect the Earth from lunar microbes. It wasn't known whether these microbes actually existed or not. And the problem with the LRL, even though it was at the absolute cutting edge of technology at the time, is that it failed, essentially. There were many, many different breaches. And it seemed clear that the need to test the samples as quickly as possible was at odds with the need to actually, protect the Earth from microbes that might exist in these samples. So with that in mind, do you have confidence about samples that might be returned from Mars, for example, brought to Earth, studied in labs here? Is there something we can learn from the LRL that should make us suspicious of these efforts, and that maybe should guide us to look for life in situ on Mars, for example, rather than bringing samples back to Earth? Or is these fears all kind of overblown? I think a lot of people would say that they are. Well, what do you think?
I think, the example of the Lunar Receiving Laboratory is really interesting because we put so much money into it and yet it still failed ultimately. I think now, being as cautious as we are being as cautious as we should be in this modern day and having better technology, we would have a better shot at building a quarantine facility for return samples and testing up those return samples. But you mentioned in situ collection of samples on Mars. I think that's also a very good idea. Knowing that any sample collected on Mars could be tested locally, but also on the flight back to Earth, that alone would take like a year. So in that process, we would have a kind of on-the-spot quarantine facility. And again, we could continue to do tests on the spaceship returning the samples from Mars. So I think there's definitely ways around it. There's no need to be not cautious because we have the technology, the budget, and the time before a sample is returned to really thoroughly test it and to quarantine it. So I think it's possible.
I'm also wondering, Clara, building off of that, if all of the testing has to be done in one location, or if there's the ability to somehow split it up, where you could do some amount in situ on a different planet, any planet really, and then be able to continue those tests as you come back to Earth and then once you get back on the Earth. So maybe there's a way that you're able to split it up to take caution while also keeping things moving and not getting stalled.
Also wondering about new space. So GOOSEY, the Georgetown University Space Initiative, is kind of all about new space, these companies that now have big dreams in space, right? SpaceX being the best example of that. Well, these companies might be taking risks, right, with planetary environments that space agencies maybe do not. Right? There was just an instance where a whole bunch of water bears, I believe, were deposited on the moon. These are tiny microbes that are highly resistant to exposure to the vacuum of space. And a whole bunch of them were deposited there by a private mission to the moon from Israel. Actually crashed on the moon's surface. So question is new space a problem here, right? Should new space be more carefully regulated? or you know, are the demands, or not even demands, but the kind of ambitions of new space companies, are those more important than preserving a bunch of microbes on Mars or on the moon, or on Venus for that matter?
Yeah, so with the tardigrades on the moon, it's tough, because if we are to ethically explore space and learn from the lessons and the problems we've caused in the past as humanity, we do have to set guidelines that everyone adheres to. In our pursuit of expanding into the universe, we have to make sure that we take a step back and protect life on other worlds. And it'll come down to our priorities as a civilization. But yeah, we have to learn from our past mistakes and kind of move forward and use space as a canvas in which to ethically explore space and do it in the right way.
And just to quickly add on, I think NASA's already shown, a lot of NASA and other regulatory agencies have shown a lot of willingness to be adaptable and to really work with commercial partners on these issues. And I mentioned how the moon was recategorized to help aid the commercial lunar payload system. And I think as we look to Mars and hopefully getting more payloads on Mars that are commercially operated, I think that there's been studies done that show that the first meter of Martian soil is extremely hostile to Earth life. And between the latitudes about 40 south to 40 north, there is very little chance that microbes transported from Earth could survive for long periods of time, thanks to the lack of water and UV radiation. So by helping to adapt regulations, not to over-facilitate commercial participation, but just to provide a reasonable framework where commercial companies can operate and help further the science goals that we all want, I think would be a great way to help, you know, encourage a sustainable space economy.
Well, how about we end it there? And I would like to close by thanking you, Clara, thanking you, Zach, Mia, Owen, for a really interesting and stimulating panel. You guys are incredibly eloquent and thoughtful, and I was just blown away by this. So thank you so much. That was fantastic.
I think it was great. You guys did a wonderful job. Thank you so much, Clara and Zach and Mia and Owen. And what's really cool is your long-term future careers are now set, because we expect you all to show up at the SETI Institute as future research scientists, policymakers, and educators. So, and one of you can have my job. So just amazing. You guys are, it was brilliant. I just wanted to note, because of how much this was featured in your conversation, you know, NASA does have an Office of Planetary Protection, and it is in the mission safety and assurance part of NASA. And interestingly, the SETI Institute has the primary contract for planetary protection with NASA. And that means, among other things, we do the biological assays of spacecraft before they are launched, things like the Perseverance rover, et cetera. But planetary protection, as you most eloquently noted, is about preventing forward contamination of other worlds we might visit and backward contamination, bringing things back here. So it is an area of concern and interest to NASA, to the Institute. And in fact, since you talked about new space, you know, a big part of this endeavor is really about education and informing the public, and, you know, commercial space, as well as, you know, other governments around the world, and doing, you know, responsible space exploration. So I think Rebecca, my colleague, can put in the chat the link to the website, the planetary protection website for NASA, that we also contribute to, and maybe the entire group of Georgetown students could become a subsidiary on that contract, because you're obviously well versed in the subject. So with that, let me turn this over to Dagmar. Thank you, Clara and team, once again. Dagmar, I think you're ready to launch us into the next panel about habitability at home.
Absolutely. Yeah. Thank you so much, Bill. So the next panel is all about a volatile Earth, and how changes in the Earth have shaped the conditions for habitability on our planet. And to get it started, here's an overview video by SETI co-founder Jill Tarter.
For now, we know of only one planet that can be easily inhabited by beings like ourselves. That's Earth. Yet our Earth was not always a habitable home for life. Early in its 4.5 billion year life, it was nearly destroyed after a collision with another planet, Theia, that ultimately formed our moon. Since then, it's been bombarded with comets and asteroids that caused regional or even global destruction. The most famous of these impacts doomed the dinosaurs, and thereby gave mammals yet a chance to inherit the globe. Less spectacular impacts mattered too. Some scientists believe that a small asteroid smashed into the ice sheets of North America just as the last ice age was beginning to wane. In an instant, ice became meltwater, pouring into the Atlantic in such quantities that oceanic circulation shut down. The result? A millennium-long cold period across the northern hemisphere that many human populations only narrowly survived. The threat to life has not only come from beyond Earth, it also originated within our planet. Immense volcanic eruptions, for example, have caused climate-altering devastation, whether slowly through the gradual release of warming greenhouse gases across thousands of years, or suddenly in explosions that abruptly cooled the Earth. Some 70,000 years ago, our ancestors coped with the eruption of Mount Toba, an explosion far more powerful than we could create with all our nuclear weapons put together. Gentler, but equally irresistible forces have also created and destroyed life on our world. The leisurely migration of tectonic plates rerouted the circulation of the oceans and lifted up mountains that scrape warming gases out of the atmosphere, transforming Earth's climate. Cycles in Earth's orbit and rotation, occurring over thousands of years, allowed glaciers to cover most of the planets, or recalled them back to the poles. Sea levels surged and subsided, at times permitting and at other times constraining the migration of early humans. We became human biologically and culturally as we struggled to adapt to these enormous changes. Life, including human life, has long created and destroyed the conditions for habitability on Earth. 2 billion years ago, for example, cyanobacteria for the first time infused Earth's atmosphere with oxygen. The planet probably cooled in response, so much so that ice may have covered its entire surface. Today, we are transforming our Earth. We have become one of the great forces of nature, to such an extent that many scientists now believe we live in an Anthropocene, a geological epoch defined by our power over the Earth. Every year, we release billions of tons of greenhouse gases into the atmosphere, warming our home to heights unprecedented for millions of years. It remains to be seen whether we will awake to that threat that we have created to our own survival and change our ways before it's too late.
So good morning, everyone. I'm Paul Vuzin, the Earth and Planetary Science reporter here at Science Magazine, which means I cover the solar system, but I also spend a lot of my time thinking about topics here on Earth, like climate change and the retreating Greenland ice sheet behind me. And I'm joined by an esteemed panel today. First, Ellen Stofan, the Undersecretary for Science and Research at the Smithsonian Institution and NASA's former chief scientist. Chris House, the Director of Planetary System Science Center at Penn State. And John Brook, an environmental historian and Director of the Center for Historical Research at The Ohio State University, who also wrote, I was thrilled to find out, A History of My Childhood Home in Worcester County, Massachusetts. We're here to tackle a simple topic, the deep 4.5 billion year geological history of Earth, the conditions that led to the rise of life and much later civilization and the demise of us all. So our panelists have a few prepared remarks and then we'll get down to discussion. And if you have any questions for our panelists, please submit them in the Q&A below. Ellen, let's start with you, please.
Sure, thank you so much. And it's really a pleasure to be here today. And I really apologize. I have a hard stop at 12:30, so I'm gonna have to leave early. this is one of my favorite topics. So I'm really glad we're discussing this here today. And it comes from a couple different things. And Jill really clearly laid this out in the video, and I think an excellent way. And one of the things I think it's hard to get your head around is in planetary science, which is obviously my background. So that's the way I approach this question. We talked so much about the habitability zone, right? Venus is too hot, Mars is too cold, Earth is just right. And life has persisted on this planet because of the stability of the conditions over time, with some little glitches like massive asteroid impacts. But I think if you think of habitability and that habitable zone, it's not just a place. It's not just like, oh, it's a distance from your parent star. It can also be a time period, because let's go to Venus. All right, early in Venus's history, we're pretty sure that for some amount of time, due to looking at the chemistry of the atmosphere, that Venus retained water on its surface. And so Venus had a probably relatively brief time period when life could have evolved. And so did it, as people were talking about in the previous session, did life go to Venus's clouds? We don't know. But so Venus could have been habitable for a short period of time. And the question was it habitable long enough so that life could have evolved to adapt to the changing conditions, which probably changed relatively rapidly? Go to Mars, same situation, right? I mean, now we're looking from Perseverance, from Curiosity, these amazing sequences of sedimentary rocks. So not only was there water on the surface, but water had to have persisted for some amount of time. And so again, Mars was potentially habitable. Did the conditions persist for long enough for life to have actually taken hold? Some of us think probably yes. Some people think probably no. And we're not going to know until we go and crack open enough rocks to actually find out. But this idea of habitability depending on stable planetary conditions that persist over long periods of time to get to complex life. So you really have to look at this deep time history of planets and see how they vary. It's not just saying, oh, we found an Earth-like planet around another star. Yes, but how long has that habitability persisted? Is it stable? Is it widely changing? Can life adapt to it? These are the kind of more complex questions that we have to answer. And just finally, I want to put in a huge plug for our exhibit at the Smithsonian's Natural History Museum called Deep Time, which actually goes through all of those things that Jill talked about, talking about the fact that you can put the climate crisis, planetary crises have happened in the past due to inside forces, due to outside forces. And now this is a new kind of crisis that we're in, and it's because of us.
Thanks, Ellen. It's a great exhibit. It also has dinosaurs, so there's another selling point. And now we can turn to Chris.
Yeah, thank you, Paul, for the introduction. Also, thank you, Ellen, for laying out the provocative vision that terrestrial planets have a finite phase of habitability. There also might be a finite window of time for the origin of life to occur on a terrestrial planet. The first point I want to make is that there's a really long record of life on Earth, over 3.5 billion years. The fact that life appears to have risen quickly after Earth formed could either mean that the origin of life is highly probable, given the right conditions on a terrestrial planet, or alternatively, it could mean that the origin of life on terrestrial planets requires a young star system, making it only something that can happen quickly if it's going to happen before that window closes. The next striking feature of the record of life on Earth is that in spite of dramatic metabolic innovation in the microbial world, it still takes billions of years before the Earth has its first animals. Now, there's plenty of metabolic and genetic innovation: methane production in sediments, oxygen production in during photosynthesis, especially in surface waters, fermentation of organic matter, microbial respiration of iron, various sulfur compounds, and oxygen. But it's not until about 500 million years ago, a billion years ago, and then 500 million years ago, that we see animals, and then ultimately 500 million years ago, complex ecosystems with animal predators, animal prey, resulting in trophic levels. So, why did it take so long to get animals? It's puzzling, but we can conclude that in spite of a remarkable level of innovation by microbes, for billions of years, the Earth had essentially no indication that intelligence or technology was even possible. So it's therefore quite possible that the cosmos is full of green slime or purple slime or pink slime, you take your pick, but largely absent of technology. Finally, we see multiple times over the history of our planet of dramatic environmental change. The video included the role of meteorite impacts and supervolcanoes, both of which have occurred during hominid history. There's also been dozens of massive basalt flows lasting millions of years called the large igneous provinces. And those drive up volcanic gases in the atmosphere, they alter climate. And the most recent was perhaps the Columbia River basalt, so about 10 million years ago. Humanity hasn't had to deal with one of these. But so overall, there's in the past times of steady long-term change, as well as periods of dramatic and rapid change. And perhaps the most dramatic, 1 billion years ago, for example, the Earth had 2 extreme glacial events with sea ice going from pole to equator. And getting out of one of these snowball Earths is perhaps even more dramatic, as the greenhouse gases from volcanic eruption not being balanced by weathering goes up to really high levels. You can dramatically pop out of one of these events, going from global ice to global tropical conditions in essentially a geologic instant. So the lesson for humans may be that really, that we really do need to tread lightly on the Earth, as rapid warming is possible due to various tipping points in our geochemical cycles. Thanks, Paul.
Great, thank you, Chris. And those humans, how do they fit into this deep history? For that, we have John. Oh, you're still muted, John.
Thank you, Alan and Chris, for setting the stage. Sorry about the muting. I'm going to work backward from the now to back into at least 1 billion years ago, but to make the basic point that we cannot tolerate as human beings living on a planet with approaching 8 billion people with a very delicate, as we've seen recently, relationships with nature, with enormous populations of people suddenly coming or emerging out of nowhere. We can't tolerate the kinds of changes that have happened on the planet Earth in evolutionary time. I mean, there's a basic premise of evolutionary history that in its transitions from habitability to various levels of inhabitability have driven evolution. Evolution is something that is driven by stress and the action of genetics, which is another little wild card that we really haven't had on the table yet. So we have to think about the tension between our circumstances in the Holocene, where we've had essentially CO2, atmospheric CO2 levels is a good measure, somewhere between 260 and 280 for 10,000 years, following amazing variation over huge amounts of time back through the Pleistocene in gigantic ice age events, which followed the degradation of the greenhouse world of the early Cenozoic. When we talk about great transitions, we can talk about great super plume events causing igneous provinces that put enormous amounts of CO2 in the atmosphere. Simultaneous with the asteroid of the dinosaur destroying asteroid, we had this enormous event of that created the great peak of heat and CO2 at the end of the Cretaceous, leading to a peak that then, ever since then, has been descending into an ice house. We are in the ice house. We've been living in an ice house in wildly unstable conditions, and only in the last 10,000 years have popped into a relatively stable Holocene world in which all of agriculture and civilization as we know it has emerged. 10,000 years is a microscopic amount of time, and in the last 150 years, we have popped, really the last 70 years, we've popped the level of CO2 up to levels that haven't been seen for probably 3 million, possibly 35 million years. So we are creating our own instability through the Anthropocene in levels that we really can't tolerate. I think I'll stop there.
Great. Thank you, John. And always, when it comes to climate change, it's always an optimistic story. So let's talk. I'd like to keep this as free-flowing as possible. Hopefully you hear from me as little as possible. I have a few questions to just start directing, but I might direct it to one person, but feel free to jump in as well. So John, staying in the geological present, but going just back just a little bit to the Pleistocene, the last time we came out of the Ice Age, and our ancestors, maybe who knows when they in North America came over to North America, but just what lessons can we take from the adaptability they had then, and do we retain any of that, or our technological civilization, our cities? I mean, what can we learn from that, if anything?
Well, I mean, you have to keep in mind that modern humanity had reached essentially modern intellectual skills, probably 100,000, 150,000 years ago. But the conditions of instability surrounding them were such that there really were decisive events that even those abilities couldn't resist. There were massive natural events, droughts that would kept population down to probably maximum 3 million people. So one of the sort of striking features of the early Holocene is, I mean, the archaeologists say it happened slowly. It took thousands of years, but in geological time, it happened instantaneously. Agriculture emerged out of the already existing abilities. And so clearly, we are building on the technosphere that our Upper Paleolithic, Middle Paleolithic, Upper Paleolithic, and Neolithic forebears established, and taken them to a massive new heights. I mean, the levels of innovation that are going to put us into space, or have put us into space, are phenomenal relative to that past. But you can see continuities in rising to challenge.
Okay, and Ellen, I thought, now to kind of jump way back, you mentioned these kind of phases of habitability that Venus and Earth, or Venus and Mars had, and their endings. What can we learn about how the habitability on Earth may end from these two planets, these two sister planets? And in a kind of more high concept question of, if you transpose humanity of today, all of our means, onto these planets and their kind of habitable optimum, assuming we didn't get bombarded out of existence, could we halt those environmental changes that rendered them inhabitable?
Yeah, it's a great question, right? And there's been some interesting chat in the room about this concept of the habitable zone, because of course, when you think about the fact that there could be life under the ice on Europa, Enceladus, maybe even on Titan, but that's not the kind of complex life that Chris talked about, right? And so like us. And so if you think of, you need a planet that has life that could persist on the surface to allow it to persist long enough to get complex enough to move towards technology. It's that stability of conditions. And I think if you look at what happened to Venus, probably a little too close to the sun, maybe a little different chemistry. We really don't know. That's why we need to go back to Venus and make a ton of measurements, which we're doing with 2 new missions, which we're really excited about, to get at how did Venus have habitable conditions? How long did they persist, and what caused them to go away? Still open questions there. On Mars, it's a little clearer, right? Mars is a little too small, cold, its dynamo died, it lost its magnetic field, solar wind starts stripping the atmosphere. That's not anything we can do anything about, right? It's just, that's like, okay, you don't recover from that. But I think what we've learned from looking at the atmospheres of Mars, the atmosphere of Venus, the atmosphere of Titan, this comparative climatology that we can do has certainly shown us, atmospheric conditions can change. Life, as we talked about, can cause atmospheric conditions to change for the better when oxygen was produced, and now for the worse as we put too much CO2 in the atmosphere. And so again, the planets set the context to me of what's happening. But no, a lot of these conditions tend to be irreversible, which is why I think for many of us, it's so frustrating to see us doing this to ourselves. Because, the Earth is, there's no planet B. The Earth is where we can live. And the fact that we're taking an active role in disrupting that is distressing, and we've got to turn it around, and we've got time.
Right. Chris, thinking of the kind of origins of life here on Earth, what's the current thinking on how life began here? What was kind of both the environment, that might have kind of cradled the development, and how did that happen? I know there's debate, of course, is not a settled answer there, but how many different kind of conditions could you imagine that might end up in this kind of present state?
Yeah, it's a great question. I mean, it's a great question because it's still one of the great unanswered questions in science. The reality is we don't exactly know how life began. And you say there's debate. I mean, there's actually like a pretty major schism in origin of life field that goes back decades, and it changes, depending on which decade you look at. The exact schism is different. Right now, it would sort of be couched as, do you need a replicator first? Are you trying to get a gooey molecule that can, has information involved with it? Or are you trying to get metabolism first, where you're thinking about a connection of interreacting, complex reactions in some sort of pool or vesicle? And so, those are all technical, rather technical debates. But for this particular audience, I think the take-home lesson is that that a lot of the basics still exist. That we know we need a medium like water. Doesn't necessarily probably have to be water. When you look at Titan, there's other options. Maybe a methane ocean might work, or you can get more creative. Maybe pools of sulfur on Io. I don't know, but you definitely need a liquid medium, and you need for as life as we know it, you need carbon. And so that may be why the solar system is early on is a great place to do it, because there's lots of CO and CO2 swirling around and on planetesimals and on early planets. But I think the field's also very optimistic about looking for life in Europa and Enceladus under the ice. And that would be a very, that would be more of a hydrothermal origin, which is quite possible. So I think all those options are still on the table, and it may turn out to be a probable event that happens whenever you have energy and water. But on the converse, we know plenty of meteorites, parent bodies had plenty of water and plenty of energy and didn't form life. So it's a great problem, and I think we're at the threshold of learning a lot about it.
And now for any of you, looking at the kind of chain that led to human civilization, all these kind of different things that had to happen from origin of life to multicellularity, great oxidation event, impacts, etc. I mean, what seems like the most unlikely moment? Kind of what is the weakest link in that chain up to the present day, not thinking of the future?
Well, I'll just launch out there, which I've spent a lot of time thinking about this, and what is really very striking is I mean, yes, advanced primates were emerged at that just before the Cenozoic started, but the genetic popping of transposable elements. I mean, there's something very special that happens in the genetics of advanced primates that is hard to pin down. I mean, why? I mean, that's what's going to make the difference. This process of how the genetics shifted to produce something with an upper story, and that is very much up for grabs. So the events of roughly 5 to 2 million years ago are very, very important, and whether the driver of increasing variability in East Africa is sufficient to really explain that is somewhat up for grabs. But I don't want to get into other domains here, but it's clearly the genetic action is very, very important, and we don't know quite enough about that.
Yeah, I'd agree. And it's interesting because we have some group at the Smithsonian who does a lot of work in East Africa, and they recently had a paper come out talking about the effect of climate stress, Rick Potts, Kay Berenger, and others. about the fact of climate stressors and how that helped humans move out of Africa into Europe. And
Exactly.
really a lot of interesting work going on in that field. But you think, okay, what if the KT impact occurred right at that point? And so there's a lot of serendipity to me in this. Like, right, we had the KT impact and it nearly crushed us, but we came back from it. And at points of stress, there was enough stress to actually spur us to become more complex, as John just talked about, but didn't kill us. And that balance, which I would argue is a whole lot of luck, and serendipity, that's what I find really interesting, because it could have been game over at multiple points.
Right. The most recent one of those is there's a series of articles about geomagnetic reversals, and apparently there was a big geomagnetic reversal at 42,000, which was pretty terminal for the Neanderthals, but modern humans made it through. So I don't know how valid this argument is, but it's an interesting new feature of the, it's kind of replacing the Mount Toba article. Mount Toba is kind of being pushed back as a very important impactor. Now this new geomagnetic argument is emerging.
I know that article appeared in Science, but there's a lot of skepticism over from the paleoclimate community on it.
Right.
Well, I'll also just jump in to kind of reiterate what both John and Ellen said, that I would agree that in terms of what happened here and why is it potentially different, it's very puzzling that we got the level of intellect for whatever reason to get to technology. You can go back plenty of back in paleontology, you can go back, plenty of different species that looked rather intelligent. You can look to modern organisms. The octopi is just extraordinary. And, cephalopods go back 500 million years. I think John kind of hit upon it, with genetics. It's probably, interfering RNA is probably part of the story. We don't really fully understand what interfering RNA is and why it's so important, but it looks like for one reason or another, an entirely different way of doing gene expression and finally controlling gene expression arose at a time, like Ellen said, of East Africa was doing some pretty wild things. So, and East Africa is a rift zone. We even talked about that. Maybe the fact that it all happened in a rift zone matters. You can see, hominid footprints across ash beds, which is just so dramatic.
Yeah, right. Yeah. No, you have to wonder about that volcanic tectonic context and toxins, and that they're simultaneously experiencing the toxins from volcanics and the toxins from a new burning savanna environments. The fires, big wildfires that are expanding savanna into the forest, are putting toxins in the air. We literally, those footprints are incredibly important because they are the symbol of our really toxic origins in a certain sense.
So looking at Earth's kind of deep history and now thinking forward, obviously we have anthropogenic climate change. I mean, is that the kind of current largest threat to human civilization, or is it something else in your mind? Is it nuclear war, a supernova, an impact, a large igneous province coming up in our business?
Well, I've been teaching astrobiology for 21 years at Penn State here. And it's funny to talk about these topics with the students and see what they think is going to limit L. It does change over what's going on. If you go further back, obviously during when Frank Drake first gave the talk at Green Bank, everybody's worried about nuclear war, that probably got to be the most extreme worry in early 80s. And I think a few years back people would have said pandemic. And oddly, this pandemic may, you could take different lessons from it. You can take a lesson that it's a big deal. It's certainly a big deal, but it also, is not a deal that's taking us back because we have such great technology, not taking us back by, a factor of 2 in population. So I think you need to worry about things that, for this big question of what limits L, you have to be looking at things that take population down, a factor of 2 or a factor of 4, and they're out there and they're geologic, in my opinion.
Yeah, I guess I would probably differ. I still think our greatest threat is ourselves, so climate being the primary one, where, we are right now headed towards at least a 2-degree world, if not higher, and we can get back to that 1.5 degree world. but we're on track for much more than that. And so, okay, is that going to wipe out humanity? Hopefully not, but it's probably going to set us back to some extent. And I would argue the numbers could get pretty high if we keep creeping that number upward. So that's like nuclear war, which is, the threat I grew up under. We are our greatest threat. And I really wonder about that with advanced civilizations. Can you get past your crazy adolescent phase, which I would argue we're in, where we threaten to throw, large bombs at each other, where we don't think about the sustainability of our planet that we live on being something that's critical. Can advanced civilizations get through that period and stabilize out, where then you can worry about asteroid impacts, and then you can worry about large igneous provinces, which are on yes, they're there, but they're on much longer time frames and more infrequent. You get a bad one, though, you're in trouble.
I don't disagree at all with what you said. You do have to get through this period for sure.
Yeah, the question is, what will we look like at 2100? And the frightening thing what is striking is how the general public is seeing it. That we are, the scale of anthropogenic impacts is accelerating literally in the lifetime of teenagers. So in terms of storm frequency and of heat wave frequency. So, and that will then is already having its spin outs into politics. And you could argue that people who are on the Belarusian border right now are they're from Syria. They are essentially, ultimately, if you run the causality back, climate refugees of some level or another. We have this enormous issue of climate refugees and the politics of climate refugees, and the politics of shifting eco zones on the planet, which are not as dramatic as an asteroid or a super plume, but they are here and now, and we can measure them in real time. And we're actually starting to watch in ways. I've been teaching global environmental since 1994, and things that I would tell my students in the 90s, keep your eye on this, have already happened. And so, we just have to keep that in mind.
And, thinking even past humanity to some extent, just, what's the end of the habitable for, all life on Earth? What is the kind of end game for all life on Earth?
Well, the expansion of the sun out past the orbit of Mercury is a big one. Eventually our galaxy will collide with the Andromeda galaxy. That's a big one too. And luckily, I sometimes tell that to, fifth graders. And then I remember, oh, right, I'm going to get all these calls from parents saying, you gave my kid nightmares. Those things are going to happen, right? This planet will be destroyed as the sun expands. We will collide with the Andromeda galaxy, but that's like over 10 billion years down the road, 9 billion years down the road. So it's not anything we need to panic about. But this idea of how do you become a multi-planet species? How do you get your technology to get up to the point where you can leave the solar system? We have billions of years to worry about that. I'm not worried about it. If we can get past our adolescent phase, if we can move through climate change, if we can learn how to, as somebody in the chat was saying, really say, we're in this together. How do we get spaceship Earth to be successful? And then how do we eventually move beyond it? And again, I never want to give anybody the idea that Mars is our escape from climate change. It isn't. We need to fix climate change right here, right now.
John, looking at thinking of the need to mitigate climate change, looking at human history, is there any events or actions that kind of give you hope about humanity's, ability for collective action to kind of tackle climate change? It's not, not necessarily global, but even kind of regional or, anything like that you look back to?
Well, we're putting an awful lot of, increasingly we're making demands on history and our forebears that are a little unreasonable in as much as they never encountered issues of this scale. And we can't really, we go back to when I was born, the population of the Earth was about 3.5 billion people. So we're talking about a massively changing context, and it's hard to place the so do we want to find examples? I mean, I'll be very specific. I would say the Montreal Accords and the refusal to use right guard, if I might point to, in the 1970s. If you look at the anti-CFC boycotts and then the national agreements, CFCs tip over and then drop. Now it wasn't perfect, but it was collective political action at the social movement level and then at the national and international level that made a difference. So I would say that we need to think of the recent political history, international political history of the 20th century, and its abilities, which have just begun to be manifested. Obviously, we're frustrated by what's happened in Glasgow. How do we advance that process further? But that's where our hopes should lie, in these international agreements and international action, and combined with action in the streets, social movements.
Yeah, I would add the Dust Bowl. I mean, we did you had literally people cleaning, dust from the center of the country off their windowsills in New York and Washington, D.C.
Mm-hmm.
It was nearly dark in the middle of the day because of the dust that was lifted because of poor agricultural processes. We fixed that. And for example, agriculture is one of the big things we need to tackle with climate change. And so we've shown we can address problems. The problem is they're across all sectors and we need to act rapidly, but we've done it.
Chris, do you have, you mentioned cephalopods, if, not to be too glib, but if human civilization is wiped out, do you have a bet on the next species?
No, I really don't. I mean, I find it very puzzling that a cephalopod or octopi, has been around for so long, because the simple answer is, oh, we have the opposable thumb, or whatever. But the reality is, the octopi tentacles make our opposable thumb look like really primitive. So I don't have the answer, but I maybe it's that the octopi life cycle just doesn't work. You have to spend so much of time as floating around the ocean as a little tiny little thing that knows nothing. There's no parental transmission of information, maybe, and that may be part of the problem. But no, I don't have a good bet. But I think it's us, and that's what I was kind of saying earlier, that even though I completely agree with Ellen and John that we have to fix this problem, that's our best bet. But if there is a collapse, it's still us. It's just us collapsed and set back a ways. And I think the real problem could be that we're using up resources that are going to be critical, like for example, helium. Helium is mostly treated as a byproduct of natural gas exploration, and yet it's super critical for high-end technology and space flight and fusion reactors or fission whatever we can imagine that's going to solve the problem. Helium is probably part of it, and yet we either release it to the atmosphere when our natural gas prices are at certain levels, or we do capture it because the market gets good enough for it. And so there's concerns here that it would be us, but that we might have already messed things up for the next us, if you will.
So one thing I think about in tackling climate change is if we're able to kind of get our handle on the global thermostat, from that point on, it's ours, right? There's we are kind of setting the terms of the planet. And, I'm wondering if we are able to do that, what does our kind of, L signature look like then? Or, is this, what does the planet look like in kind of a sustainable, if you were kind of looking at it from afar, as kind of the concept here, you'll have a lot of land draped in solar panels. There'll still be kind of differences. And, how do you think or envision kind of what Earth might be like if we have, addressed climate change and mitigated it?
Well, one of the things I want to say is it's not just climate change, right? Because if you look to the fact that we're in this mass extinction right now, it's being caused by other human activity besides climate change. Whether it's the fact we move harmful microbes around the Earth at the speed of aircraft, whether it's the fact that we're encroaching on habitats around the world, and leaving wildlife less and less, where biodiversity is in a crisis, and it's not just climate change. So as we're fixing climate change, we really need to think about Earth's sustainability. We need to think about things like a circular economy, so that we can say we need to, we run out of, every year we run out of Earth's resources. I think the date keeps moving back. I think it's early August right now. So we're using more than a year's worth of resources in about 10 months. We need to get that not just to 12 months, but to 14 or 16 months. And again, it depends on things like developing circular economies and really thinking about the fact that we need to learn to live with nature rather than in opposition to nature the way we do now.
Great. Well, I think this might be a good time to turn to audience Q&A. Maybe we can get a question to you, Ellen, before you have to go. Is that Dagmar?
Yeah, let's get started with none other than Jill Tarter. Jill has a question.
Yeah, Ellen, I was delighted to hear you use the phrase technological adolescence, because I don't hear it anywhere outside the walls of the SETI Institute usually. But my question to you is there anybody in Congress that is thinking in these terms? And what is the legislative awareness? Because it's going to have to go there to find some solutions.
Yeah, and I think we all see, thanks Jill, and hi Jill. I think we all see at this point that the solutions can't just be individuals, right? We can't recycle our way out of this. We know that for sure. And my electric car isn't going to solve the problem. So individuals do need to make action, and I'm not putting that down. I see much more movement on the corporate side, where you see a lot of companies seeing regulation, or water shortage, goods shortage coming down the road, where companies are actually really leaning forward on what they're doing. Government's moving the slowest. And I think there are lots of people in Congress who actually see what's happening. And the problem is, and we're seeing this play out right now, are we going to get enough of a consensus to move this forward? And is it going to happen fast enough? And if it's not going to happen fast enough, what can we all do as individuals? And I always tell people the most important thing you can do about climate change is vote.
I always tell people exactly the same thing. So that works out well. Hey, I'm also interested in this notion of an adolescent phase, the idea, right, that humanity evolves towards higher states and has evolved towards higher states over time. I think this is a very common notion in SETI. And as a historian, I always kind of have some trouble with it. And I'm wondering, where does that come from? And can we trust that notion?
It totally comes from Star Trek. I mean, at least that's my opinion. And I love that, right? And that's not bad, because to me, science fiction is where we play out our possible futures. Plugging the Futures exhibit at the Smithsonian. How do we explore, we have agency in the future. And the way we imagine futures is by walking through them through the arts. And that's critically important. And I'm really sorry I have to go, everybody.
Yeah. Thank you, Ellen.
I would suggest that Steven Pinker's focus on cultural evolution, making us kinder and better than we've ever been in the past, might be one of the agencies that is driving this moving to a better state.
John Brooke, as a historian, how do you feel about this notion?
Well, it's a contest. I mean, I'm sitting here thinking about the kind of the driver of hominin evolution, which actually was something called, which the anthropologists are calling competitive scavenging. Competitive scavenging meant early hominins were shifting to using tools and communications to talk to each other in little small bands, to scavenge off the herds that they followed and to fight off the hyenas. I mean, there is a certain amount of that still in us. And we talk about rising to higher levels. We have to overcome the kind of tribal basics that reemerge very quickly when we aren't, when we don't have access to refined discussion, to put it quite bluntly. We have our tribal violent backdrop is still embedded deep in our genes, and it's hard to break out of it. So we can talk about a kinder and better world. Now, on the other hand, people have been working. I mean, I just finished a lecture on the 1850s and the transition to the Civil War, which is simultaneously tribal, but also grounded on the framework that slavery should end. Slavery should come to an end, a humanitarian vision. And really, there is a history of humanitarianism that is embedded, that drives much of our kind of thinking, ability to empathize with other people and to think about our circumstances beyond our immediate interests. That has been evolving and shifting and changing a lot of what history does. Historians do, for looking at the last 300 to 400 years, is the emergence of that empathy quotient. And so we are asking for, a planetary empathy quotient, and a lot of people have responded, perhaps not enough.
There's also, just to quickly add, a way to harness human competitiveness for climate mitigation. A good example of this is the US-European steel deal, which will hopefully ratchet up. It's essentially trade protectionism, but with a climate veneer that you can use a form of what Bill Nordhaus calls a climate club, where you can actually put these pressures on other countries that they're out of the club. They want to get out of these trade protections to mitigate climate change.
I want to point out that Catherine Denning, who is an archaeologist at York University, has a point here in the comments that Carl Sagan is an originator of the concept of technological adolescence, who was, of course, very concerned with global thermonuclear war and nuclear winter. He was part of the team that came up with the nuclear winter concept. I would actually argue that it comes even earlier than that. I'm a historian too, and I started working on early modern history at the beginning of my career. I think it comes from the notion that civilization is more modern and superior, so-called civilization, right? Often that meant European Western civilization to other kinds of ways of organizing populations. And it kind of originates, I think, from a pretty problematic history of thinking of the world societies as being at different levels of development. And so I'm a little bit concerned with that concept. I'm not sure we're that much further developed, superior, evolved than populations from thousands of years ago. So as a historian, that makes me worry a little bit, that concept. Chris, do you want to talk about that too, or should I move on to the next question?
Well, I was just going to say, we certainly are more populous. That's the big difference.
Sure. Yeah, more populous. We have powers and technologies that I guess our ancestors never would have, but also problems that they never encountered. John, go ahead.
Well, just that this is a kind of truism in American political history. It's easier to when all boats are rising, it's easier to be empathetic with other people, and when the boats stop rising, when people stop getting access to cool new stuff, and meaning they have less money, you have rising tensions. And so there is this internal dynamic of contradictory dynamic here, which is the benefits of technological civilization spread widely lead to social peace, but they lead to ecological devastation. That is the Anthropocene, that is the Great Acceleration. And the Great Acceleration stalled in a certain sense, perhaps because so many people expired to it. And we have the raw tensions over access to things, and spilling over into raw tensions between people.
Yeah, that's great. Let me see here. There's a number of questions in the Q&A section. How long will the resources, so Raymond Merrick asks this, how long will the resources of Earth last humankind? How long could the resources of the asteroids last us, and would they have enough of what we need? So a question of, hey, what if we keep on using those resources, we keep on expanding, we don't turn into the monks that Mike Wang mentioned earlier today. What if we keep on expanding? Is there enough for us in the solar system? For how long?
Well, I think that going back to what Michael Wong said, I think he hit it right on the nail on the head, that it all depends on whether we massively adopt solar. You know, I mean, sure, there's plenty of metals in the ground. There's metals on the seafloor. There's metals under every igneous province on the planet. There's metals in the asteroid belt, but you probably don't even need to go to them, at least not in the short term. You know, and it all comes down to really energy. You can do a lot with different materials. You know, you tell an engineer, I want to change the structural piece. I don't like the fact that we're using copper. Okay, fine. We'll use silver. We'll use nickel. We'll use cobalt. I mean, you can change out materials very easily in engineering, but it all takes energy. And if you don't have the energy to do it, then engineering becomes extremely hard. And so he was correct in saying that the game changer here is how much we adopt solar and other sustainable energies. But solar goes right to the heart of the question being asked, because it talks about asteroid mining and all that sort of stuff. All of that would be, again, similar reasons to go out and get the metals you need to build big arrays. And if you want to go to sci-fi, you're going to Dyson clusters and whatnot, or constellations. You know, that's all going to be metals and materials, which we have. We have them on the Earth, we have them on the Moon, we have them in the asteroid belt. But it all comes down to the energy. The sun gives us plenty, but we seem to still, you know, we got hooked on fossil fuels, and we sold ourselves the idea of natural gas getting us off coal, but that is really only a very small step. We've got a long way to go.
And to the point of a lot of, even without the reconciliation bill passed, there are a lot of states that have already, you know, very generous feed-in tariff policies or solar supports. A lot of states don't have it too, but you know, there's action that can be taken, you know, right now if people want.
Yeah, it really can't be stressed enough that the plummeting costs of renewables, solar and wind, are primarily responsible for steering us away from the most apocalyptic scenarios for future climate change, which is where we seem to be heading even a couple of years ago. Right now, things seem more optimistic, which means, well, okay, maybe not abject apocalypse, but we're headed for a very bad place.
Right, and you know, within the last 10 years, that changed, right? I mean, I think 10, 12 years ago, we're all sort of shrugging our shoulders. I don't know what the future is. I don't know how to make it. You know, I kind of know that I'm going to live in a future sci-fi movie, but I don't know which movie. And so, you know, at least now we know we have an option to make it an optimistic movie, because the technology exists, and it exists today, and it exists fairly inexpensively.
We might get to a Kim Stanley Robinson world.
Kim Stanley Robinson, yeah, maybe. To me, it seems a little bit like Blade Runner, but hoping for a Star Trek future. Fingers crossed. Another question here is about carbon capture. So the carbon capture that is going on now, what state is the carbon in when it is stored underground at some point in the future? Could all this carbon come back to haunt us? This is a question, a rather technical question, I think. But do any of you feel like you might want to comment on that?
My understanding of this new Iceland technology is that the new work that we've done in Iceland, the new carbon capture systems are creating totally inert rock forms that from which it would take eons to get the carbon back out. But I defer to Chris.
Oh, well, I mean, yeah, carbon capture and well, there's two different types of carbon capture, right? Carbon capture from point sources. That's the way to retrofit something you can't give up. Like, and you know, we can basically give up anything, but not politically, we can't. So politically, if there's something you can't give up, then point capture is going to help. But the point about, yeah, the stuff in Iceland, that's the way, you know, you ultimately deal hypothetically with the inability to get to zero, right? You can't get to zero because you just can't give up your gas range, or you can't give up your you know, the flights. You know, the flights will be maybe biofuels can do a lot, but biofuels compete with food. So there might be limits to what biofuels will do in the terms of airplane flight. But, you know, in this, you know, we're making up our sci-fi movie here. Jumping to that sci-fi movie, you know, you have, let's say 90% of flights done with biofuels, and you have still people using gas ranges or restaurants using gas ranges, they'll still be, we won't be quite at zero, right? And all electricity production could be renewables, or some mix of nuclear. You get to a point where you still don't get to zero. You just can't quite get to zero. And unfortunately, we have to get to zero. And so that's where, capture and sequestration into volcanic, deep aquifers and volcanic terrains actually might be quite useful.
There's also, you might want to get below where we are, look back down even further, because you keep kind of 1 degree Celsius long enough, you probably still lose the West Antarctic ice sheet.
Yeah, I think historically there was workshops in this, I don't know the years, but 70s or 80s, just deciding what is the optimal amount of CO2 for the atmosphere. This is, of course, before it was anywhere near what is now. And those workshops were thinking about like how much extra farmland you get in Siberia, for example. Now, of course, you're making Mexico kind of uninhabitable, but apart from the ethical issues, there were these kinds of workshops, and I think that the consensus was 400 ppm, which we've already blown past.
Right. Yeah, that's a really good point, Paul. That a lot of times people assume that, okay, when we reach 2 degrees Celsius, that's it, we're stuck there forever. But with negative emissions, right, carbon capture, it offers at least the potential of reversing some of that. Not all the impacts of climate change, right? Melting ice sheets will continue for a long time, unfortunately, centuries. But if we can get CO2 levels low enough to sustain a much lower temperature, then there is some hope for the long-term future as well. Okay, so maybe just a couple more questions. This is a very specific question. By Ryan Wyatt, and I think, John, this one might be for you. I'm wondering if there are references for the primate RNA topic that the panel has been discussing. So,
well, there are, yeah, I mean, why don't, I'm not going to go into them right this second, but there's a vast array of vast literature on the RNA side, but particularly the transposable element literature on which the RNA plays a role in, I'm not going to conjure up the actual citations right this second, but I'm happy to consult. If anyone wants to get in touch with me, my email address is brook.10@osu.edu.
well, and I think, John, you've got a number of references in your books too, right? So a rough journey.
Yeah, but I will put in a pitch, which is I've just written the first 2 chapters of the revision, which are radically new. So hang on to your hats. It's going to be a whole new ride, a lot of new material. I would like to get back to our last point, which the tone of our conversation in the last few minutes has been assuming kind of a gradual, a directionality toward 2100. In other words, if we do this, we can bend the curve. We are facing in the Arctic, fundamental shift. It's kind of like the eruption of CO2 and methane that's coming out of the Arctic is something equivalent to one of these super plume events in terms of its speed and scale. It may not be quite as big, but it is a big deal, and it may overwhelm. It looks like it is probably on course to. It may be what's behind our acceleration the last few years, and it's going to get worse in the next 25 years, possibly the next decade. And then, then already people are talking about the other kind of intervention, the intervention that is a verboten word. Carbon capture is the most kind of benevolent of geoengineering responses, and there are others, and cloud seeding and ocean seeding, putting iron filings in the southern oceans to accelerate plankton blooms and CO2 drawdown. But that's the other side of once we have our hand on the thermostat, there's a big question out there right now in the scientific engineering world of when do we should be thinking about how to geoengineer, and in case we actually need it 5 to 10 years from now. And again, I defer to Chris, maybe he has more details.
Well, yeah, no, it's a great point. And I actually wanted just to correct myself and explain myself earlier when I said the big things that could limit L are geologic. I didn't mean to exclude our own trigger of geologic cycles. And so you absolutely, the warming of the Arctic is the scariest thing we're facing. And I kind of agree with you that we can do all these changes politically and change our economy, our energy use, and still end up with a huge warming event. And that's just a different sci-fi movie will be in the future. But I wouldn't want to propose what my favorite geoengineering tool would be, because I don't want to get to that world. I don't want to, I don't want to be in the world where we have, dikes around all coastal cities and all the reefs of the world are wiped out, because geoengineering doesn't stop acidification of the ocean, for example. And so, I absolutely agree. We may have to cool in order to keep sea level from rising by putting sulfate in the atmosphere or something. But we don't want to take pressure off the decarbonization of the economy, because we also want to address acidification of the ocean and other effects as well.
Yeah, it's really important to know when you see these numbers, right, for the future, 2100, we're on course right now for almost 3 degrees Celsius of warming. That's a model average. That's the average of a whole bunch of different models that climate scientists are running. It could be significantly more than that. Could be a little bit less, could be quite a bit more. And that's driven by these kind of feedbacks that John is talking about. So anyway, and once we do these geoengineering interventions, if we do, or if we reduce emissions or whatever we do, we will be masters of Earth's atmosphere and oceans. The Earth will become a kind of human machine. And to some extent, I suppose it already is. So maybe we should be looking for evidence of that on other planets. And with that in mind, I will turn it over to Bill.
Great. Well, thank you, Dagmar. And thank you, Paul and Chris and John and Ellen, who had to leave, but fantastic panel. And I think, this was Habitability at Home. And hopefully this discussion brought home really the importance and severity of this issue. That's kind of the point of the entire event today. I think Ellen, put it properly when she said, we are our own greatest threat. From my perspective, this is the defining issue of our time. And pretty much everything else that's going on in our planet, however impactful it may feel in the short term, like COVID, these all pale in comparison to the issue of climate change and rising global temperatures and increased greenhouse gases in the atmosphere. And so it's certainly our hope that through events like this, the public really begins to get it. The politicians really begin to get it. I don't think even at COP26 that was really evident, but I think this discussion certainly brought home the importance of this issue. It is a global conversation, and I'm glad to see at least that our conversation is reaching people around the globe. So we have folks joining us today from Italy, Sri Lanka, Guatemala, Sweden, the UK, Armenia, India, Canada, Argentina, Peru, Siberia, Poland, and Portugal, not to mention the US and Mexico and Canada. So anyway, wonderful that we have all of you here. We're going to take advantage of the only actual break that we have in today's program coming up, because the rest of the day is packed full, but we're going to shorten this break so we get back onto our schedule, where the next panel, Habitability in the Solar System, will start on time at 1 o'clock Eastern, and that will be moderated by Michael Wall. At 2 p.m. Eastern, we will have a 30-minute session with the Artists in Residence program of the SETI Institute, hosted by Bettina Forget, who is the head of our Artists in Residence program, to offer some artistic perspectives that are germane to today's conversation. And then at 2:30, we will have the Habitability Beyond panel, discussing habitability in exoplanet environments and habitability outside of our solar system. That'll be moderated by Ross Anderson. And then at 3:30, another 30-minute segment where our philosopher and artist, Jonathan Keats, will have a discussion about the Great Silence workshop. And then finally, we will close at 4 p.m. Eastern with Habitability at Home Redux, with Alexandra Wietze hosting and moderating that panel discussion, which will hopefully bring it all back into perspective, tie all these outward-looking perspectives back into the habitability issue here on our planet. So we're going to break now, and we'll see everybody back at 1 o'clock Eastern, and that will be here at 10 o'clock, so a short break. And please come back and join us. Thank you all so much. And thanks again to our panel for that wonderful discussion. See you all soon.
There we go. Can I do a quick audio?
I can hear you.
All right. Welcome back, everyone. We're going to get going right back on time here and explore the topic of habitability in the solar system. So I'm going to turn it over to Sarah.
Oh, we're so welcome. We're so excited to welcome everybody back. So yes, we're going to be talking about habitability in the solar system with moderator Mike Wall, who's a senior reporter from space.com, as well as Abby Freeman and Morgan Freeman and Kendall Lynch. But first, we're going to watch a wonderful video by Natalie Cabral. If you could play that, Lee.
Earth is the only planet we know is inhabited in the solar system. But what about the habitability of other worlds, places we already have visited with spacecraft and robotic explorers? Take Mars, for instance. We know today that Mars has all the conditions for life to appear a long time ago in its history. It had energy, it had water, it had more organic molecules. But Mars became this hostile world, cold and arid. So what happened? Was there life on Mars earlier on? Is it still here today? Can Mars teach us something important about the fragility of life and the conditions that are necessary for it to appear and to be sustained on the planet? And what about Venus? Venus might have been habitable too before it became this fiery inferno that we know today with the greenhouse effect. Today, the surface of Venus is hot enough to melt lead, but higher up in the cloud, the temperature is cool and maybe cool enough to sustain life. The recent discovery of phosphine is leading to the hypothesis that that might be the case. But phosphine is not only a biosignature, the signature of life. It might be also the sign that there is some active volcanism at the surface of Venus right now today. The only way we'll be able to know is to send a mission, and one of them is going to get there very soon. Of course, the possibilities don't end here. Much farther away in the outer solar system, there are little moons like Enceladus and Europa, and they may harbor liquid water ocean within them. Those oceans are being heated by gravitational tides from Jupiter and Saturn. And who knows, them too could be hosting organic molecules and the beginning of life. Weirder still is Titan, where it rains hydrocarbon, ethane and methane that is filling Great Lakes and seas. Is Titan a natural lab for us to understand life as we don't know it? On this world, what fingerprints are there for us to decode? What lessons can we learn about our world and about ourselves by studying the beginning and the end of habitability on other worlds? In many ways, the search for life in the solar system is telling us much about our own coevolution of life and its environment here on Earth, about its fragility, and about our responsibility in sustaining it and protecting it.
Okay, so that's a good little intro to a very big topic. Hi, everybody. Thank you for actually joining us today. As was said, my name is Mike Wall. I'm a reporter at space.com, and I've got the honor of actually leading what's going to be a pretty fun discussion today. So first things first, we are going to be taking audience questions with about 15 minutes left in the session. And just a reminder, put your questions into the Q&A tab. There's a chat tab down there too, but please use the Q&A tab. Those are much easier for our sort of moderators to go through. Okay, so let's get right to it. We've got three very accomplished, very interesting folks to talk to today about this stuff. And I'm not going to spend a lot of time on bios because that will take away from the time we've got to talk. So we've got Kendall Lynch. She's an astrobiologist at the Lunar and let's see, Planetary Science Institute, or Lunar and actually Planetary Institute. And we've got Abigail Freeman. She is a planetary science. She's a planetary scientist at the Jet Propulsion Laboratory. And we've got Morgan Cable, who is also at JPL. And they all have different specialties. For example, Abby is currently deputy project scientist for the Curiosity rover. And also Morgan's working on the Europa Clipper missions and also Titan Dragonfly mission. So there's lots of fun stuff to talk about. And let's just start off. Kenda, do you want to give your intro first?
Sure. So I'll just kind of go over the work that I do.
Sure.
So I'm an astrobiologist and a geomicrobiologist, and I am particularly interested and focused right now on understanding habitability in the subsurface environment. we kind of focus on life in the surface, but I'm also very interested in life in the subsurface, where, especially on some of not only our relic ocean world of Mars, but on our current active, beautiful ocean worlds, the subsurface is kind of where life is going to be at. And that's because that's where we're probably going to find some more of our liquid water. And we really want to try to understand that. So I try to study and understand life in subsurface environments here on Earth and how life survives in them, especially in the extreme environments of those environments, and try to translate how that will help us understand life on other planets.
Okay, cool. Can we go to let's see, Abby next? Do you mind?
Yes, hello. First of all, thank you so much for having us today. Yes, my name is Abby Freeman, and I'm a planetary geologist. So I spend most of my days thinking about the rocks across the solar system and what we can learn from them about past environments, and understanding kind of the evolution of habitability from the surface through to the subsurface is something that I'm fascinating in. And what makes planets habitable, what evidence can we find in the rock record that they are or were once habitable, are things that I'm extremely interested in answering with mostly robotic spacecraft in orbit and on the surface.
Okay, great. And last but not least, Morgan.
Hi, everyone. It's such a pleasure to be here with my friends and colleagues, Kenda and Abby. Just such a joy to talk about these things that we're so passionate about. Yeah, so I technically am a chemist, but got sucked into the world of astrobiology. And as you mentioned, I'm fascinated with the study of these ocean worlds, places like Europa and Enceladus and Titan, studying how we might search for biosignatures in these worlds, but also just looking at the interesting organic and prebiotic chemistry that can happen there to see where these worlds may lie on the habitability spectrum. And I also do dabble a little bit in Mars, not a whole lot, but I was fortunate enough to be part of a team doing some field work in Iceland on some of the fresh lava fields there that we think may make some good analogs for parts of Mars. So really excited to talk about any or all of these places and the connections between them.
Great. So yeah, I just figured we would start out pretty big, just a big open-ended question, and that is, how sort of bullish are all of you on, like on the prospects of there being alien life in the solar system, and like a very different question, how bullish are you that we'll be able to find it in like a reasonable time frame? And yeah, I mean, like I would define reasonable maybe within the next 20 years or so. So yeah, I mean, whoever wants to take that, go ahead, and we can just kind of just kind of run from there. Do we think that there is life out there in our backyard, and can we find it? What do you think, Kenda?
So on the question of is there life out there in our backyard, I am full bar unequivocally yes. I definitely think it's out there. Now the question of can we find it is, well, we're working out. The answer is we're working on figuring out how to do that. Yeah. I think the bigger part of the question is, can we find it and verify that we found it? I think that's the big problem we're trying to work on, is, making sure we don't have the Viking effect where we find something, but we're really not sure what it is. That's the big thing that our community, especially within the astrobiology community, are working on really hard, like defining defining not only habitability, but defining our biosignatures. What does it mean to be a biosignature? How do we confirm that biosignature? And what would be a mutually confirming other biosignature that would confirm that? It's really turned into a lot of forensic science for us in the astrobiology world, and really, really confirming each piece of the data puzzle to put together the story of who done it, And so I think that that's the big thing that's going to be a challenge for us to be able to answer that question of can we find it, is can we find it and verify that we found it?
Yeah. What do you think, Abby?
Yeah, I mean, I can give the scientist hat answer, which is, I don't know. That's why we're looking. But, given what we found so far with the exploration of our own solar system, and that there are so many opportunities to have conditions that we think have all of the ingredients that at least life as we define it needs, liquid water, energy sources, organic material, I would find it very surprising that there would be no other places in the entire universe that don't have life. Looking at our own solar system, there's just so many opportunities for life to have arisen. So I think everything we've found really pushes in that direction, that this should not be a unique process unique to Earth. Will we detect life in the next 20 years? Man, that would be exciting. I sure hope so. I mean, we have so many missions on deck that are going to give us our best chance to do that. At the Mars front, we have our samples that are hopefully going to come back from the Jezero Delta area where, you know, if we don't find life in them, I don't think it's going to say Mars never had life, because there's many other kinds of environments we can look on Mars, including, as Kenda talked about, the subsurface is largely unexplored, but it would give us our best fighting chance, I think, to definitively find that answer. And then to the outer solar system, and Morgan can talk more about this, missions to Europa. There's dreams of missions to Enceladus that would be amazing. And, you know, I'm really optimistic about the kinds of data that those missions would provide. I'll let Morgan talk about those ones because she's the expert.
Yeah, go for it, Morgan.
Sure. Yeah, just building off of what Abby and Kenda said. Yeah, it is a big challenge, right? That to be able to bring the right payload to the right place that is able to make these kinds of discoveries. And this speaks a little bit to Joseph Urban's question that he just posted in the Q&A about having the sufficient technologies in place. We do have instruments that are capable of reaching, you know, the parts per billion or subparts per billion, in some cases, limits of detection for some of these biosignatures, but you still need to bring them to the right place, collect a sample that is contamination free, or at least has that minimized. Life may be heterogeneous in some of these environments, right? And Kenda can speak to that with some of the field work that she's been doing, and I'm sure Abby can as well. And so a lot of things need to go right for us to be able to make a discovery that we all can agree would be civilization level science. And we have some incredible missions that are in the works. Europa Clipper is going to launch in 2024. The Dragonfly mission is slated to land in, by 2034 on Titan. And so we will have instruments in place that can make these discoveries if these beautiful worlds work with us and are able to provide access to these samples that we need. And there was something else I was going to say. So sample processing is important. Just the fact that we've learned so much from Viking, right? But we still only have a sample size of 1. And so I think it's really important, and all of the teams who are working on these missions and mission concepts recognize that we have to be humble. We have to question every single assumption that we make that goes into the design of these experiments, these payloads, and our interpretation of those measurements. Oh, and I remembered the thing I wanted to say. It's not just searching for biosignatures, right? It's understanding the context of where you find them. So the geochemistry, the physical properties, and what some of us like to call the provenance, right? How did that sample get there? What processing did it undergo before it got there that could tweak or change the biosignatures we might expect to find? So there's a lot to think about.
Yeah, and that's yeah, and that kind of brings me to another question. Do we actually know enough about life on Earth? I mean, we take it. I mean, it's all around us, right? But it's pretty complicated, and we don't know exactly where it started. We have an idea that it started really fast, pretty much as soon as our planet cooled off enough to have oceans. There are microfossils basically. So that makes you feel confident maybe that life is no miracle. But do we know enough about how life started on Earth, what sorts of environments gave rise to it, that we can translate that knowledge to a search on other worlds like Mars or on Enceladus? And I mean, maybe Kenda, you can talk about some of the analog work that you've been.
From a standpoint of from the prebiotics standpoint, we still have we're answering some significant questions. We're making very good headway there. So there's still a lot for us to learn to understand kind of how life got started here. Under what context, and actually one thing is we know it wasn't necessarily one single start. There were probably multiple stops and starts. So trying to understand that aspect of the prebiotic chemistry and life, how we evolved to the point of, where life could, sustain itself. I think, we're making good headway there. And I think that we have enough knowledge now to start. And we are starting to look at other worlds as prebiotic worlds, not only just just habitable worlds. Like Morgan said earlier, some of these, we look at this habitability spectrum now because, for example, Titan, with its crazy environment, may not end up being a habitable world, but maybe it's a prebiotic world. Maybe it's a world that's on that prebiotic life arising spectrum, right? And so, and we can look at that from other, in other aspects on a lot of our other habitable planets as well. So I think that we always need more information, right? But I think that from that standpoint, we're making very good headway. Where I also think it's important is what another thing that Morgan pointed to, which is that context, that environmental context, and not in just the arising to sustain life, but the different types of environments that can sustain life, and having context for, did those environments exist where you found an interesting sample, and having an understanding of the context of whatever sample you're getting from, not only where it came from, but where it came from. Was it actually habitable in any sort of way? Could there have been a sustained ecosystem? And then, what does that look like, so that you can put the context behind that sample to place it somewhere on that habitability spectrum. So hopefully, I probably didn't answer that as directly as you probably wanted me to, but that's the answer I got for you.
Yeah, sure.
Can I add one quick thing, Mike? Is that okay?
Yeah, sure.
Okay, yeah, I thought that was really well said, Kenda. And one thing that I was just thinking about now that is really going to be important as we move forward with these, getting back into biosignature and the search for life, is managing community expectations, right? I mean, it would be amazing if Europa Clipper arrives at Europa and we see a giant squid, wave its nodally appendage, and we're like, oh, hey, we found life.
We'd love that.
Right, or,
that would be awesome.
Yeah, there are also, microscopes that are getting to the level of flight that could find cells or bits of cells, if those are in those samples. But chances are, if we do find a biosignature, it may not be that that completely obvious. And even if it is, we may have questions, right? Like the Martian meteorite ALH 84001 that had that thing that really looked like a little worm, but it turns out there are all sorts of abiotic explanations for that kind of morphological biosignature. So I think it's really important for us as communicators to make sure the community understands the kinds of things we may expect, and to sort of temper those expectations so that we don't end up in the same thing where we were with Viking, where, oh, we're going to look for life. Oh, we didn't quite find the smoking gun, and we're going to shut down astrobiology for another 20 years, right? None of us want that to happen. So I think that's on us as communicators to make sure not just the planetary science and astrobiology community, but the general public knows what we can expect with these kinds of payloads and instrument investigations we're planning.
Absolutely, 100%.
That's a really good point. And yeah, I mean, managing expectations, it like goes to the broader public too, not just the scientific community too, right? Because what do you guys think would constitute I mean, you can never be 100% sure of like anything basically unless you see that giant squid arm waving. But what would be a confirmation that would rise to the level of a detection, and how would you be able to communicate that and the uncertainty that's involved to the public at large? Because I mean, nuance is not something that most of us are very good at digesting, as we've seen over the past few years on social media and so on.
Again, that's something that we as a community are trying to figure out, is what would be, if a detection either in situ or via return sample, what would constitute enough of a smoking gun or finding enough of uncovering the needle for us to announce to the community, we found something, and here's what it is, and here's all the data to back it up. And I don't think we have I don't personally have a direct answer for you, because that's something that we are actually trying to define as an astrobiology community. So
yeah.
And a planetary science community, the whole science and exploration community. We're trying to define this so that we can lay this groundwork for all missions that are doing, habitability and biosignature exploration, so that we can come back and have this standard of what does it mean to say, I've got a definitive possible, positive result.
And this is a huge question, because this is potentially the greatest discovery in the history of our species. So we would hope that we've got it sorted, how we want to announce it, how we want to confirm it, and so on. That's a big deal.
Yeah.
Do you have thoughts, Abby? Or
yeah, I was just going to say, that's a good point. I will say I think it's good that we can lean on history and the scientific process to make sure we get it right. You know, even if from a public appearance perspective, it might seem a little bit bumbled, but you know, the scientific method, it's always to be skeptical, be critical, and using the ALH 84001 as an example, you know, this was a great case study where there was a potential discovery of life. There were several at the time thought to be very strong lines of evidence all supporting this discovery, but the scientific community, even after it was announced, kept poking at it, kept trying to find alternative explanations. And I think that helped shape perception that, okay, maybe this isn't quite as big as a discovery that we thought, and it's ambiguous. So the scientific process works, and I think it's important to also communicate what is involved in this process to the public when discoveries like this are announced.
Yeah.
Every time and often in between. Absolutely.
Yes.
As much as possible.
Yeah. And yeah, I mean, people have been talking about Viking a lot. It's kind of hard to believe it was in the mid 70s, and there was a really ambiguous detection. And as you've said, you know, it sort of chilled. Yeah, I mean, it chilled NASA's efforts. It sort of put the brakes on the astrobiology quest for decades. And here we are. We're in a new era where we're learning so much about the solar system. We're learning about ancient Mars being potentially habitable. We're learning about all these ocean worlds. Venus is coming into the forefront as a potentially habitable world even today. So now it strikes me that there's a different problem now, and that might be one of, I mean, how do we prioritize all of these really interesting worlds, right? Like, I mean, everybody would love to see a Europa lander and an Enceladus kind of like crevasse eel going in, trying to get down to the ocean. We'd love to see like a Venus mission going into the atmosphere with all sorts of instruments. How do we prioritize which worlds to seek out now that we know there are so many of them that are potentially interesting astrobiologically? And is there a role for the private spaceflight community in that decision, in that quest? I mean, Rocket Lab, we have heard, is trying to plan out their own Venus missions and so on. So that's a pretty big question, and it's multi-part. But I mean, what do you guys think about that? How do we prioritize which worlds we look at and which missions to fund, and what kind of role can the private community play in this quest?
I can jump in on that first, if I may. So we are in the middle of a process that does happen every year with the planetary science and now astrobiology decadal survey. And so I do think that through that process, the planetary science and astrobiology community is able to communicate and help establish that prioritization, because there are all of these incredible worlds to explore, and we would all love to send a flagship mission or multiple to each of them. But NASA's budget is only so large, and so we do have to make some difficult decisions. And so that prioritization for the next 10 years, which includes more than just astrobiology, right? It's planetary science in general, is going to come out. The draft of that decadal survey will be out in March of next year. And so I think that will really help us frame, okay, where do we really want to focus? Where can we leverage the technology investments that we've been making and instrument development and all of these things to be able to do the best science we can and be able to map that to what the prioritizations is established by these communities, what they really want to see in the next 10 years. And I'll let Abby and Kenda jump in, and if they want to say anything about the commercial side, I can add my 2 cents there at the end.
Okay.
Yeah, I guess I'll add my 2 cents. Exactly agree with what Morgan said about the importance of this planetary decadal survey, which is the community consensus for the next 10-year prioritization. I am so excited about the entry of commercial companies into enabling more space exploration. You know, we're seeing that with Rocket Lab, or with potential Venus missions. We're seeing this with all these commercial lunar lander providers through the CLIPS program to the moon. And I think right now it's a bit of a Wild West, but a really exciting, you know, open place to explore about how we can leverage potential new players into the space market, and either partnering with NASA, partnering with other entities, and how we can, you know, use this increasing pool of stakeholders to widen the participation in space exploration and how priorities get selected. I think it'll be kind of partially a practical thing in terms of who might be footing the bill. You know, if it's something like lunar exploration, where it's NASA is assigning the priorities and saying, companies, we need you to provide us a service to go to the moon. Can you do that? That, in the sense, is still driven by NASA, which is getting input from the community. for exploration goals, some of them might still be a little bit too far away for commercial companies to take on without external partnerships. But yeah, isn't it also cool to think about if they have the capital and the ability to go explore places that they desire? Yeah, it's interesting. I don't know how that's going to shape planetary exploration, but I think it's a really neat to think about and requires a lot of thought.
Yeah.
Yeah, I think I think a couple of things. I think that the decadal survey process is extremely important. But I just want to also make sure that everybody clarifies that decadal process only kind of sets the stage and the direction for NASA. It doesn't necessarily set the stage and direction for ESA or JAXA or the Chinese Space Agency or any of the other countries that are developing their space programs. So we have this, in addition to the corporate, involvement in our space exploration future, we also have to think of this broader sense of a global space, kind of our global space plan. Like what are our global space objectives as a world? Like what do the other space agencies have to say about the directions and the priorities for where they want to go? And we're starting to see that evolution of shared priorities and missions. For example, in our Mars Ice Mapper mission is a shared mission where we're starting to have a lot of strong international participation from other space agencies, and so the shared goals have to be considered. The science definition is that just got released, is a very international team, so that we can evaluate the shared goals of all the partners, both U.S. and other countries, and also, with whatever, support that we're getting from some of the industry as well. And so, yeah, I think it's definitely a very interesting new world. There's going to be a lot of other issues with regards to space governance, with the participation of private companies, and that's definitely above my pay grade. But I think there's going to be a lot of interesting, questions to answer, on how we integrate all three of those aspects of the future of space exploration.
You said you were going to jump in, Morgan, with your thoughts on the private side.
I actually think Abby and Kenda covered it really well. And I really love Kenda's point about this being an international endeavor, right? There are 3 different nations that now have missions at Mars, and that's super exciting. And that was just within the last year that happened. But I don't know. Time has no meaning anymore.
2020.
Yeah. Yes. Okay.
Last year.
Yes, but still, it's incredibly exciting, and leveraging those international partnerships is going to be just as critical as working with industry.
Yeah. It's exciting, and there are a bunch more opportunities that are coming, but there are also complications, right? When you talk about, some of these private companies, one of them, if they want to talk about SpaceX, is working to get people to Mars. I know NASA is too, but on like a research outpost level, that's what NASA wants to do. SpaceX wants to help colonize Mars, and that could very, very much complicate our search for life on Mars and trying to interpret what we find there. So yeah, maybe you could like you guys speak toward we're trying to do multiple ambitious things as a species with spaceflight, and one of them is trying to find life, and another is trying to take ourselves to other planets which might make it both easier to find life if you have astronauts that are doing it, but also a lot harder to interpret what they find. So yeah, could you guys maybe talk about those twin quests and how we can untangle the complications that arise from them? I know that's another big question, but that's one that we're all confronting now, right?
Well, like I said before, it's a matter of, expertise that's kind of outside our wheelhouse, which is that whole issue of space governance and space law, and what is legal, and what is going to be allowed and what's not going to be allowed, and who owns what. And so there's a lot of things to disentangle there. And I think that's what it's going to take. It's going to take the people that have been thinking about space policy and space law really coming together and trying to define, create those definitions that from an international perspective on what are we as a global society is going to agree is going to be okay for how we attack this new wild frontier. It is the most vast expanse frontier. How are we going to how people are going to stake their claims? You just put your flag down and that's your planet? Is that your rock? Is that your asteroid? How are we going to do this? It's a complex societal question. That's a global societal question that I'm very excited to start seeing happen, because we've needed this discussion to happen for a long time. And luckily we have people that are interested in study this and study and consider space law and consider space governance and policy, and that are really, working to kind of try to start answering these questions. So from that perspective, I think that could be a workshop like this in itself. And I think it would be a great one that I would attend. From the science perspective, yeah, I mean, if I was weighing into that, I would weigh in as a scientist and say, here's the things that we need to consider if we want to send humans, like, for example, to Mars. I'm for humans going to Mars. I think we can do a lot of science when we have humans on Mars. We need to do it in a careful way. So that we don't, basically, mess up our field site, contaminate our field site, for lack of a better word. And I think there's a way to do that. And so that's where I would weigh in, is on, here are the constraints that we need to consider to send humans, and try to do, slow gains to make sure that we're not negatively impact the environment that we're trying to study. But again, it's a complex issue, and I'll let the others weigh in.
Do you guys have any thoughts, Abby, Morgan?
Abby, why don't you go first?
Yeah, I don't think I have anything particularly profound to say on this beyond what Kenda just said. It is a thorny issue. It is something that I think other people have better expertise in than I am. I am in agreement that there's a lot that humans can do in terms of exploration that we just can't do with robots, as sophisticated and as amazing as they are. And that in terms of the question of looking for life, it gets far more challenging, though, when humans are in the mix. And so it has to be done carefully, but that shouldn't prevent it from being done. And this is talking just about scientific exploration.
Sure.
Yeah, humans certainly are just mostly squishy bags of water, and the microbial biota, like in our digestive systems and things, those cells, what are equivalent to, or maybe even outnumber our actual cells. So we are communities in and of ourselves. So yeah, that may be a concern if you're trying to look for one alien cell life form in an environment, if you're sending a human there. But I do think our planetary protection scientists are brilliant. If we're able to characterize the microbial, sort of identify which species are present on our spacecraft now, right? And so we can potentially develop some type of machine learning type technique to filter those out, so that even if we do bring some contamination along with us, as we're inevitably going to when we send our squishy bags of water, that we can still be able to make some stronger scientific conclusions by filtering through those types of things. So there are ways that we can go about it, and I'm sure we'll be able to. Just in my mind, I could see certain areas of Mars saying, okay, well, we'll target this for human exploration, and there'll be these other areas we'll do our best to keep pristine, and those could be equivalent to the national parks here in the States, but on Mars, maybe there could be something like that.
Well, I mean, we already have something like that that's been set up on the moon, right? With the Apollo heritage sites, we already sort of have national parks on the moon. It wouldn't be that difficult to expand that concept to Mars. Yeah. Just to go back to kind of what we were talking about at the beginning, like what are we looking for? And this is sort of I mean, it probably depends on which world we're exploring, right? But what are some of the biosignatures that you would look for when you're rolling across ancient Mars? Or what are some of the biosignatures that you want to look for in the oceans of Enceladus or of Europa, or in the thick smoggy skies of Titan? Like what are some of the things that scientists are targeting in the search for life? And that's also a big question, but like, whoever wants to go first.
Who wants to go first?
That's like, Morgan, you unmuted first. You go first.
Okay. Yes, there are lots of things, and you are right. While some of them are world dependent, there are some sort of overall classes of biosignatures that we may be seeking at each of these worlds. One of them is the morphological biosignatures. If we can find cells, gosh, if the cells moved, if we found a, squid's noodly appendage, that would be amazing. And Abby can probably talk in a little bit more detail about fossilized evidence, stromatolites or things like that, to kind of more Mars relevant things that might be preserved in rock. So that's one class, sort of morphology type things. As a chemist, I get really excited about the molecular biosignatures. So these would be things, for example, you may have heard about amino acids. They have this property called chirality, where they're mirror images of these molecules and life only uses one out of the two. And so you can look for that kind of evidence. And there, some people think, okay, well, that means we're only looking for a particular molecule and that's only found in Earth life. So we're really biasing ourselves. We're doing our best to take a step back from that. And instead of just looking for one molecule, and if it's there, life is there, and if it's gone, life is not there. Instead, we want to look at these different classes of molecules and look for patterns within them. For example, amino acids, very important for life. That's what makes up our proteins and all of our cells and all known life. Amino acids are also found in meteorites. We know that they're made abiotically too. But the difference is when you have an abiotic scenario, the most common amino acids that are made are the ones that are just chemically, thermodynamically, the easiest to form. So they're the simplest ones, things like glycine and alanine. But life can't make very many interesting proteins with interesting functionality just with those two amino acids. So anytime life is involved, now you'll be enriched in some of the more complicated amino acids, ones that have these cool functional groups that can like grab onto metals and make binding sites and do chemistry that keeps us alive. And so when life is around, you'll find some more of these wacky, weird amino acids that are kind of challenging to make in terms of like the thermodynamics for them to form. And so we'll look for the pattern in amino acids and say, okay, well, does this fit with an abiotic theory? Or is this really wild and strange and could life be involved? And so those are the kinds of things we'll look for. And it's not just with amino acids. We'll look at other classes of molecules, membrane forming molecules like fatty acids, because we'll assume, if it's an aqueous environment, it's going to need some sort of nonpolar way to shield the microbial machinery from the outside environment. And we'll look for other classes of molecules, maybe an information carrying one, equivalent to DNA, but not those specific molecules, maybe others that can do the same thing, form very long chains that are equivalent of an alphabet that can store information. So those molecular ones, and I'm sure there are other ones. They're like energy biosignatures, energy carrying molecules, or we can look for really weird concentrations of things that shouldn't be in that environment if we understand the geochemistry. So like if we expect this environment to be really oxidizing, which is electron poor, and then we see a ton of reduced species that are rich in electrons, we're like, how did those get there? Those kinds of things. And now I'm going to shut up and let these other two brilliant colleagues weigh in as well.
Well, I can just follow up on that, and like Morgan said, a lot of, like looking at the fatty acids, amino acids, also other types of lipids that we know, some we know that they're just made just generally, again, easily abiotically, but we also know that some that are made abiotically and in different abundances. It's all about patterns, like Morgan said. We also are very interested in isotopes because life has a tendency to do weird things with isotopes. So sometimes understanding different patterns in different isotope concentrations can give us indications of life. Also, like Morgan said, looking at different patterns in different other kind of materials, like she said, like the reducing versus oxidizing. But we also look at different patterns of minerals. If we see an overabundance of a particular type of mineral and we don't really know why it's there, that could be a bioindication, could be a type of biosignature. Also, looking at specific trace elements, like big concentrations of trace elements that tend to get used by microorganisms as their specific metal core for enzymes that they use to do metabolism, like for example, molybdenum and vanadium and iron are favorite enzymes, our favorite metals that get used in the core of metabolic enzymes. So those are things that we could look up. If we see a big concentration of molybdenum in one spot, I'd be interested to look at that and go, what's going on there? Why is there this big clump of molybdenum here? Things like that. I'm trying to think of what else. And yeah, the textural biosignatures is very much a thing. These textural features, like Morgan said, stromatolites. I also look at other microbial like microbially induced sedimentary structures and these fine layered structures that we see in sedimentary environments. So there are a lot of different things that could be biosignatures as well as not just the physical like components of life as we know it. And I'll let Abby weigh in some more on that.
Oh, no, that was extremely complete and really interesting. Yeah, I don't have much to add. I'll make one point that Morgan chatted me that I agree with. the idea that if we do think we've discovered a biosignature through any of these chemical or morphological discoveries, if we just find one potential indicator, that's going to be a tough sell. What we're really looking for is to see if we can find evidence that has multiple ones of these kind of coming from all different sorts of directions. And the strongest proof of potential present or past life will be when you have multiple of these lines of evidence that all point to the same conclusion. So that's really the gold standard and what we're going to be looking for.
If I can just add to that, what I like to tell people is it's very much CSI astrobiology. You know, it very much is. You are trying to put enough pieces of your case, forensic case together to get, you know, to get rid of reasonable doubt when you go in front of the judge. And that's what you got to do.
Yeah, because there are going to be very strict judges and like among your sort of peers when this paper goes to peer review, right?
We're a jury of the public,
yeah,
right?
A jury of your peers is going to pick it apart, try to. That's what science is all about. And yeah, just in terms of a more societal philosophical question, I guess, I mean, this is what would like this detection mean? Say it's confirmed and say people accept it and don't scream fake news, which is a possibility these days, unfortunately. But what would it mean for society to make, and for science in general, and for us as a species to have this in our hand? And I mean, I know that's complex too, because is it like related to us, or is it strange life, which we could talk about too? We haven't talked about strange life yet, and what that would mean to make a detection of kind of life as we don't know it. But yeah, what would this mean to us as a species?
So there's so many different ways that can go. For some, it's going. I mean, you know, it's going to be hard for some members of the human species to accept because of the nature of whatever their belief system are. Having that external data point verified is going to kind of challenge the core of their beliefs and, you know, that they've built their life on. So it's going to be a challenge. So I want to acknowledge that that's going to be like a challenge, and that's going to be very hard for them. And we have a lot of conversations like this. We talked to a lot of philosophers, we talked to theologians, we talked to a lot of people about this, you know, what is the impact of this discovery, and that's, you know, how is that going to affect people spiritually versus just, you know, not just societally. I think, you know, I think for a lot of us, I know for myself, I should say, and for the people around me and what I've tried to develop with them, I think it'll be very profound and exciting to have that realization that we're not alone in the universe, and that, you know, life isn't this just fluke. It's more of a pervasive thing, and that to me, and hopefully to the people around me, also means that we could have a future also off planet. You know, the human species can have a future off planet. So I think that would be profound for us to have that understanding that, you know, once Earth is over, that's it for life. That's not the case, you know. Mm-hmm. So it's a big question though.
Oh yeah, totally. Do you have any thoughts, Morgan, Abby?
I do, but I want to give Abby a chance.
Oh yeah, I don't know if I have anything actually beyond what Kenda just said. You know, it'll change everything. I think it'll hopefully be a uniting sort of discovery. I don't know. I watched a lot of Star Trek growing up, so I have the vision of, you know, the Vulcans landing on Earth after the big World War and that bringing everybody together. And so maybe something like that will happen. Probably not, but wouldn't it be nice to think that that's what could happen?
Yeah.
Yeah, I actually go back and forth about this because I remember being on a flight at one point, and I'm pretty friendly, so I usually make friends with who I'm sitting next to. And this is in the pre-COVID times. It mentioned I work for NASA, and the person asked, "Oh, well, we've already found bacteria on Mars, right? So what are you guys doing next?" And I'm like, "Nope, that hasn't happened yet. If it did, I would be doing a really happy dance, and you know that would be really amazing." And so I think, given how prevalent a lot of these, you know, science fiction films and TV series and all of the streaming content that we have now that have kind of normalized these ideas of alien life, and not just in our own cosmic backyard, but beyond, I do think that a lot of people, it may not change things too much for them. But then sometimes I go back to exactly what Kenda and Abby mentioned and how profound of a thing this is. And I really do think if, let's say, we find life on Mars, we realize that it maps to a common origin with Earth, and then we all find out, oh, wow, actually we are all Martians and there was an impact and it transferred stuff to Earth. That would be really freaking cool. But yeah, I think everyone's going to interpret it in their own way with their own belief system, and it's just going to make our jobs even more fun.
So are we at, I think we're at like 45-minute mark, and I think it might be time to start taking audience questions. Is that, yeah? Do we have some audience questions to dig into?
We do. In fact, we do. We've got some really great ones. So thanks, everybody. And if you have more, feel free to put them into the Q&A down at the bottom of Zoom there. But let's start off with this one. If we arrived at a moon or a planet that has no life, but has the potential for life, should we move in or should we leave it alone?
Ooh.
So I could jump in there for a moment. Great question, by the way. And actually, some of us are already thinking about some of these places like the lunar surface as really great testing grounds for some of our biosignature instruments, right? Because we want to make sure that we don't have any false positive measurements. That would be where you take a measurement of a place that does not have life, but then your instrument says that there is life there, right? That would be a problem. And so I think there's a lot that we could still do to help us supplement and challenge our life detection techniques and strategies at these worlds. In terms of us moving in, yeah, if we can leave a few places pristine, I'm okay. I would love to go up there, bounce around in a spacesuit. That'd be awesome.
Yeah, I'm kind of with you, Morgan. Like, I think that, yeah, leaving a few places pristine, you know, like the kind of the whole national parks idea, but even more so, like literally, like just kind of leaving it like in a reserve, like don't go in there at all, I think would be kind of cool to kind of to let it go. And I think the answer is it depends. If it's a place where we can actually move in, you know, then I think we'd have to have a deeper discussion about, you know, the pros and cons and all that. And I think that would take a deeper discussion. But some of these places that have the potential for life are not places that we really want to move into anyway. So I think it'd be good to just kind of, you know, let it roll and see what happens on its own, and just kind of maybe stick a nice space station next to it and kind of keep an eye on it. That would be kind of fun.
Yeah, it's gonna be tough for us to set up an outpost on Europa.
Yeah, exactly.
Do you have any thoughts, Abby?
Oh, I just, you know, thinking about moving into other planets, the moon, Mars, there's no other planet I can think of that has more resources or is an easier place to live than Earth. So I think we need a real good reason why we would want to move to permanently live in one of these places. You know, try living in Antarctica permanently, and that is going to be orders of magnitude easier than living on the moon or Mars. So,
but Abby, if you were standing on the surface of Titan and you had wings and you flapped them, you could fly. You don't want to.
Oh, I'm not saying I don't want to visit these places. I would give anything to go do my geology on Mars in person and, you know, stand on the flanks of Mount Sharp and look out over the rim of Gale Crater. That would be amazing. Would I want to move in and live there permanently? Heck no. That seems like a horrible idea to me.
Oh.
You know, real hard to get air, and there's water there, but not a lot. You're going to be constantly fighting against the equilibrium that the planet is in right now. So it's going to take a lot of work.
By the way, it looks like Jill has a question.
Yeah.
Or a
Jill, do you want to go ahead and chime in?
Sure. I want to go back to something that Morgan was talking about. Morgan, you suggested a methodology where we would catalog the microbial load on the spacecraft. And then when we found similar microbes on a planet, we would ignore them, right? And figure it was contamination. But doesn't that impede our ability to try and figure out whether this panspermia actually happened?
That is an excellent point, Jill. I'm struggling to balance this intrinsic desire that all humans have for exploration and the fact that we are not going to be able to prevent people from going to these worlds and bringing their microbial biota along with them. And so I think that is going to be a challenge, but if we are able to keep certain areas pristine enough, that we'll be able to make comparative analyses there without this need to filter out from potential contamination sources, that could be absolutely something to do. And one nice thing that we're working on now that can help with that is Mars sample return, right? We've had very strict planetary protection requirements for all of the robotic spacecraft we sent to Mars so far. And if we're able to bring back some of those samples and be able to look at them before a human presence is before a human ever first sets foot on the red planet, that may be one way that we can more definitively address that question.
Okay, thank you.
All right, so here's another one. Speaking of Mars sample return, this is a nice follow-on from John Rummel. What provisions would you recommend for sample return in terms of bat contamination control, given the unknowns about Earth and Mars life? Speaking specifically to the sort of COVID-19 analogy is what he writes.
Abby, do you know more about, I'm not a huge, I don't have a whole lot of detail on the MSR planetary protection requirements.
No, I don't either. And John Rummel certainly knows more than I do. So
I was going to say, John, you know more than we do probably about some of these. We know, but yeah.
And for those of you guys that don't know John, he's our former planetary protection officer for NASA. But I don't think we actually have a way that folks that aren't panelists can speak, unfortunately. I don't know, John, we'd love to hear more thoughts from you about that in the chat. Maybe we should move on to another one here.
Just one quick point about that. I mean, I know NASA is planning to build an entirely new facility to house these samples, so yeah, they are thinking about it. That plan is in work, but they're still ironing out details. But they're taking that bat contamination possibility very seriously and thinking about how best to contain it, bio level 4, whatever. They're already thinking about that sort of thing. But yeah, I mean, details are being ironed out.
Yeah, one thing I can say is, we have COSPAR, this international treaty that we have signed on to, as well as a host of other nations, to ensure that we don't bring anything back that could serve as a risk to any of us or any other organisms here on Earth. So that's definitely something that's seriously considered. And if you want more information, I'm sure there's more on the Mars 2020 website. So what is that, mars.nasa.gov? And I think you can find more details there.
Yeah.
Oh, that's great. All right, this is another one from Joseph Urban. If you had unlimited funding, what data would you want to be able to collect to fully verify that there is or is not evidence of life within our solar system? And what would that technology look like?
All the data. Every single instrument we can throw at a sample, I'd want to do. I'd want to do isotopes. I'd want to do looking at, fatty acids and amino acids. So I would want to do isotopes, GCMS. I'd want to do, mineralogical mapping. I'd want to be able to have like something like a micro XRF. So I could do, mapping and elemental mapping of the entire, surface structure. I'd want to be able to have a microscopic imager. I want to be able to do mineralogical analysis, full elemental abundance. What else am I forgetting? I want to do everything. I want to do it all.
I don't know if this is going to sound bad coming from a Mars person, but if we're really interested in the life, like really interested, and we had unlimited budget, unlimited technology, I want a Europa submarine. I think that would be amazing.
I would second that.
Yes, absolutely.
More than one, actually, would be even better. But yeah,
and
definitely.
Let's go to Enceladus and maybe even Sirius
one for
too.
Enceladus, please.
Yeah.
One for Enceladus to go look at the hydrothermal plumes and stuff underneath.
And Titan too. Everyone keeps forgetting. Titan has a liquid water ocean underneath all the cool stuff happening on the surface, like all of these. Yeah, I think having some sort of a drill or a melt probe that could access the subsurface oceans of these worlds, and in the case of Enceladus, some type of robotic snake-like eels would be great, or some other way to get down through that crevasse and into the vent and into the ocean. And not just the top of the ocean. I mean, you can learn a lot at the ice-ocean interface, but getting down to the seafloor, looking for hydrothermal vents, How cool would that
so
be?
Cool. It would be so
Yeah.
cool.
And then exploring places like Ceres more deeply, right?
Wow.
To understand how an ocean world ages and what it's like at the end stages of its life. And then, of course, sending things to, Vega and the TRAPPIST system and all these exoplanets that are the most Earth-like worlds as well, studying those. We would want to do all the things.
Yeah, we'd want it all. Just everything.
Okay, well, here's a follow-up question from a different audience member, but along the same lines. Let's sort of bring it back to the next 5 or 10 years. But what are you each personally most excited about in terms of prospects for astrobiology in the near future?
Abby, you want to go first?
Yeah, sure. Yeah, I'd say two things that I'm really interested in. Obviously the return samples from Mars sample return, and actually even what Perseverance finds once the rover gets to the delta remnants. Right now it's on the crater floor, which is fascinating for its own reason, but the best place we think organics might be trapped are the remnants of this delta, and it's looming tantalizing off in the distance. And Perseverance has some instruments on it that could directly detect some of these biosignatures. So that would be amazing. I can't wait to see what they find. I'm also really excited about the Venus missions, not necessarily in terms of a life detection, but just in terms of an understanding of planets as laboratories for learning how planets work and become habitable or inhabitable. Venus is such an unexplored world, and having that as a comparison to Earth and to Mars, it's going to be amazing in just our understanding of planetary evolution in our own solar system and beyond.
I will just second everything. Absolutely. I will admit that I'm very so excited for a prospect of both a Europa and an Enceladus landed mission. We won't be able to get to that subsurface ocean, but we'll learn so much just getting on the surface and being able to look at what, especially, if we get near both landed missions, anywhere near the plumes, to see what's coming out that could tell us what's going on in those subsurface oceans. That will be so exciting. So I'm very excited for those as well. The prospect of those missions that are on the horizon, as well as, sample return 100%. Percy getting to that delta front is an absolute excitement for me, for the work, especially for the work that I do in subsurface work. And then just the prospect of sample return, and then yes, fight our Venus missions and Dragonfly. And it's just a great time to do the work that we do right now and to be in the careers that we're in.
Oh my gosh, I totally echo that. I just feel so lucky, and to be able to work with amazing people like you, be able to talk to amazing people like the rest of you is just amazing. Yeah, I think Europa Clipper, we're going to learn so much about Europa in just a few years, more than we can all imagine. But like Abby and Kenda said, the in situ missions, there's something about taking an image from like the perspective of being landed or setting foot on another world, that provides. Cynthia Phillips is a friend and colleague of mine, and she talks about this, that provides this perspective that you can't get from an orbiting mission or a flyby mission. And so I think Dragonfly, just like the Mars rovers, we are going to be able to connect to Titan in ways that we haven't really been able. Now, the Huygens lander, of course, gave us the first image of Titan. That is amazing and incredible, but Dragonfly is going to be able to do that from many, many places. And I just can't wait for the first complex mass spectrum all the way up to 2000 Daltons. It's going to be incredible. So anyway, yes, all of this is great. And we're just so lucky to be here, and I can't wait to see what the next 5 to 10 years holds.
So there are actually more questions, but we are 2 minutes until the end of our session, maybe 90 seconds at this point. So I don't know, Mike, do you have any sort of closing thoughts that you want to leave us with?
I personally don't, but if any, do you guys have any things that you want to bring up that we haven't talked about? Maybe one quick thing. Kenda, you actually mentioned that like life on Earth probably started multiple times and died out and came back again. And that's an interesting thing that we didn't really touch on, the whole concept of a shadow biosphere here on Earth. So maybe in the last minute or so, how does that play in? Maybe like the search for a shadow biosphere play into the search for alien life? And that's another big question with the minute left.
I was like, what a loaded question. So that's where my colleagues who do amazing things like experimental evolution and do things like that do work in trying to, unevolve or like turn back time on genes to kind of understand what ancient metabolisms and what ancient molecules look like and how things kind of started. I think that they could better answer that question as far as what that means for the shadow biosphere. But I think from the standpoint of, what it means for life, it means that it kind of, from my perspective, increases the possibility of life on other planets, because it means that there was no one right way that life started.
Right.
It's just that life got started and then something stopped it, and life got started and something stopped it. It could have been, asteroid impact. It could have been, just the chemistry didn't work right, or, it's that there were multiple pathways, but one was able to stick it through everything, including like dinosaur killing asteroids and things like that. So there were, I find it just encouraging that there's no one right way to do life. And I think that that's the take home message for me about that prospect of this multiple start and stops.
And working with our Earth colleagues, right? Like bringing in these people who study the origin of life on Earth, the cryosphere, oceanography, all of these things. So like bringing them into the fold of planetary science and building off of their expertise too. Yeah, I totally agree, Kenda.
Yeah.
Okay, great, thanks. And that's a kind of an optimistic note to kind of end on. I mean, if like life started on Earth multiple times, then it's probably out there for us to find, and we're on our way trying to do it. All right, thanks everybody. That was a lot of fun.
It was great. Thank you, Mike and Kendra and Morgan and Abby and Sarah. I think that was really awesome. I think Elon Musk has famously said he wants to die on Mars. It's probably much easier than he thinks. Elton John has said Mars ain't a great place to raise your kid. I think he's absolutely right. Ellen Stofan earlier today said Mars is not a plan B for planet Earth. Nevertheless, I think that Mars, the prospect of finding life and ideally life with its own unique biogenesis on Mars is fantastic. And the similar prospects in Europa, Enceladus, Titan, and elsewhere. So yes, let's put submarines on those worlds and let's investigate. Personally, my quote in all this is, I think the most remarkable thing we might discover about life is that it's not that remarkable after all. That wherever it can take hold, it absolutely does. Intelligence and technology may be a different matter, but in any case, this was a wonderful conversation. Thank you all so much. And I think we're going to move directly now to Jonathan Keats and our artists in residence from the SETI Institute to take us through the next half hour. Jonathan, are you there?
Yes, I am here, and I am happy to present Bettina Forget, who has been running the Artist in Residence program at the SETI Institute and has organized with us a program that she will present in terms of bringing a couple key SETI artists into dialogue with some of the great themes that have already come up and that will come up ahead. So I'm going to turn it right over to Bettina, and she can take it from there.
Hi, Jonathan. Thank you for this introduction, and thank you for including the Artist in Residence program into this wonderful conference. So welcome to this artistic interlude to Earth at the Crossroads. You will be treated to 3 presentations by 3 of our artists in residence, works that will reflect on the thought-provoking conversations that we've had up to this point. My name is Bettina Forget. I'm the director of the art program, as Jonathan mentioned. The program connects contemporary artists with our SETI Institute's researchers and facilitates an exchange of ideas to catalyze new perspectives, insights, and modes of comprehension. Our program encompasses various artistic disciplines, including the visual arts, literature and spoken word, music, film, dance, theater, with artists hailing from the US, Mexico, Germany, China, and Dubai. The artworks, performances, and public projects resulting from the AIR collaborations are situated right at the cutting edge of artistic and scientific practice. It is my immense pleasure to introduce 3 artists who work right there at this cutting edge: Dexter Spitz, Felipe Perez Santiago, and Daedalus. Hello and welcome, everyone. So first up is Dexter Spitz, aka Jordan Holmes, who describes himself as a nerd by day and artisan entrepreneur by night. Jordan has a background in materials science engineering from Virginia Tech, but is also a self-taught writer of music and spoken words performed by his alter ego, Dexter Spitz. Today, he is presenting both spoken word and music pieces. Dexter, why don't you go ahead and share your work with us? Sorry.
Sure. Hello, and thank you for the warm welcome. That was a pretty good intro. Usually it's difficult for people to try to pinpoint who I am, but you got it down pretty good. So again, thank you all, and looking forward to sharing a couple of pieces with you all. I have one that is spoken word and one that is music themed. First up will be the spoken word piece. And the place that I kind of went to with this conversation today was when I look at the positive things that we need to do to make this world a better place and to make things more sustainable, I think that we first have to turn to ourselves, first to kind of look inward. I really love this quote that, the color of the paint within the can is basically going to be the color of the walls. So my thought there is, that like we really have to look at what we have internally going on, because that'll ultimately result in what shows up in the world. So I'm going to share this first piece and share screen. Okay. And you guys can see my screen, right? Can you hear me okay? Somebody give me a thumbs up. Okay, yeah, just making sure. I really, really, really love cheeseburgers. The greasier, the better. You can hold the tomatoes, but throw on some lettuce with as little nutrients as possible, grilled onions, ketchup, mustard, lather it in barbecue sauce, and don't you dare add bacon on it. Now, of course, a higher class burger is preferred, but on a late night, a fast food place whose arches shall not be named will do. And I know that it's not good for me, but it's fast, it's tasty, and it's convenient. Now, in general, I eat relatively vegan, actually, working out most days of the week, running miles with the dogs, taking vitamins, eating the rainbow of fruits and veggies. I quit alcohol and smoking, yet I sat at the doctor's office while I wrote this. My doctor is concerned that I have high blood pressure. Me, with high blood pressure, why? See, I promise you that my diet is not all burgers. My blood work looks good. So we sat and we discussed it in the office a bit. And she said, maybe there's a genetic component. The scientific jury is still out on this topic. But if you go back in my family history, high blood pressure is all over the place, along with obesity and substance dependency, all results of what I thought of as convenient-based indulgences, but also trauma, abuse, and hardship. See, it's in my blood. I have sworn to break the cycle. So here I am at the crossroads between convenient indulgence and sustainability, trying hard to unlearn unhealthy pathways passed down from my father and my father's father and so on, just to keep living. My father's father died of a brain aneurysm. He had high blood pressure for years. It's the silent killer. I have no recollection of meeting him, but I did as a baby, apparently. It seemed that he consumed alcohol and nicotine like they were going out of style, drinking, smoking, chewing, cigars, cigarettes, you name it. And I don't know what his eating habits were like, but I can't help but wonder if he loved cheeseburgers, because I too struggled with nicotine. Now, I'm sure there are deeper influences contributing to the continuous consumption, as there were with me. For him being a Black man in the South in a less than ideal time, the pressure added up of being a man in society at that time, not being able to express emotions or vulnerability, just always pressing on and on. But nonetheless, I doubt that the consumption practices or that environment lowered his blood pressure. Mine rises just thinking about the hardship, and he literally died when the pressure was too much. We know more about health now than back then, but one thing is for certain: endless consumption, whether in pursuit of convenience, quick satiation, numbing the pain, or obtaining the new shiniest object or high, doesn't seem to work out well in the long run. And I lay awake at night contemplating between if it's something that I am doing wrong, or if I am handed down genes or affinities for poor behavior that I didn't ask for. See, here I am at the crossroads between convenient indulgence and sustainability, trying so hard to unlearn unhealthy pathways from my father, my father's father, and so on, just to keep living. I don't know if my grandfather ever even had a chance to think about his health. Were the immediate circumstances too pressing? Was there too much trauma passed on to him that he never asked for? It's hard to think about the future when the current is pressing and alarming. See, I am conflicted at feeling frustrated that I do everything to try to stay healthy, wanting to just eat a cheeseburger in peace, but having the guilt of one more bite sending my blood pressure even higher. And I know that it's the silent killer, so the convenience is nice, but it rocks me to sleep. But I also know that I can now choose differently. But how very blessed am I for standing on the shoulders of my father and his father and so on, to even have the time to choose differently. How blessed am I for standing on the shoulders of my father and my father's father and his father and so on, to have the knowledge and the perspective and technology and insight and resources and research, the voice, the platform, the courage, which is also still in my blood, to know and choose differently. So here I am, left with a decision at the crossroads between convenience and sustainability for a better life for me, for us, and our future generations, just to keep living.
Okie. So that is the first piece. And then the second one here should be a short little snippet. Essentially, what I'm constructing for the SETI Air program is a series of stories and kind of music videos that are told through basically music about space related things, but not too on the head. But I will play just some still images along with the track called I Need Space. So.
Space when I'm feeling like I can't get my mind ever calm down, get away. I need space. Oh, what can I do? Oh, what can I do? Oh, no, no, no. Oh, what can I do when I'm feeling like I need to get away, get away? I need space. Input overload, overload. Way too much time on the phone, on the phone. I've been moving like a million miles a minute, but it feel like light speed. 99 problems, one more 'cause you don't like me. I've been trying to find a way to love within myself, and you just tell me down, trying to throw me on the shelf. Instead of criticism, you could throw a little help. But everything's perfect when you're talking about yourself, right? I guess we all biased. What would the world sound like if we were all quiet? What would the world sound like if you felt heard? Like, who am I if everything I want is self-serving? All the hate, get away, get away. Take me to a place where I feel safe, you can come too. Trying to find a little bit of space, trying to find a little bit of space just to run to. Oh, what can I do when I'm feeling like I need to get away? I need space when I'm feeling like I can't get my mind ever calm down, get away. I need space. Oh, what can I do? Oh, what can I do? Oh, no, no, no. Oh, what can I do when I'm feeling like I need to get away, get away? I need space.
All right. Yeah, so thank you again. There will be more to come with the project with some visuals. If you check out any of my work, you know, the visuals get pretty weird. But thank you, and looking forward to the other SETI Air artists.
Oh, that was awesome. Thank you so much. And I love how you sort of bring everything back to the human condition, especially, I think that links so beautiful to the conversations we've had today. All right, so next up is our artist Felipe Perez Santiago. He's a multi-laureate composer and one of the most active and recognized musicians in the current artistic scene. His music has been played on commission in over 40 countries and is included in more than 20 discographic productions worldwide. He's the founder and artistic director of the Malka and Vortice ensembles. Felipe has been collaborating with Jill Tarter on the phenomenal Earthling project. So Felipe, come and tell us more about this amazing collaboration.
Yeah, thank you very much, Bettina, and thank you everybody for being here and for having me invited. It's really an honor. It's a pleasure. I will be very brief because we don't have so much time, and obviously I want to leave some time for Alfred to do his presentation. So the Earthling project, I've been part of the SETI Air program for nearly 4 years, something like that. And I have been partnered with Dr. Tarter, which is a great honor for me to collaborate so closely to her. And the idea of this Earthling project is to gather human voices from all over the world, for which we developed an app here in Mexico City with a great team of collaborators. And through this app, people from all over the world could download it for free and record their singing voice, expressing something about their culture, tradition, personal life, etc. So we got hundreds of submissions from all over the world. We got recordings from more than 50, 60 countries from all continents. Incredible recordings from children all the way to elderly people. And with those compositions, what I did is made collages of people singing together, like if they would be singing the same song, let's say, like they would be in the same room singing together. And all these recordings, all these compositions, which turned out to be 7, they will be sent in a disc to the moon with our other partner, who is the Arc Mission Foundation. And they will be set in a disc, which will be launched to the moon next year in collaboration with the Astrobotic Space Agency in the Peregrine mission. So it's very exciting to know that all the people involved, which are, like I said, hundreds of people from all over the world, now they can stare at the moon and know that their voices will be up there in a disc that is meant to last about 5 billion years, and is the first time that we make a disc like this in human history, at least to be set on the moon. So since we don't have so much time, I will share 2 of the recordings, or well, let's start with one and then we'll see, because I really don't want to take away Alfred's time. But I'll play the lullaby that it was made with lullabies from all over the world of people that shared me their voices. I'm starting sharing my my screen, and I will share the computer sound. And now I will play this lullaby. If you have headphones, I would strongly recommend you to use them. If not, it's also fine through the speakers of your computers.
꼭 달가우지 마라. You got an idea You got an que tienen sueño.
Ninna nanna ninna oh, questo bimbo a chi lo do? Se lo do al lupo bianco, se lo tiene finché è stanco. Se lo do alla befana, se lo tiene una settimana. Se lo do al bove nero, se lo tiene.
You got an IQ of 22. Your most expensive clothes are body shoes. You're walking down the street.
En la noche caminaba entre las nubes.
Turn 16 and
Tus divinos ojos con sueño.
questo bimbo a chi lo do? Se lo do al lupo bianco, se lo tiene finché è stanco. Se lo do alla befana, se lo tiene una settimana. Se lo do al fuoco nero, se lo tiene.
Llamadela, pom pom pom, oso sanga, pom pom pom. Mariva querida se mariva nase.
So that is the lullaby, and I will play a very short one, which is the melancholic. There is only about 2 minutes, so yeah, we can proceed.
از همه جاده حالیا para volar in my head, in my head, la batalla la libre voy a ser tornado, voy a ser just fight my war in my head, in my head, in my head, in my head. Mi sala dans mon petit canon, intimement crevé dans mon petit canon. از همه دنیا
Okay, thank you very much. So that's part of the project, the Earthling project. So I leave the space for Alfred to show his work. Thank you very much.
Oh, thank you, Felipe. That was phenomenal. I so love your work. It's very hard to squeeze 3 phenomenal artists into a half hour. So I really appreciate everybody, trying to make the best of the short time that we have. And I also put the Earthling website into the comment section. So please go and check that out. So we're moving on to Daedalus, also known as Alfred Darlington. They are a trailblazing artist, DJ, and producer who have been active in the electronic music world for the past 20 years. Under the alias Daedalus, they have released over 20 LPs and countless EPs and remixes. They are currently assistant professor at the Berklee College of Music in Boston as a founding faculty member of the new electronic digital instrument program. Thank you, Daedalus, for joining us, and it's over to you.
Thank you so very much, Bettina, and I really do appreciate everyone's contributions today, both these artistically melded in everyone else's sentiments and the science realms. I'm overwhelmed at this possibility and equally at the challenges we face I guess my piece today is a comment on how noisy we are as a people, how much din and kind of chaos we generate and just are emanating out into outer space. And yet when we're looking the opposite way, when we're trying to find similar signs, how relatively scarce it is. And that we have this idea that if maybe we just caught a bit of our own reflection, we would have this kind of semblance of intelligence and understanding. And so I'm trying to crystallize that, synthesize that quite literally, using some modular synthesizers today. I'm going to be doing a short performance, hopefully, and I'll try to be mindful of the time, using a few techniques, gesture-based modulators, sequencer, what's called a quantizer, and then an oscillator, in this case, a wavetable oscillator. Not to get too technical, but I think this is the right place to be a bit technical. So I'm going to go ahead and present that thusly. I'm going to turn off my video and get that going. But thank you all so much for being part of this wonderful, grand everything. Let's get this going. Is that coming through? abrupt, but I want to be mindful of our time and be careful and conscious of the contributions we can make. Oh, I should have mentioned too, rose quartz was the other component, maybe not as potent as some of the other modulators, but possibly had an effect or influence on what was going. So thank you all so much for having all of us SETI heirs today.
Wow, bravo. I was mesmerized. It's sort of magical and out of this world. And I could have listened to this for another half hour. I'm so crushed that, we have to wind this down. Thank you to everyone who came today. Thank you for joining us for this half hour. Find out more about the SETI Air program at seti.org/air and see all the we have 8 artists in total. So come and check that out. Back to you, Bill.
Thank you, Bettina. Thank you, Alfred and Dexter and Felipe. That was just awesome and inspiring and moving, and so wonderful to have the opportunity to explore this intersection between art and science, which you guys do so eloquently. So thank you for that. We're going to, and I will say, by the way, we will give you a longer opportunity in the spring when we reconvene this workshop and this event at Georgetown University, hopefully in person with COVID permitting, for a much longer event and an opportunity to do things in person and really to appreciate the work that you all do. So we'll look forward to that. And with that, I'm going to hand it over to Jonathan, who's going to kickstart us as we go beyond the solar system and explore the topic of habitability beyond. Jonathan?
Thank you, Bill. So we have already today explored the L variable and habitability at home and habitability also in the solar system. So it seems only natural and apt that we should go beyond to the universe, or maybe the multiverse for that matter. We are really looking at an escalation in scale here, which I think is going to be very interesting with this panel that will be moderated by Ross Anderson, who's the deputy editor at The Atlantic. We're looking at an increase in sample size on the one hand, but also greater ambiguity potentially because we're looking farther away and gaining potentially a broader perspective that contains all sorts of complexities that we really need to figure out what it all means. And so with that, I am going to turn it over to Lee to roll the video.
If you're the pessimistic type, you probably figure that humanity is headed for the exit. We're going to do ourselves in. We might do that with a nuclear weapons, just unleash them all, let them fly, and that would probably take us off the surface of the planet. Or maybe we'll use our biotechnology to make designer babies and sort of eliminate Homo sapiens, or just construct a pathogen that no medical interventions can stop. But the threat du jour is in fact climate change. Climate change extends for a century in front of us. We're not doing very well in combating it either. Is there any sort of experiment that might give us hope? Is there any way to know that we have at least some hope of having a longer L, if you think in terms of the Drake equation? Well, there is, and it's called SETI. Yes, if you do a SETI experiment and you pick up a radio signal or a flashing laser, or you see some sort of giant artifact like a Dyson sphere out there in space, you would know that at least that society was able to, survive their technological adolescence, to make a long-term go of it, and that would be encouraging. Now, if on the other hand you don't find a signal, well, that's a little bit ambiguous because you don't really know. Does that mean nobody was able to do this? That everybody wipes themselves out after they become a little bit technological? Maybe, but maybe they're just deliberately being cryptic. So the bottom line there is you can't prove a negative. And even though SETI is an imperfect crystal ball, it's the only one we've got.
All right. Hello there. I'm Ross Anderson, Deputy Editor of The Atlantic. And in this session, we are going to be talking about habitability beyond the Earth, as Jonathan said, through the lens of the Fermi paradox and the Great Filter. And as you all know, these are conceptual tools that emerge from the search for extraterrestrial intelligence. a domain of scientific inquiry that has sometimes struggled for legitimacy in a way that I suspect future historians of science will find perplexing. I've been working on a book about SETI, and in doing so, I often find myself evangelizing for it. And one of the things that people are often surprised and delighted to learn is that SETI scientists spend a lot of time thinking rigorously and creatively about how civilizations like ours evolve with their planets across deep time. And so I'm excited that that's our theme today, and even more excited to have with us for this conversation 3 scientists of the first rank who I will introduce now. And give a little wave, I guess, when I say your name. First, we have Dr. Jill Tarter from the SETI Institute. Second, we have Dr. Sophia Sheik from UC Berkeley. And third, we have Dr. Sarah Walker from Arizona State University and the Santa Fe Institute. Okay, I was hoping that to start us off, the 3 of you might each give us a kind of foundation for this discussion by sharing your perspective on the Fermi paradox, this idea that our failure so far to observe intelligent life out in the cosmos is somehow surprising or requires explanation. And then I hope you might tell us what you make of the great filter, the idea that one way of explaining the Fermi paradox is that there's some difficulty latent in capital N nature, some filter that prevents planets, which we know exist in great number, from evolving into observable civilizations. Dr. Tarter, let's start with you. What do you make of these ideas as tools for thinking about SETI and for thinking about the fate of our species and planet?
Well, thanks, Ross, but you've started with one of my pet peeves, which is the Fermi paradox, because there is no paradox, right? The logical structure of that argument is that if anywhere, anywhen another technological civilization had arisen, they would inevitably, very quickly evolve the capability for space flight. And then they would use that capability to populate all of the worlds in the galaxy anyway. And we look around and we say, they're not here. And the only way to get out of that is to say they never were anywhere, anywhen. But I think that's wrong, because I think we can't say they're not here, right? If you were interested in the question of, are there any fish in the ocean? You could take a glass and dip it in the ocean and then get it up here and take a look and see, did you catch any fish? Well, that's an experiment that could, in principle, work. But if you didn't see any fish in your glass, you're not likely to conclude that there are no fish in the ocean. You're likely to conclude that you haven't sampled enough of the ocean in order to have a reasonable chance of catching a fish. And of course, you'd miss all of the lovely fish that are much bigger than your glass. So I think that's where we are with respect to exploring for technological civilizations elsewhere. We just haven't looked well enough, long enough, and possibly in the right way to be able to make any significant statement about the existence of extraterrestrial technologies. So I don't like the term fairy paradox, because we can't say they're not here yet. So I can't think that we can't construct a logical paradox.
Jill, I find myself quite sympathetic to your position, and I hope I tipped that off in my intro. But Sophia, what about you?
Well, first of all, totally agree with Jill on that one. You sort of stole my line of argument in a way there, so now I have to come up with something else. But actually, I think I'll take that opportunity to say, yeah, if you don't see any fish in the glass, the conclusion should probably be we need a bigger glass and not there are no fish in the ocean. And so that's something that we're working on. And the hardware that we develop, especially to do radio SETI searches or radio technosignature searches, which is what I specialize in, is developing so quickly especially over the past couple decades, that we're able to, instead of going glass by glass, go, well, hot tub by hot tub. And that's only going to improve over time and accelerate how much of that search space we can look at. And so right now, it's very hard to say, how many extraterrestrial intelligences might be out there with these sorts of technologies, but we're starting to place those limits. And so I think this is a question that we can come back to in a couple decades or 100 years, and then maybe there will be a Fermi paradox. But until then, it's not maybe worth trying to conclude too much from our non-detection so far. And then on the point of the Great Filter, there's something very interesting here that I would love to talk a ton about, but I'll try and keep it brief, which is that as we move through human civilization, the things that we are anxious about, the things that Seth mentioned in that intro video, things like bioengineering pandemics or climate change or things like this, change. And they're often related to anxieties about what our current technological capabilities are and how that could go wrong. So from papers in, say, the 80s and 90s, you see a lot of anxiety about nuclear annihilation. And so there were SETI papers thinking about, like, okay, maybe that's the Great Filter. As soon as you get the capability to build nuclear weapons, you blow yourself up, and that's why we haven't found any extraterrestrial intelligences. And now, if you look at a lot of the existential risk literature, you see people talking about artificial intelligence. We're going to create an AI that goes rogue and destroys humanity. And maybe that's why there's a Great Filter. And so I think a lot of the different scenarios that people construct for what technosignatures we're going to be able to detect and what ways that civilizations might kind of traverse through their lifetimes and eventually end are very much related to where we are as humans. And you can see this as well with atmospheric pollution and climate change, which are also very prominent in the current SETI literature. And so I think that's where we need to make sure we're incorporating the perspectives of people in the humanities, of historians, of science and technology scholars, to make sure that we're not carrying these biases around without being aware of them.
And Sarah, what about you?
So I also agree that the Fermi paradox and the Great Filter might be ill-posed, but perhaps for different reasons than what Jill and Sophia pointed to. And the reasoning that I have really is that there's a lot of assumption that we understand what we are, and therefore when we're looking for other examples of the phenomena that we are in the universe, we think we know what we're looking for. And I just don't think that's accurate, because I think we're very close maybe to developing a theory that is a more fundamental understanding of the nature of life and intelligence in the universe. I hope we're close, but we don't have it in hand yet. And so just as sort of an example, we did make first contact a few years ago with a phenomena that we predicted existed, but we had never detected in all of human history before even the history of our entire planet, which is gravitational waves, right? And gravitational waves permeate the entire universe, but unless you have the theory that predicts their existence and the technology to actually go out and detect them, you can't make contact with that phenomena. And I think we're premature in thinking that we're going to be making contact with alien intelligence because we actually don't understand the nature of that phenomena, and we don't yet have the technology for making that contact. Although I think the sort of efforts that have been built up over the past decades are brilliant as far as looking for radio signals. It might not be that that's actually, we know what to look for in those signals, or we actually know yet, what the search volume is, or what other kinds of technology might be out there. So I think for me, the sort of first question we need to be asking is, what are we? And to that point, the Great Filter, I think there's another way that you could define the filter, which is that technology evolves on a planet. It's part of biological evolution. It moves into technological evolution. Whatever the physics is that describes us should describe all of that. And at a certain point, you have enough understanding about the universe to understand yourself. So there's a filter as far as your perception of the physical world and what you can actually detect out there, right? So gravitational waves we didn't detect for 100 years after we understood what they were. When we understand what we are, we also have to develop the technology to do that. So there's a technological filter on our ability to actually detect ourselves. And so, or other examples of us out in the universe. So I think when we're thinking about sort of the technological phase transitions we're undergoing now, one of those key transitions is actually going to be artificial intelligence, because artificial intelligence is building systems that are like us, but not us. And they can help us understand ourselves in ways that we wouldn't be able to do without them. It's a little like, when you invent the microscope, you can see a whole world of microorganisms. So maybe you were looking for that fish in that volume of water in the ocean, but you didn't realize that there were tons of microbes in there until you had the technology actually to see the life in what you were looking at. I think artificial intelligence is going to be critically important for us understanding ourselves so that we can actually see that sort of volume of space that actually is life out there. And just one final point I want to make on this note related to not understanding ourselves. There's sort of this implicit assumption that we make that life is common in the universe. And I think that's really premature because we actually don't know what the phenomena is. I'm very optimistic it's common and that we'll find it. And the kind of things that we're doing are going to be really helpful in the long term for discovering what we are and actually finding other examples. But right now we simply don't know the probability for the origin of life, and therefore we can't say anything about the likelihood of life on other planets unless we detect it or solve the problem of how life arises in the first place.
I want to touch on a point you were making, Sophia, which is about whether certain stages of a civilization or some intelligent life's development are incidental, or whether they happen for all intelligent life. For instance, someone might think that all civilizations necessarily originate from a planet or a moon, but perhaps as you move further away from their origins, and this gets to what you were saying, Sarah, although you were saying this about their very origins, into more complex features like organism anatomy and culture, the less likely you are to see that kind of convergence. And so I want to ask all three of you, especially as it concerns our topic today, whether you think that climate change or extreme biodiversity loss, or pick your favorite kind of extreme ecological crisis, are just inevitable steps on the civilizational ladder, something that just always happens when a tool-making species first industrializes? Or are we enabling ourselves by thinking so, by pretending that our specific choices, our preferred modes of relating to the Earth and its other inhabitants are universals?
Well, let me just make a comment there. We used to be very fond of quoting Arthur Clarke's third law. Any sufficiently advanced technology will be indistinguishable from magic. But today's philosophers are actually posing that any sufficiently advanced technology will be indistinguishable from nature. And I'm quoting Carl Schroeder there. And I wonder if indeed those two examples don't indicate the arc of our cultural evolution, and that there may be a commonality in that, because it takes an aggressiveness and a curiosity to get us intelligent in the first place. But if we don't overcome that aggressiveness, we're not going to have a long future. And so if indeed you get the evolution of cultural evolution as well as biological evolution, and that cultural evolution allows you to act in a way that is not as aggressive to your fellow creatures, but allows a state to set rules and enforce punishments, then I just think that might be a common arc.
I guess I'll jump in next here. So it's hard to say, right, one way or the other, whether we are an example of a common civilizational arc of intelligent life, or whether we're an outlier. But I think it is interesting to see where the work has gone in the field. And so one kind of common framework that we use is the Kardashev scale, this idea that you can quantify the some sort of intelligent civilization by how much energy it consumes. And this is very useful. It's a useful framework for trying to figure out what kinds of intelligences our instruments are sensitive to when we're doing searches. But I think it also illustrates the way that we think about the evolution of other civilizations, which is that there's some sort of resource consumption, energy gathering, energy use that is expansionist, that is accelerational, and this very well maps onto what humans have done. And so there's been a lot of work in that area thinking about what's the most efficient way to collect energy. Where would you want to be in the galaxy if you care about collecting energy? And there hasn't been kind of a commensurate amount of work thinking about what if that wasn't your goal as a civilization? What if your goal was to live sustainably with your planet and you didn't have ambitions to collect as much energy as possible or extract as many resources as possible? Now, there is an argument to be made that the most extractive civilizations might also be the easiest to detect, but I think there's a hole here where we need to think about what would a civilization's evolution look like in harmony with its biosphere if it wasn't being as extractive as possible. And that's important, not just for understanding what sorts of extraterrestrial intelligences we might detect or we might be missing, because we're missing the sustainable ones perhaps, but also important as a mirror to figure out what our civilizational track might look like and how we could use our imaginations of what other civilizations might do to improve our sustainability and relationship with our biosphere.
So I think maybe when we're thinking about these problems, it seems like there's two issues when we build narratives about ourselves or when we're building narratives about what other intelligence might be out there. And the issues are that we focus too much on the nature of the individual and we focus too much on the nature of our particular point in time. So individuals are special and our point in time is special. And if you remove those kind of assumptions from how you're trying to understand what's happening now on this planet and what the implications of it are, and you think over much longer timescales as we do as astrobiologists to think about the coevolution of life in this planet over many billions of years. And you also realize, as Jill pointed out, that there's cultural evolution and collective phenomena happening in human civilizations and with our technology right now. I think the narratives that we build from that understanding are quite different. And I think that there is some indication that long-term sustainability is possible, and the kind of hiccups we're having now are things that feel very existential to us because we're talking about them a lot. And usually I tend not to worry about the existential threats that we talk about a lot because it means it's on our sort of collective consciousness that these are problems and they need to be addressed in the near term. And so I would think like the greatest existential threats to civilizations are the ones that we're not actually thinking about because we're not even aware they exist. And so I think long-term thinking is actually critically important for having a proper dialogue, which I think Sophia and Jill already alluded to, but I just wanted to stress that point.
Yeah, this question of long-term thinking, Sarah, is so hard now when things are changing so rapidly. Now, 1,000 years ago, you're going to do what your parents did, right? Because things weren't changing culturally. But now it's very, very difficult to establish a mindset where you can think in terms of a long future.
Yeah, but I think part of the thing is like that information is getting integrated at a scale individual humans aren't aware of anymore. So because our technology and we as people are so integrated, some of that processing is actually happening at a societal scale and not an individual scale. So I think there's always sort of a level that's actually keeping in pace with the sort of longevity of that system. It just might not be us anymore. And culturally, we have a lot more idea what's going on than we do as individuals. So I agree. I think for us as individuals, it feels very fast, but I don't think for sort of technological evolution, what's happening right now is fast at that scale.
Let's return to the Fermi paradox for just a second, the Fermi paradox that we've all resoundingly rejected. Suppose that we wanted to use today's technology, I'm going to ask you about some speculative astronomy a bit later, but just stick with today's technology to have a better sense Fermi's paradox, whether it is actually in fact paradoxical or just provisional. And imagine you could commandeer the budgets of NASA, the NSF, the ESA, Roscosmos, whatever, and whatever other bucket of money, various billionaires there is out there to search for intelligent life. What would you want to do?
That one is something that we talked about at the turn of the century when we published SETI 2020. What would we like it to do? And the thing that we realized is that over all these decades, we've had essentially zero sensitivity to transient phenomena. So our answer to that is you want to look at all the sky, all the time, and across the entire spectrum. And we're beginning to make it, finally, decades later, make it a start on that with some optical SETI searches that will look at 10,000 square degrees of the sky at the time, or in fact, all the sky all the time with laser SETI. And in the microwave with the Malure wide field array, it's a start, but that is what you'd want to do. If you had infinite budget, you would really want to be looking at all the sky all the time at all frequencies, and you'd want to be developing as unbiased machine learning algorithms as we can build to take in this fire hose of data and look for something that we don't predict. So the other thing we've been doing since the beginning is asking machines, does this pattern exist in the data? But we really want to be asking, are these data information rich, or are they just noise, and not be prescriptive about what we're looking for?
So I have quite a different example, which is just coming from the other end of the spectrum. So I think Jill's suggesting we look for technology and look for these kind of unseen signatures of it. I think we need to build better origin of life experiments. And what I mean by this is we need to do it at scale, where we have international collaboration, multi-billion dollars, to actually explore chemical space using digital robotics and sort of the robotic, like there's a lot of digitization of chemistry and chemical experiments at scale. And part of the reason for that is if you build a planet simulator on Earth, that is a geochemical engine that is evolving chemistries out of it. And then you actually are exploring those for the emergence of lifelike or intelligent chemical systems. You are actually building a platform for constraining the value of the P-life term in the Drake equation, right? We don't know the original life term. We don't have any constraints on it, but we can actually start to bound that probability by doing that. And we can do that here on Earth. And we have a lot of the technology already to do it. And we have a lot of the theory to guide that kind of experiment. And I think if we do that, it's a really different way of talking about the search for intelligent life, because we're basically trying to grow it in the lab from scratch. But those life forms, if we do the experiments right, would be as alien to us as anything that we might find off Earth. And it would be under a set of conditions where we really could start to understand the process. So for me, that's the number one, because it would solve the origins of life and allow us to have some constraints on what we're looking for elsewhere.
So Sarah, do these models have feedback in them?
So a lot of the ways that we talk about doing these things is actually like a recursive exploration. So if you imagine that you had an AI that was like actually partially physically embodied in a chemical system and sort of abstractly embodied in AI, and it was doing a recursive search of chemical space, you would actually be able to kind of curtail the combinatorial explosion and actually search along directed pathways. So there's some way of building intelligence into the exploration to look for other intelligence, but I think it's within the realm of possibility. There's a lot of people interested in this. I don't think that, like we think software is intelligent, but software is not embodied intelligence. It's not the same as us. It's something we invented, and it's very abstract, and it doesn't have quite the same properties as chemical intelligence does.
So I wanted to take a totally different tack with this one. And this is partially inspired by the Astronomy and Astrophysics Decadal Survey that came out kind of within the last week or so. And something that's really interesting is for these big surveys, state of the field, all of the money of the giant federal funders looking for the next 10 years. There's a lot of focus on missions, what kinds of instruments can we build? What kind of surveys can we design? to get as much data as possible to learn more and more about our universe. Don't get me wrong, that's fantastic. But at least for searching for intelligent life in the universe, there are many existing data sets that are kind of untapped, and many ideas that people come up with and say, hey, technology might do this. And if it does that, it should be detectable like this. And then no one ever searched for it. Papers that came out decades ago. And it's there are many reasons for that, but partially it's been just a lack of funding and a lack of a community to follow up these ideas and to discuss these ideas. And I mostly work in radio wavelengths, but the more time I spend in the field, the more I realize that we really need a very diverse, both in the participants and the science that's being done, portfolio of extraterrestrial investigations. So that's things like, we should look for Dyson spheres, but what if extraterrestrial intelligences don't make Dyson spheres for some reason or another? Then we should be looking for radio signals. We should be looking for intelligent species that pollute their atmospheres the way that we've done to ours, but we shouldn't be maybe putting all our eggs in one basket. And so I think what I would love to see is just more support for kind of furthering all of the different avenues of searching for intelligent life, because right now we don't know which one is going to succeed. So we want to make sure that we're following up all of the possibilities, and also just support for kind of new blue sky ideas on what intelligent life might be like, what technology might be like, inspired by things like artificial intelligence and synthetic biology, where we can go down these kind of rabbit holes of, okay, what if we're the weird ones? And most life is like this other thing we haven't even conceptualized yet. What signatures would that leave? And so I think that's something that kind of with infinite resources, I'd love to see so many more minds getting involved in this project, so many people collaborating on very different ideas, both ones that have already been theorized and ones that we've yet to come up with.
Let's those were outstanding answers. Let's indulge in a little speculative astronomy. Imagine astronomy as it's practiced, say, in the year 3000. Do you think by then, or at some future date, with a massive telescope or several, leveraging some local lensing effect, it might be possible to watch a bunch of civilizations, assuming that a bunch of civilizations exist across the galaxy in sufficient detail to see how they evolve over time? You know, there's already theoretical work on how we might be able to zoom in on exoplanet atmospheres, of course, and spot everything from pre-agrarian civilizations to planets that are covered in cities, to those engaged in nuclear war. And I'm wondering if we might be able to use techniques like that to develop a kind of grand census of civilizational outcomes, or would that kind of knowledge only be possible with contact and cultural exchange?
Ross, I think you could do it in a statistical sense. I don't think you'll ever do it by finding a single example and waiting around and continuing to observe it to see how it changes. Because, you know, we have a finite lifetime and we're pretty damn not very patient. So I think that you could probably do it the way we have done, constructed the story of how stars and planets form, by looking and finding lots of examples at different phases. Now, we have, with the planet and star formation, we have confidence that the physics is going to work the same everywhere. So we can put apples and oranges together in a time sequence and infer evolution. I don't think we have that kind of confidence necessarily in technological evolution, or the evolution of cultures and species, but we could try. I don't think you'll ever get there by studying just one, but statistically, with lots of examples, we might be able to try and answer your question.
Yeah, now I'm thinking about like trying to infer general theories of economics from observing exoplanets. But I think that's the right way of thinking about the problem, though. If you have enough data points, you should be able to reconstruct the general principles. Yeah, I agree with that.
I definitely find myself somewhat skeptical that we could get the sort of data we would need to really understand what was going on with another technological civilization on the planet. So I think maybe, given this kind of example where we can observe a lot of different civilizations throughout the galaxy, we could get some senses as to what might happen, potential just outcomes or almost states, potential states of planets. But I think without some sort of contact or exchange, which of course, given the distances between things is very difficult, it would be hard to understand the why and the how. I think a statistical census would be the only way to go about it. So totally agree with both Jill and Sarah on that. But even then, I think it's so easy when we, as humans, to project our kind of biases onto whatever we're trying to observe. And so sometimes that's, observing animal behavior and attributing kind of anthropomorphic ideas onto that behavior. And I think you would see a very similar thing where we see like, oh, there's a civilization on this planet and we can measure the temperature going up and up. And we can say, oh, well, that's an example of global warming, and global warming happens because of these reasons. But I think that would be going a step too far. We don't know that that's why a planet might be warming. And so I think even with really good observational information, it's hard to understand something as complex as an intelligent species interacting with its planet, interacting with its technology, from just passive observation and data points. But maybe I'm wrong about that.
Sophia, my favorite example of this, I think, which is given the budget that you say, and these fantastic telescopes will build something that can actually image those 7 Earth-sized planets in the TRAPPIST-1 system. And they're at different distances from their host star. So physics tells us they should be at different equilibrium temperatures. But suppose we can image them and we see that they all look the same, right? They're all at the same temperature. They all have the same albedo. They all look identical in our fantastic telescope of the future. What does that tell us? Is that a way of deciding that you've got a technological civilization there that wanted some more real estate? So it went to the next planet over and made it home.
So there's one more thing here that I think that we need to take into consideration, which is how convergent is technology across different examples of life, which I think Sophia might have touched on a little bit, but, there's a lot of assumption that, if we're looking for alien life form, even at the chemical level, it'll use the same molecules that we use on Earth, right? So we use amino acids to, look for life in the solar system, or we look for oxygen as a biosignature on other planets, right? So, but if you think about the size of chemical space, like the number and diversity of molecules possible, it's exponentially huge, even for small molecule chemistry. So, so it's realistic to say if you think of life as a general process and not a chemistry of life on Earth specific process, or a technology of life on Earth specific process. If you think of it as a general process, if you have geochemistry on a planet and you're exploring this huge combinatorially diverse space, already at the level of chemistry, you should see some divergence between what chemistry you see as being biological on one planet and what you see on another. And that will form some kind of statistical scaffold that then you would expect the evolutionary trajectories to be completely different on those planets. And if you think about the space of all possible technologies, it's even exponentially larger than the space of all possible chemistries. So to think realistically that there's going to be some convergence in technology is, I think, really premature. So I made the joke about economics, but money is obviously like something that was invented on Earth. It's not a physical thing. It's an abstraction that our civilization invented, which happens to work very well. Might be that the only planet that has economics is our planet, because it's just so unique to our particular space and our particular trajectory of evolution through the space of what's possible. So I think we have to take those things into consideration when we're thinking about, what are we going to see out there and how can we build general models, which was the points that were already raised.
Yeah, Sarah, we've just seen a recent example of getting into trouble that way with the phosphine announcement.
Yes.
The Venus, where the original authors actually went so far as to say that they had explored all chemical space, and there was no way to make that phosphine without some biological component. And that's just such a difficult thing to.
I think that way of pursuing the life detection problem is an impossible uphill battle, because I don't think you can rule out every other explanation besides life. I think you have to have an explanation that it is life, and then you have a real hypothesis that you're testing, and it's sort of so yeah, I think but part of the reason I would make that argument is because of the combinatorial space that life exists in. Life is chemical for a reason. It exists in this high dimensional space that's very hard to navigate through, which is why life requires information to do it. And that information is specific to the molecular architecture it has. It's a good example.
I want to, since we are thinking far out in the cosmos, but trying to make our speculations, our cosmic speculations, bear on life on Earth here, I'm going to ask the three of you to suppose that we do make contact and we do have some cultural exchange with another civilization, and it is semantically legible by some miracle. And that this civilization is likely an older civilization. I know that there's been some deserved criticism of the notion that these cosmic others would be like gods dispensing wisdom to humankind, but suspending that criticism for just a moment, what question would you ask them if you only had one and you were hoping that their answer could improve our prospects here on Earth?
Well, you need to watch the movie, right? Because that question is in there. It's how did you survive your technological adolescence? How did you make it through?
It feels like a big question to just come up with an answer on the spot, but
we only got one question, so I'll make it a big one.
My kind of off the cuff answer would just be, how common is life and how common is technological life? Okay, maybe a two-part question. But I think that from that, you can infer a lot about the difficulty of evolving and surviving as a technological civilization.
I would ask, how does it feel to be you?
Alien qualia. Love it. Before we get to some audience questions, suppose we never find intelligent life, or we have good reasons to know that there is no one else, or that simply that civilizations are just too widely spaced in the cosmos. They're like one every 100 galaxies, and we have no hope of ever kind of coming into causal contact with them. Given y'all's choice of profession, I'm sure that would come as a disappointment. It would come as a disappointment to me, I'll say. But how would it make you think differently, if at all, about our human existence?
I keep going first. It would make me really, really take seriously how important we are and how we shouldn't mess this up, right? If we're a rare example of an intelligent species, then we owe it to the cosmos to stick around and not do ourselves in.
So I finally gave myself a more optimistic technical argument that's kind of in the vein of what Jill is saying, actually, which is, if cosmologists like to count the number of degrees of freedom in the universe, right? And so we know the universe started in a low entropy state. And then if you actually could count like how much was happening on this planet as a very unique planet, I think it would probably outweigh everything else we can observe in the rest of the cosmos, just because of the chemical diversity, biological diversity, technological diversity on this planet, right? So in some sense, more is happening on this planet than what we know of is happening in the rest of the universe combined combinatorially. And so, so if you buy these arguments about sort of life being this creative process that is actually generating complexity in the universe or generating more novelty, then then that process is really happening here. And it indicates that there's sort of a long technological future for our planet because it's an explosive amount of creativity and things happening in our long-term future. So, so I guess it kind of at least gives me hope that the technological future on Earth is long and bright. If we're the only one. And so I guess that's kind of a little maybe too cosmological for most people's taste, but I think it's actually really important to think about our place on that scale. And I think, you know, my other sort of opinion, which is probably more controversial, is I think most of our cosmological models are failing because they don't account for the physics of technology. And so the long-term future is maybe quite different if you take that into account.
Hmm.
Yeah, I think the optimistic take on this is exactly what Sarah said, that if life is really that rare, then we're in the most interesting place in the universe or in every 100 galaxies. And we're here, we can take advantage of that. We can understand these really rare states of biology and chemistry, physics you couldn't observe anywhere else in our galaxy. And that's kind of cool. And I think from another standpoint, and maybe this is my physics brain, but I would be so curious if we were able to make that determination, like what's going on in the rest of the galaxy then? If it's not life, what is it? And does it just mean that the solar system is really just this perfect special place to be? What makes it so special? I think it would really change our astronomical understanding as well of like the context of planet formation, of star formation, of galactic evolution in really interesting ways. And so I don't know if that's quite as interesting as the implications for kind of the future of humanity, but I think it's kind of fun to think about.
So Sarah, I'd like to pick your brains on synthetic biology for a second. I used to say that we'll never be able to understand what is necessary versus what is just contingent in terms of biology, the biology of life as we know it, until we find a second genesis, another biology. But then people have been arguing with me that say, no, you know, we're getting somewhere with synthetic biology, and we may actually be able to answer that question, necessary versus contingent. And are there other ways to make life?
So I think it depends on what you qualify as synthetic biology. So I think sort of current synthetic biology, where we're trying to build cells from known parts, is actually just an extension of known life. So that goes into the contingency issue. And so is technology. So this is actually a big problem in the origin of life field. It's really hard for us to remove our agency and our timeline from the experiments we design. And so in my mind, anything we build is actually an example of life. That's part of the same example of life we are. Because of that, you know, we had to evolve and form on this planet before we actually designed experiments that we're now trying to test principles of life. And so those experiments we're doing are actually examples of life too. But I do think it's possible to reduce the amount of information that you put into an experiment and basically control for how much information you put in, and then try to evolve synthetic life from scratch, which would have controlled sets of contingencies that you put in the initial part of the experiment, and then you can actually see how much physics generates for free without you actually designing it yourself. Because we are physical systems and we are designing physical experiments, so we're putting the design in. We need to actually remove as much of our agency and our information as possible, and then watch that process happen. So I do think it's possible to happen on Earth, to remove the contingency of our evolution, but we have to be very careful about how we talk about it and how we design the experiments.
Okay.
Okay, I think Jonathan is going to join us with some questions from the audience.
Yes, thank you, Ross, and thank you to the panelists. We have a few questions, and we still are inviting more if anyone would like to add them to the Q&A panel. But we're going to start with Mike Antares, who has asked a rather broad question, which I think could lead to some good conversation. What are some of your favorite thought experiments or questions when it comes to potential contact with life beyond Earth?
Okay, let me jump in again. I've been struggling with some talks that we've been having at the SETI Institute. We used to say that mathematics would be the means by which we could communicate with another intelligent technology. But that's not so clear to me now, because at least the way we express mathematics apparently is determined by the structure of our brain. And that it's possible that indeed another technological or intelligent civilization might have mathematics, and they might be expressing the same kinds of things that we're talking about, but we wouldn't recognize it as such because their mathematics would be so different from ours, because their brains are differently structured.
Anyone else have any thought experiments?
Well, I might not answer the question directly, but Jill brought up my favorite example of thinking about physics of life, because I actually have a very similar view that mathematics is not universal because it's an invention of human minds. And part of the reason we think it's so powerful at describing the physical world is because we can communicate it so effectively. And also we can communicate it between us and our technology. So it's like this particular kind of information that's easy to propagate in our biosphere and easy to retain its properties and its meaning. And so I think actually when you invert these sort of canonical biosignatures, like we always thought math was gonna, it would be the same math we have, or it would be the same molecules we have. And then you ask questions about what does that look like from the outside? And how should I think about those things if they were being generated by a general physical process? I think we start to get some real insight. So my set of thought experiments I do on mathematics is to do what I call a physics of theoretical physicists, which is like, if you're asking questions about what does theoretical physics look like generally, I think you start to get new ideas about how to think about that problem. And what it might look like on other planets, even if it doesn't look like what we look like at all. Which is again going back to this idea that we need to be able to recognize the unknown physics of us. But I don't know in full detail what all those signatures look like. We have one sort of candidate from some work that we're doing on physics of life, which we call assembly theory, which is trying to get at the idea of detecting complexity, particularly in molecules, as a biosignature. And the idea there is like, if you take a molecule and you break it in half again and break it in half again and break it in half again, you basically build this giant tree-like structures of all the ways of assembling the molecule. And if the shortest path in that space is sufficiently long, it suggests you need an information processing system to build it, because random exploration of that combinatorial space would never get you to this one specific complex molecule in high abundance that you would actually ever observe it. And we think the same thing for technology. So there's some people don't think about molecules as technosignatures, but there's some molecules like Taxol that are so complex that you would never expect anything but an intelligent civilization to be able to produce them. So I think if you just think in chemical space, like there's these boundaries that only living physics can cross. And then when it achieves what we call sufficient intelligence for technology, there's certain molecules that can only be produced then you start to kind of see, what the physics of life constructing this possibility space and actually making these things that you would never expect to see otherwise looks like.
Sophia, do you have a thought experiment for us as well? I mean, it seems like we started with a thought experiment that in a sense, that's what the Fermi paradox is. It's one way of looking at it. What would you pose as a thought experiment?
Sure. So I don't know if this is quite a thought experiment, but something I've been thinking a lot about lately is I recently published a paper about the signal that was investigated by the Breakthrough Listening Group that we were calling BLC1. And it was something that looked a lot like what we would expect a radio signal from space, from an extraterrestrial intelligence to look like. And it took a lot of work, almost a year of my professional life, to track down what was causing it. And in the end, we can attribute it to human technology. So not an alien signal after all. But that process was long and it was slow and it was complicated and it required us to develop new methods. And I think the case study of phosphine on Venus, that purported detection, is also a great example of maybe what might be sort of a spicy take, which is that first contact will probably be boring. In that for us to find and verify extraterrestrial life, be it kind of microbial or intelligent, is going to take years and years and years and dedicated instruments and time and back and forth in the literature and extremely detailed statistical analyses and things that just aren't particularly interesting to the average person. And it'll take us a long time to come to a consensus if we ever do. And that the information that we get from that process will take a long time to parse in a way that is not quite like the UFOs landing on the White House lawn sort of view of first contact. And so, especially with this kind of latest investigation that I did, it's a reminder that science is long and complicated and easy answers aren't always going to be there. And so what will our reaction to that sort of first contact scenario that is complicated and ambiguous and boring look like might be an interesting thought experiment on its own.
Ross, you're writing a book about the Fermi paradox from what I understand, and wondering, well, first of all, is that true? And if it is, maybe you would like to announce it to all who are listening. I'm sure will be avid readers, but also in light of that, what would you see as a thought experiment that might be of interest given this context?
Yes, thank you for giving me a sort of free moment here to plug my book, which is not about the Fermi paradox, and in which I hope to actually go the length of its 300 pages or whatever without actually mentioning the Fermi paradox. It is tentatively titled The Long Search, and that's based on the idea that it's about the search for extraterrestrial intelligence. And it's, my sense, which I suspect is shared by many here today, is that that search is going to be with us for a very long time. Not because it won't be successful, but because it's going to be an area of interest for humanity as long as humanity is around, and that we sort of live right at the dawn of it, and that this is kind of as such, a moment worth recording in some kind of literary and philosophical detail. And so in terms of a thought experiment, one thing that, if you'll allow me to sort of steal the microphone, the question asking microphone back, and put a question to our panelists. Given that we all arrived here promising to discuss the Great Filter, but skipped right over it because we don't buy the underlying Fermi paradox, I wonder if I might ask our panelists to assume the Fermi paradox is interesting and valid for a moment, and that the Great Filter is a compelling way of thinking about it, of some of the explanations for it. And famously, people who have kicked around the Great Filter have said that, the filter could be in our past, which is to say it could be the origin of life or sexual reproduction or the Cambrian explosion, or it could be in our future, which is to say that we are kind of bumbling towards some existential risk that is in our blind spot. And I wondered if our panelists, if they would indulge me by entertaining the Fermi paradox, if only briefly, could tell us whether they think a filter would be in the past or the future, and which one would strike them as most likely.
I always think it's probably at the origin of life itself, because I think once life gets going, there's some explanation for why it's done the things it has. But I tend to think about that transition as sort of, like NP hard in a computational sense. It's actually really hard to calculate what the probability of transitioning from non-living to living matter is, because it's actually transition in the physics. It's a little bit like the quantum to classical transition, and identifying that sort of exact boundary is quite hard. So I think that event is actually the hardest one to constrain, because the rest of it at least from my perspective, and obviously I have kind of a very biased perspective being a theoretical physicist and looking for universal principles, I think the rest of life is kind of explained by the same principles. What you want to know is, why does that physics take over in the first place? And I think that transition is quite hard.
Are you, in holding that position, are you troubled at all by the fact that life appears to have gotten jump-started relatively quickly on this planet?
No, it doesn't bother me at all, because that's an artifact of post-selection. So, I mean, in people that do proper probabilistic assessments of the origin of life probability based on the fact that we would have to be here, like we are contingent on that event, right? So if you post-select on the fact that we wouldn't be here without an original life event, you actually can make arguments it's very probable or very rare based on the fact it's super quick. So you can get very super quick transitions if you post-select on them very easily, which means you already have the end state. If you have the end state, it's easy to say something happened fast.
And Sarah, isn't it correct that if it takes a long time to go from microbial to mathematicians, then we couldn't be here unless life had started very quickly?
Right. But yes, that's exactly right. But if you think of it as an entire distribution of possible values for the original life event, right? Like, and how quick it is, and you make your argument, you're already selecting on some tail of the distribution, right? That is the one that happened fast. And if we only have one example, we don't know if it's closely distributed there, or that is some very rare tail of the distribution. There'd be no way of assessing. And so that's sort of how that's built into these probabilistic arguments.
Well, we are at the end of the hour here, and a fascinating panel, which actually has teed up in some very interesting ways where we are going next. But I'm going to turn this back over to Bill for a moment, since he is bridging us from one section to the next.
Great. Well, thank you, Jonathan. And I mean, what a inspiring discussion. Fantastic. Sarah and Jill and Sophia and Ross, that was wonderful. Ross, since you're an obvious fan of our work and support personally, you know, the long-term prospects and the long-term ongoing need for this kind of work, then we'll promote your book at the Institute, and you can promote the Institute in the Atlantic, and that would be a really symbiotic relationship. So in any case, really fantastic. And, you know, we could continue this part of the conversation all day, just like the other panelists. Absolutely inspiring. At this point, we're going to transition over to another conversation that's going to be led by Jonathan to discuss the Library of the Great Silence and all that it implies. So Jonathan, I'm going to turn it over to you for the next 30 minutes, and then we will wind up with Habitability at Home Redux, which will be 4 p.m. Eastern and 1 p.m. Pacific time. So Jonathan?
Great. Well, thank you very much, Bill. And as I said a moment ago, it certainly is auspicious, all that has been discussed in the past several panels, but especially this most recent one, in terms of the subject that I'm hoping to bring up in the spirit of a workshop. And the origin of this was, in fact, well, the origin of the conference that you're all attending coincides with a project that I'm referring to as the Library of the Great Silence. And it's a project that I have been developing as a SETI artist in residence, and that I gave a SETI live talk with Seth Shostak, who has been the scientific advisor on the library, which was a conversation that our own Dagmar de Groot heard and led to a conversation with him in which we started to consider some of the questions that came out of the library that I'll describe to you in a moment, and that ultimately led to this framing that we have taken for some of the crises that we are facing in our society today. That is to say that we can potentially use habitability as a window into climate crisis and vice versa. So what I'm going to do is I'm going to attempt to share my screen here, and I am going to go through a quick introduction to the Library of the Great Silence, and then I'm going to, as best we can do, given that there's really no possibility for true conversation here, I'm going to try to open this up to conversation. So bear with me while I attempt to share my screen with far too many windows open all at once. And I will then go on from there. So I think that I'm sharing screen, but it looks like the Q&A window is still popping up. Is that still in the corner? Can anyone tell me?
No, you're just seeing your screen, John.
Great, perfect. So I'm going to take a step back for those of you in the audience who don't know the history of the Fermi paradox, which has been thoroughly attacked in the previous session, but which I would like to bring back around for the sake of a conversation that I think can lead us into some interesting territory, even if it does not persuade many in the room that there is a paradox in the first place. So the Fermi paradox came about allegedly in 1950 when Enrico Fermi was having lunch with some colleagues, and they were talking about how the universe must be teeming with extraterrestrial intelligence. And Fermi famously said, well, where is everybody? And so, of course, this question was a little bit disturbing to the common assumptions of the time. That is to say that people assumed that any alien intelligence would probably be much like us, sending out signals, I love Lucy and all that, and probably also would have some sort of itch to go and to visit other planets. So as a result of the fact that no little green men were visiting, and also that we weren't hearing anything, this Fermi paradox came to be known as the Great Silence. And there are, as the previous panel has alluded to, and as many of you know, there are many explanations for the Great Silence. And they range from the fact that we, in fact, are alone, that the universe is not teeming with intelligent life, or maybe there's no life at all. It's also possible that when intelligence gets intelligent about being intelligent, that life forms stop watching I Love Lucy, and perhaps they don't need to take space shuttles and spaceships to be able to get around. In other words, it may just be that there's a short period where everything becomes obvious and then it no longer is. But the great filter is, to me, the most interesting of these hypotheses, not because it is any more plausible, after all, we have a sample size of 1 at this stage, but because it is potentially the most generative, and generative in a way that we're hoping as co-organizers of this conference will be more broadly. What I mean is that when we posit that there is some stage in a civilization where it gets to a level of complexity that it is likely to be apparent to other civilizations elsewhere in the universe, that level of complexity results in some event that is self-annihilating. This is deeply disturbing, existentially so, and certainly makes a lot of sense given that the Great Filter comes about historically within the context of the Cold War, and that we're talking about it today in the context of mass extinction and of climate change. But more broadly, it seems interesting because whether or not it is true, and whether or not there is any paradox at all inherent in the fact that we have not had any contact, nevertheless, it brings us into a framing of ourselves and our civilization that I think can help us to understand ourselves better. So the Library of the Great Silence is effectively an interstellar reference library. And the interstellar reference library is intended for all beings anywhere in the universe to be able to share filtration events that they maybe have gotten by, because it seems that more likely than not, if there is a great filter, there probably is more than one. And it probably, therefore, would be helpful to any civilization anywhere to be able to share notes with others in terms of great filters that have been circumvented or surpassed. So the Library of the Great Silence is a space in which to be able to consider these transitions that potentially are self-annihilating, and to do so in the most open-ended way possible. By open-ended, that means that it is a library that is open to all beings everywhere. But at the same time, it means that for the beings who are likely to use that library in the short term, namely us, that it is universal to the extent that we are capable of thinking of universals, and that can potentially, even if it's only us in the library, can lead us into a new space, a new mental space. So when I said universal, I mean, we're not only using English here. I mean, we're not only using language. In fact, the library is not a library of books, but is a library of things. And I've started to assemble some of the objects that will be a part of this library. And ultimately, over the course of this conversation, we're going to start to look at these objects as well as to nominate others that belong in the library. So the objects that I've selected, largely on the basis of the fact that I had them at hand, begin with the hand axe, an implement that goes back to Paleolithic times, and that was one of the first artifacts that really did transform the world that humans, or that hominids were living in. The library is intended to have as broad a range as possible, and to have objects that instantiate various transitions in ways that are going to be necessarily incomplete, but that nevertheless, because they are just things, because they are objects rather than words, that they can be studied without prior assumptions, or with fewer prior assumptions at least than would be needed if we were to be looking at books in English or any other language. So we have, for instance, fire as instantiated here in matches. We have gold, which has had a profound effect, not as an element, but in terms of how we've used it, in terms of how civilizations have come into power dynamics with each other. We have, of course, a very familiar object from here today, the face mask. And we have many more that I don't have represented here that range from substances, coal, fertilizer, trinitite, silicon, plastics. We also have, in the way of materials, dice, which have, through chance and the way in which they've operationalized chance and gambling, really have transformed society in various ways, arguably. The compass, the clock, pen and ink. I don't want to give too many examples because I want to open this up in a moment to bring others into this discussion about what the transitional objects are. But first, I want to say a little bit about how the library is intended to be used. And of course, this, like everything in the case of a library that's meant to be open to all beings throughout the universe, is somewhat of a guess as a starting point, and a guess that is meant merely as a gesture in the direction of co-discovery of what will probably be a much more interesting proposition going forward, a library that will be much more effective going forward. But at present, what we're looking at in terms of this library are these objects and ways in which beings throughout the universe, probably first humans, will be able to come together and to manipulate these objects in order to be able to consider transitional events and their relationship to one another and who and what we are, where we are today. So in other words, it becomes a way in which wordlessly, setting aside all the assumptions that are latent in English or in our language more broadly, it becomes a way in which to interact, for people to come together around existential questions that we are all facing, that we have faced, that we may face. And so simple machines, this idea that comes from the Renaissance that it's not exactly true, but it's useful once again, that there are elements to all machines and that they include the lever, the pulley, the screw. The idea is that these simple machines can be used as a way in which to express relationships based solely on physics, and that also geometric relationships can be inscribed in a library space where nesting and various other phenomena can be expressed. The idea is to get us outside of our assumptions, to get us into a space that is shared where none of us have an advantage, where none of us can go based on previous instincts on what our received wisdom might happen to be, in order to be able to open up a whole set of questions that we're all asking already, but that we're asking in ways that, in a sense, we're conditioned by our past. So the library is intended to be everywhere. And I started out here in Abruzzo, a region in Italy, where I just happened upon a temple that had been dedicated to Jupiter, that then fell into ruin and became a Catholic church that later was deconsecrated and is now once again falling to ruin. A space of transition that is like the transitional objects, a space in which potentially we can reflect on these sorts of events that are apparently how we become what we are, and therefore have embedded in them all sorts of phenomena, such as overreach potentially, or more benignly cooperation. Cooperation, in fact, being one that we would like to figure out how we might better be able to promote. So this first branch was installed quite simply in Abruzzo, in this space, and is a sort of a prototype for what can be throughout the world done as a sort of set of libraries that each community is able to form on their own, that each community is able to come up with in terms of what objects belong and where those objects ought to be. And I'm currently working with a space at a university in Budapest on one of these, and I'm looking at a space also in San Francisco. But we're ultimately also looking ambitiously at a headquarters. The headquarters being at a place that will be familiar to many of you, which is the Allen Telescope Array on Mount Lassen. Probably the ultimate tourist attraction if you're an extraterrestrial, and certainly I've just been there recently, a great place to go, even if you're from Earth itself. And we'll be able to bring these objects into this space to be able to interact with in the present, and also ideally through deep time, whether it's us, other beings that replace us, other beings that come from elsewhere, if in fact there are beings from elsewhere in the universe. So now I'm going to open up to discussion and to especially to nomination, because I believe that the nomination process itself is going to be one of the most crucial in terms of how we get into the sort of conversation that I personally believe we all need to have about who and what we are and what we need to become. That this is through SETI as a framing, a form of applied SETI, that is through the lens that I come from, which is as an experimental philosopher and artist, a way in which to get us outside of ourselves and a way in which to reframe everything. So I'm going to end the presentation here, and I am going to attempt to use the comments and Q&A as best I can. It's a little bit challenging because I'm kind of here alone at the moment, but if anybody would like to put into, let's go ahead and use chat for the sake of simplicity so that I'm not looking at two places. And if anyone would like to perhaps take on the role of speaking for those who are, well, ironically silenced by the fact that we are in a Zoom seminar. Maybe Bettina, would you be willing to take on that role?
Yeah, absolutely. I'd be happy to.
So
right.
This is an experiment.
Jonathan, do you want to stop sharing your screen? And
oh, I'm sorry.
That's okay.
Where does that happen? I've just lost. Stop
Be at
share.
the top. There you go.
There we go. So this is an experiment, and we're just right now looking for what goes into the library and why.
So would you like me to make a suggestion?
Sure, why don't you get us started?
I'll get us started. I think what would be really interesting is a string of a musical instrument, because I'm thinking about how humanity started with art. You know, we have evidence of art making that is visual. I'm imagining that there may be art making that was more sound-based. And I like the idea of a string because it is also mathematical, it's also frequency. So we've got that nice intersection between art and science.
No, I really like that. And I really like also what it suggests in terms of having an evolution, or at least what we perceive as being our own evolution in any given sector. So whether it's musical instruments or forms of energy ranging from coal to solar and beyond, it seems like that could be a really interesting way in which to organize such a library.
Yeah, and that reminds me of something. I think in the first panel, Michael Wong was talking about how technologies is sort of creating this global village and connecting all of us. I think art is doing the same thing and has always done that and has always connected us to ourselves and to others. So I think an artistic aspect should play a big role in the library. And if you have, I'm going to just go and keep an eye on the Q&A and the chat as well, if anybody else has any suggestions.
Let's put Mike Wall on the spot. Mike has actually written about the Library of the Great Silence already for space.com, and therefore he's done more thinking about this than many. Mike, would you perhaps like to suggest some nomination?
Just in terms of what objects to put in there?
Yeah, what belongs in the Library of the Great Silence? It's a conversation that I've undertaken in Abruzzo with people who were living in this town that was decimated by an earthquake, and then quite recently. And so that earthquake loomed large. So I'm very interested in both a very local, you're in San Francisco, what comes from San Francisco, but also in the global, or if you've been on other planets, and I know that space.com takes us all sorts of places, that would be welcome as well.
Well, something that just came to mind just a second ago. I mean, you're talking about it being like a repository of transition. I mean, what about something that memorializes how we mark passages of our own dead, like something ceremonial? Could put like a sarcophagus from the ancient Egyptians in there, or an urn, or something that speaks to us as a species, how we mark passages. I mean, maybe that's too meta, but I mean, if you're looking for a document of transition, I mean, how we mark our own transition to the afterlife might be interesting.
We're already getting very meta because we are going to include one of the feeds from the telescope array at the Allen Telescope Array. So SETI itself seems like it's a very relevant.
Yeah.
How would you interpret that if you were a being from elsewhere in the universe, and how might that help to define which of these objects makes the most sense? Is it human remains? Is it the treatment of human remains?
Yeah,
I mean, get to that.
It would probably be human remains. I mean, maybe something. I mean, maybe cremains, and maybe that would tell them a little bit about how we're constructed if they want to analyze what the bones are made of or the chunks are made of and so on, but also how they're venerated. There's a lot of cultural information in there too, right? So, I mean, like, I don't know. I think it's just worth, because that's something that makes us, I mean, it doesn't make us human because, no, I mean, elephants mourn their dead and so on. There's not something that singles us out, but it is a big part of us. And it was a big part of our transition in terms of our culture. And so, yeah, that just struck me. But yeah, I mean, and there are different layers of information in something like that. So.
Bettina, I'm sorry, but Bettina, are there others? I'm not watching chat here, so.
No, don't watch it. I'll watch a chat for you. I really like this. Lucy Victorious says, I would like to nominate a self-portrait of Rembrandt by Rembrandt as an example of artists who had the capacity to immortalize themselves visually, which kind of really beautifully dovetails with Michael what was said. But I also like the idea of that selfie. That kind of tends to permeate the centuries and our need to look at ourselves and us as individuals. And you have that beautiful tension between the local and the universal as part of that library of the great silence. So maybe you can respond to the idea of the artistic selfie, the self-portrait.
No, it's very interesting. I think what we need really is to go all the way back to those handprints that are found in prehistoric caves, which seem in a way to be the first selfie, and to go from there all the way up into the present. There's no shortage of selfies today. Are you seeing other?
And I'm seeing more from a viewer on YouTube. I nominate the vacuum triode tube and also transistor, a major transition in communication and task accomplishment from Peter.
So it's really interesting to think about, what are the technologies, not only because of the fact that they are, of course, transitional, but because of when we hold a mirror to ourselves, as Rembrandt did, but where we're doing so as a society, what it is that we see as being, what are we going to boast to mom about, in a sense. So it seems that almost in a way, everything that we're doing right now or could do in a library of the great silence is a form of Rembrandt's self-portrait, only writ large at a societal level. So it's a really interesting thing to look at those technologies and to look at them from afar. And I think that more broadly, what we've been doing so far in this conference and what we're hoping to do going forward is to be able to take that outside view to see ourselves from a very different vantage.
Jonathan, I was I've just raised my self-esteem in my own mind, because I actually had the same exact thoughts as Bettina. So if I'm thinking like Bettina, then I'm really feeling good about myself. But yeah, I was going to say, the vacuum tube and the transistor, and maybe the abacus before that, as critically important transitions, or representing very important transitions in human history. Also, maybe like the mud brick, which kind of represented the transition from dwellings based on natural environments and habitat like caves and forests to human-made structures, which was another, like the hand axe that you showed early on, where was a transformative point in human history to actually build our own dwellings. So, but so many wonderful ideas.
Yeah, and I'm right now in Tucson, which is a place of adobes and an abundance of bricks. I'm just going to maybe ask, as I see that Alice Gorman has joined us, and Alice is a space archaeologist who brings also a great perspective in terms of the deep time in Australia. Alice, do you have any thoughts for us as you're waking up for what belongs in the Library of the Great Silence? And Alice and I are going to be running a workshop at Flinders University next year. So it is apt, perhaps, that she have the last word before we turn it over to Bill and go on to the next panel.
Well, I wasn't expecting to have to comment in this panel, but perhaps something that is indicative, an object that is mass-produced, decays easily, and will become part of the silence. And my favorite objects in this line are Ziploc bags and plastic cable ties. So they're ubiquitous on Earth. They represent something iconic about the contemporary era, and they are also very fragile and will decay into the silence that we're looking for or looking at.
That is a perfect way in which to round this up and to ask all of you to continue to put into chat any nominations that you have, or to get in touch with us. And we will continue to build this library, branches all around the world, and watch this space or watch ATA for the headquarters that we hope will be coming soon, and that we will be able to invite you all to visit. Thank you.
Jonathan, do you have a website for the Library of the Great Silence that people could visit, or a way to communicate through that website to you?
Yes, in fact, you, Bill, have a website, a web page. The SETI Institute has one, and
for you,
we will put this into chat if we can find it.
I think Rebecca can do that. So it would be good to put that in the chat. And with that, we're right at the top of the hour and moving right along. And thank you. That was really fascinating. It's a wonderful project, inspirational again, and a good segue into our final panel discussion of the day, which quite fittingly is habitability at home redux. And I think that Dagmar is once again going to kick us off for this discussion, which should tie up in a nice, neat little bow all the amazing different perspectives that have been shared with us today. So Dagmar?
Yeah, absolutely. So this is Habitability at Home, once again, Redux. And it's so exciting to be joined by some panelists whom I have just tremendous respect for. And the next video will be moderated by Dava Sobel, one of my favorite authors. So here we go.
The search for life beyond Earth is surely one of humanity's greatest undertakings. And if the forecasts of scientists are credible, that search will likely be rewarded within the lifetimes of those of you in attendance today. Try to imagine the tremendous impact of someday learning that biology is a commonplace in the cosmos. Even where we stand now, astrobiology studies have already taught us much that is relevant to our home planet. For example, Earth's nearby sister, Venus, has shown how greenhouse warming can turn a promising young world into an inhospitable inferno. The desolation of Mars holds a different lesson. As we investigate ways to terraform the red planet to our liking, we will gain insights that may guide us in geoengineering our own atmosphere to impede climate change. Just as your English teachers once asked you to contrast and compare the work of different authors, you will be able to contrast and compare different worlds, and not just within our own solar system, but also among the planets of other stars. New telescopes will bring those distant exoplanets into your purview, letting you see the results of nature's experiments on all of the trillion or so planets in the Milky Way. In its narrowest definition, habitability means an environment that can support life. Studies of life on Earth have exposed the stunning variety of forms and circumstances in which biology can thrive. Terrestrial life can adapt to the most severe conditions imaginable, from noxious gases to extremes of heat or cold, and even intense radiation. The solutions that Earth's extremophiles have devised for their own survival may very well prepare us to face future threats anywhere in the solar system. As we move forward into that future, we will continue to follow the science.
Welcome to the final panel of this fascinating day. I hope you've enjoyed the conversations that have been going on here. I certainly have. I'm Alexandra Witze. I'm a science journalist based in Colorado on the traditional and unceded lands of the Ute, Cheyenne, and Arapaho peoples. I've written about Earth and astronomy topics throughout my career, and most recently as a correspondent for Nature. Our purpose here at the end of the day is to turn our gaze back onto planet Earth and talk about how lessons from this interplanetary context that we've been talking about so far can inform the climate crisis that we find ourselves in today. Now, what we're facing with anthropogenic climate change, as you know, isn't like anything we've experienced in our history, or as far as we know, that other civilizations have faced on other planets, although who knows. So our remit here is to talk about how those cosmic perspectives can illuminate this challenge. Please put your questions in the Q&A box, not the chat, and we'll take those towards the end of the hour as we've been doing throughout the day. We've got an all-star panel for you here today, so let me introduce them. Alice Gorman is a space archaeologist at Flinders University in Adelaide, Australia. She's an expert on space heritage and space history, and you probably know her on Twitter as Dr. Space Junk. Victoria Herman, who we are trying to get online at the moment, is a climate change researcher and policy expert who's on sabbatical as president of the Arctic Institute in Washington, D.C. We hope she'll be here soon. She's worked on climate impacts in communities in the Arctic, across North America and in Fiji, including innovative projects looking at coastal impacts in America as a National Geographic explorer. And David Grinspoon is an astrobiologist at the Planetary Science Institute, former chair of astrobiology at the Library of Congress, and the author of Earth in Human Hands, among other books. So let's go to some opening thoughts from our panelists on bringing this vision back down to Earth, considering the climate emergency that we find ourselves in. I want to ask our panelists to talk a little bit about what their research tells them. What does your research say about the habitability of our planet today and how habitable the planet may be in the future, especially given what we're pummeling it with, unlike any other planet? So let's start with Alice, if we could. You're muted.
Unmuted. I'd like to start by acknowledging that I'm talking to you today from the lands of the Kaurna people of the Adelaide Plains, and I extend my respects to their elders, past and present, and acknowledge their connections to earth, sky, and sea country. And I would also like to extend my respect to the traditional owners of any of the lands that the audience and panel are joining us from today. So I'm a space archaeologist, so I wanted to take a bit of an archaeological perspective on this, relating to some of my recent work, particularly around off-Earth mining. So 3.3 million years ago, hominid ancestors made stone tools at the site of Lomekwi in Kenya. And from that time onwards, hominids on Earth have been digging stone and minerals out of it. The oldest actual mine that we know of is at Ngema in Southern Africa. And more than 40,000 years ago at this location, hematite was mined for access to pigments. And later on, this ore was actually used to extract iron itself. And so now we have an Earth that is covered in mines, some of them enormous, like the Garzweiler mine in Germany, which is 48 square kilometers across, and the Bingham Canyon mine in Utah, which is 4.5 kilometers wide and 1.2 kilometers deep. Until the 1950s, probably you could have said that the Earth was in an aggrading phase. So minerals and elements were being moved around within it. And there was an estimated 40,000 tons of cosmic material that arrived on Earth every year. So we're gradually building up our mass. This changed in the era that archaeologists call the contemporary past, which is basically World War II and afterwards. So in archaeological terms, the contemporary past is radically different to the eras that went before. It's characterized by mass production, consumption, and discard, like my favorite cable ties and Ziploc plastic bags, and also radioactivity and nuclear signals. If you take a longer term view, we've moved from an aggrading phase into an eroding or degrading phase. Because now in the space age, we're actually taking minerals and elements of Earth off planet and putting them into space on other planets and moons. So there's approximately 8,000 tons of material currently in Earth orbit. And on the moon, there's about 187,000 kilograms of human material. And that number is set to radically increase as commercial enterprises are encouraged to go to the moon. And there's also a smattering of material on Mars and Venus and in the asteroid belt. And we know that the moon is going to undergo radical transformation, probably sometime in the next decade. So for me, what this means is that humans have begun dismantling the solar system. So for some people, such as Elon Musk, this is a promising beginning of humans becoming a multiplanetary species. Or you could perhaps look at it as as leapfrogging Kardashev's stage 1, where the planetary civilization uses all the energy resources of the one planet, and then heading straight into stage 2, where you're starting to utilize the energy of an entire solar system. In some far future scenarios, entire planets are dismantled to engineer massive structures at the solar system scale, like Robert Bradbury's Matryoshka brains. So in a sense, we've actually started this process already. We have artificial rings of debris which encircle the Earth, and you could perhaps 3 million years in the future liken these to the flakes of stone that have been left at the site of Lamekwi in Kenya. So that's it from me.
Thank you, Alice. It's a fascinating perspective on resources, sort of, yeah, not just extracting within the planet, but also how that moves outward from into this closer space near to Earth. Thank you for that. Victoria, I think you've managed to join us. Are you able to unmute and give us your initial thoughts?
Yeah, thank you so much. I think to your question on the habitability of Earth today and moving forward, for me, it's a question of what and how do we define habitability? Will humans live on Earth? Yes. What type of life will they be able to lead? Will we be able to hold close our identities? Will we be able to practice our cultural heritage? For many communities, and especially Indigenous communities reaching back from time immemorial, those questions are a bigger question mark for me of, is this future planet Earth habitable? And I also think there's a part that includes geography. What parts of planet Earth will be habitable? We already see that our Earth's landscapes, our maps, both political and cultural, are changing because of climate change. How will those continue to change? What lands, sovereign lands, cultural landscapes, spiritual landscapes will we lose, not in this long, far off future, but in 2021, in 2022, for communities in the Arctic, in the South Pacific, along American, US and US territory coastlines, where much of my work is. I'd love to hear other panelists' thoughts on what their definition of habitability is, and how we find some type of common definition so we can move forward on ensuring that this planet Earth that we all share is habitable, to kind of that utmost degree that is not just livable, but is truly habitable.
That's great perspective. Thank you so much, Victoria. And we'll come back to that circle back to that question of defining habitability versus livability versus some other ability, which I think is a great distinction to make. And then over to David.
All right, good afternoon. And thank you so much for including me in this really interesting program. I've just been riveted by the panels so far. I study comparative climate evolution of Earth-like planets, focusing on how they can gain and lose habitability. And yes, we should circle back to that excellent question of what exactly we mean by that term. And I've had a long time fascination with Venus. I'm on the science team of a mission called Da Vinci that we're going to launch to Venus in 2029. I'm very excited about that. But much of my work in the last decade has been focused on Earth and applying a planetary science and astrobiology perspective to understanding the human presence and our current environmental predicaments. I was the chair of astrobiology at the Library of Congress, and the project I began there was to study the Anthropocene from the perspective of an astrobiologist. What is the Anthropocene from a planetary perspective? It's really another way of asking, what are we? My answer is that we are the first geological force to be aware of its own existence. In planetary history, this is the moment where cognitive processes have become major planetary processes. Now, this realization can be both frightening and potentially empowering. Some scientists are currently debating whether the Anthropocene should really be considered a geological epoch like the Pleistocene, or just a momentary event like an asteroid impact. I think it's kind of a silly debate because the real answer is we can't know yet. The interesting question is, what will the Anthropocene become? And it's empowering to realize that that is up to us. It will depend crucially on the difference between accidental or inadvertent planetary changes, some of which I think Alice was describing very well. The difference between that and intentional or conscious planetary changes, where our actions are guided by an awareness of consequence on a global scale. We are confronted for the first time with the existential need to find a way to act as a global entity. There are some examples of us doing this, so arguably we're learning, but arguably not quickly enough. If we, quote, solve global warming, it may mean that we've gained that ability and therefore ensured our own longevity against a whole host of other threats. This is also very relevant to SETI and the question of L in the universe, longevity, that we've been discussing today. More than any technical development, getting through our current bottleneck and achieving great longevity may require a change in worldview. And I do think that space exploration, astrobiology, and SETI can naturally promote global long-term perspectives. There are many interesting critiques of the notion of the Anthropocene. And one is that species talk is inherently problematical, that by assigning agency to humanity as a whole, you neglect issues of environmental justice and the differentiations of responsibility and agency, because humanity is not all one thing, of course. And yet there is something called humanity that is changing the planet. Both these perspectives are true. And one of the definitions of maturity is the ability to hold two seemingly contradictory ideas in your head at the same time. Humanity as an entity is something new and significant on the earth, and we have to recognize this and to come to grips with what it means. It's also true that there is no singular we. There are vast local differences and historical differences in agency and responsibility. Many of the most exciting solutions recognize both and find synergisms. There are ways to empower Indigenous communities that also help them to help themselves, help the planet. I'll stop there. Thank you.
Great. Thank you so much, David. We'll circle back to some of these much broader questions, I think, later on in our conversation. Thank you for setting the stage like that. For now, though, I think I'd like to circle back to the question that Victoria had raised. I think I'd like to get down into some of the nitty gritty about what we mean by habitability. And I want to talk in more granular detail about climate change at home, what it means to be living on a planet with climate change. And later on in the conversation, we will open up a little bit more broadly again to the interplanetary perspective. So let me throw it out to the panel. Habitability, yes. What constitutes a habitable planet? Who is it habitable for? Who is it not habitable for? Actually, Dave, do you want to pick that up first, David, since you were on that?
Yeah, I mean, we could have a long discussion about this, but briefly, when an astrobiologist says habitability, they're talking about something much broader than I think we may want to focus on in this panel. They're literally saying that some kind of life could inhabit that environment. It could just be bacteria. It could be some kind of biochemistry that could not survive on Earth. So it's related to just our broad question of are there environments that absolutely cannot support life in the universe, and are there environments that can support life, and can we differentiate between the two of them? Now, I think we would all agree when discussing Earth's environment, it's not enough to just want the Earth to be habitable in that sense, because that could easily include no human beings. It could easily include the mass extinction of almost every species on Earth today, and the Earth would still be habitable. So in a sense, that's kind of like a very low bar. I think we can set the bar higher, and we can talk about habitability for human civilizations and the maintenance and protection of a healthy biosphere with a lot of biodiversity and avoiding mass extinction. That is another sense of habitability that is perhaps more restrictive than the strictly common astrobiological use, but is very important for us to consider. And there are relations between the two. But when astrobiologists study habitability writ large, it informs us of how planetary climates change, which can inform us about how to protect that more, sort of precious habitability of our current environment here on Earth.
Yeah, great. Thank you. Alice, when you think about habitability, what context do you think about that in?
Well, being an archaeologist, I guess I sort of think of things in that context. And a huge area of study, particularly for us in Australia, is what people did during the last glacial maximum, which is about 30,000 years to about 16,000 years. So you have large parts of Earth covered in ice sheets, huge areas of tundra. In Australia, it's incredibly dry, and water accessibility is a problem. And people, adapted to that and used various technologies to survive through it. And in the common sort of discourse around this stuff, it's like things get better. Like when the climate gets warmer, vegetation changes, becomes more diverse, then life gets better. And I often think that's only because we're looking at it from this perspective, because people living through the last glacial maximum obviously thought that was normal and fine, and that's how things worked. And, came up with rich cultures and particular ways of adapting to the landscape and the conditions. And there's a sort of a common narrative that kind of says, the world went downhill when agriculture became the most common form of subsistence. And this is a process that kind of kicks us off and gets us to where we are today in the Anthropocene, as David has been discussing it. So I think it's interesting we can take this long-term perspective. And I guess when I think about that concept of habitability, there's that difference between surviving and thriving. And the standards we have for thriving now are incredibly different to what they have been at any point in the past, and seem to be kind of premised on the idea that we can continue on this kind of technological trajectory, I guess, without it falling over completely. And it seems to me that kind of future is very unlikely, that if this trajectory we're on of changing the way the Earth is, continues, maybe we will, by our standards, end up at something in a period like the last glacial maximum, where everything is different and cultures have to become, and societies have to become different, just to survive and hopefully thrive.
Great. Thanks for that, Alice. So you're talking about both the past and the future. And I wonder if, just to frame our conversation going forward, we can talk about the present a bit more. So Victoria, I'd like to ask you to talk a little bit about your work with communities on the front lines of climate change. We've had a lot of general discussions today during this symposium talking about greenhouse gas emissions in a very broad sense, looking at the planet from outside, seeing a technosignature of CO2 building up. But that's a very abstract way of looking at it. People's lives all around the world, everybody's lives are being affected, and you have been at the front lines of the communities who are most impacted. Can you talk a little bit about some of your work in some of these northern and other communities that are being so affected? How much time do we have here, and how quickly is that time running out for these communities and all of us?
Yeah, I thank you for grounding us in the present and really the everyday life-threatening reality that climate change is for millions of people across this planet. When you pose that follow-up question of what is the definition of habitability, for me, it has to be grounded in equitable habitability in order to talk about the experiences of humans, communities, countries, continents experiencing climate change today. We have to talk about equity and justice, because habitability, 1.5 degree world, a 2 degree warmer world, will still be habitable, but it won't be habitable for everyone, and life won't look the same for everyone. And we know that because that is true today. We know that the Arctic is warming at about 3 times the rate of the global average, and the 4 million people that call the Arctic home are experiencing catastrophic climate change today. It is impacting food security, not just being able to feed your family in coastal communities, but also the food that you serve. Is it nutritious? Is it the food that has been passed down from one generation to the next in a strong indigenous and traditional knowledge lineage? Will that be able to pass forward? And if not, is that future world habitable? I think we really have to position our conversation today on the heels of COP26, as it just concluded. And one of the biggest focus points in Scotland was this idea of loss and damage, of the things that go beyond adaptation. What happens when we lose things that are priceless? And that's really tied to this question of habitability. What happens when you look at a world where the communities that I work to support in Louisiana, in Alaska, in Fiji, don't have the things that are most important to them? All of that is not to say that being on the front lines of climate changes is a story of victimhood. It is a story of loss that is critically tied to questions of climate justice. But communities are strong. Communities have a vision for a resilient future, even if that future is challenged by larger countries emitting greenhouse gases. But they are powerful. And that is also a story that was brought to COP26. My work in Fiji is a great example of that. Fiji is experiencing some of the most intense climate changes on this planet, from slow onset disasters like sea level rise to sudden onset disasters like big cyclones. And while Fiji is facing a future where hundreds of villages may not be able to be physically where they are today, they might need to move from ocean communities to mountain communities, challenging your food, your identity, your culture, your transportation networks. But in the face of that, Fiji is one of the first countries that has created a national relocation guideline for communities to seek safety and are in the process of moving 61 villages further inland. They are innovating in this space. And as we move forward, I think, and I'll keep talking about this, I'm sure, in other stories in Alaska and the Gulf. But it's important to hold those two things simultaneously, that there is power and there is also constructed vulnerability from injustice past and present.
Thank you for delineating the long history that has led us to where we are today, and the different scenarios in which we all find ourselves, in which many communities find themselves coping with histories going deep into the past. Alice, can we stay on this equity and inclusion idea for a little bit here? Let's dwell on this. We talk a lot about Homo sapiens as a species during these broad conversations like we've been having today, but of course, we're a huge variety of individuals with many different backgrounds who have been influenced and brought to where we are based on, centuries of history. Alice, you've worked a lot on Indigenous issues. So talk to us about how society can face the climate challenge a little bit more equitably, if possible.
I've got a number of thoughts on this, and something I want to say first, picking up on what Victoria said, was that something that's absolutely glaring to me at this point in time is that 94% of the world's political leaders are men. And there are numerous studies which show that interest in the environment and climate change and finding solutions to that are gendered. That in general, it's seen as emasculating to be interested in environmental justice or saving the environment. So in terms of inequity, we have an incredibly huge problem right there. So we have 25%, I think, of parliamentary positions across the world are held by women. Ministerial portfolios are something even less than that, something like 13% or something like that. So the people making decisions at that global political scale in order to do something about climate change come from a group of people who, it has been proven, think that this is girly and feminine and not worth compromising their masculinity for. So in terms of equity, that is a huge problem. But I'm coming back then thinking of my own career, which has been in cultural heritage management, working with Indigenous communities in Australia. And a large part of that process has been working on environmental impact studies. And there's many people could point out the flaws in the whole environmental impact model better than me. But when I think about, again, as Victoria said, cultural identity being a huge one, if there weren't legislation and models to do this, basically everything would be destroyed and Indigenous communities would be left with no recourse at all. So as it is, there's a massive power imbalance. You have an Indigenous community up against a massively wealthy mining company, often which is supported by state or federal governments. So it's a very difficult space to have an equal voice at the table. And there's no choice but to participate in that system if they want to have any voice at all. But the system itself, you could argue, is flawed because it's small human communities and flora and fauna and all of those things which in a sense only have the voice provided to them by the experts who are mobilized as part of the environmental impact study to make sure that endangered species aren't destroyed, all that kind of stuff. So I guess the fundamental question here, and I have been arguing we should apply an environmental impact model to space as well, because it's kind of the best we've got at the moment. But the question, I think, is it's difficult to step outside that. And I think at that broader national, international sort of environmental scale, you can't opt out of the model. And yet the model is complicit in the changes that we're seeing and which are contributing to the situation that we're in.
Yeah. David, what are your thoughts about how best to incorporate equity and justice moving forward?
My thought is first unmute and then give my thoughts. It's a great question, and I really appreciate what Alice and Victoria have been talking about. You know, it's tricky because, again, when coming back to the Anthropocene, we could say, oh, well, humans are changing the earth. Well, really, are all humans equally, responsible? And so there's a way in which, just by saying that, you have to be careful that you're not sort of buying into some diffusion of responsibility. And yet there's also a truth to it. I mean, I think of evolutionary history, and we could say, 100,000 years ago, humans left Africa and started spreading around the planet, or maybe it was 70,000, we argue about it. But the point is that we talk about it as it was a moment in history. But if you were actually there at that time, it wouldn't be like all humans. It would be probably there were certain people who had more power and others that had less. And there were complex reasons why some people left and some people stayed, so there's the global stand back and look at the phenomena view, and then there's the granular what's really happening and the lives of individuals and communities. And I think we really need both perspectives. And one thing that I keep learning about these examples, it's kind of a question of, is the glass 3/4 empty or 1/4 full here? Because certainly there are formidable problems, but we can point to some bright points as well. And some have been mentioned, but I keep hearing about these solutions where Indigenous communities are being kind of empowered to find their own solutions in ways that then multiply and really help with global solutions. And for instance, there are these forest communities in Indonesia where there's a long history of them sort of selling out for cash so that the forests get cut down. And, there's a sad history of this, but in reality, no Indigenous people want to lose their forests and cut it down. There's a lot of times they've been placed in these untenable positions where short-term survival, they don't have choices. But now there's a wonderful book by a woman named Kinari Webb called Guardians of the Forest, where she talks about this. It's very, very powerful book. It just came out. Talks about this new model where in Indonesia, villages and communities are being given resources and aid and help to improve their healthcare and sort of things that they've needed cash for before to sell out, and say, you know, we'll help you with healthcare so you don't need cash. And do you want to do that in return for preserving your forest and working in your forest rather than cutting it down? And they're like, of course, we love our forests. We don't want to cut it down. And so you sort of provide communities with tools to be able to continue their relationship with the land in a way that is desirable to them, and also then you're not contributing to deforestation. And there's other examples from coastal resources. There's a wonderful group called RARE that I've learned about, that they're actually based locally here outside of Washington, D.C. And they've been really effective in helping turn the tide in many locations of the destruction of coastal resources by going to these fisher communities and saying, hey, you know, overfishing is really a problem. The resources are being depleted. We don't want you to stop fishing because we know that's how you support yourself. But if you'll set aside some portion and not fish that portion, then we'll also help you with technology and techniques and so forth, so that you can actually increase your yield and do better financially and do better for your community, but also help to preserve biodiversity and let the populations come back. And it's working. This is working in many places. And there are other examples as well. So I think we can learn ways to work with indigenous communities, not just sort of pave over the world in the quest of humanity moving forward, and yet recognize that there is a sense in which we're all in this together, even though the solutions are often focused on local problems and local communities.
Thanks for that, David. Do either of you want to respond to that, or? We're good. Okay. I'd like to thank you for that. I want to sort of move on to the sense of urgency. So as Victoria mentioned, we're coming off COP26 in Glasgow, which, you know, we're not anywhere near 1.5 targets. Could have been a lot worse perhaps in Glasgow, but it was certainly not an excellent outcome for the climate. And this is despite the fact, I mean, scientists have known for decades, I mean, more than a century, if you go back to Svante Arrhenius, the basics of CO2 emissions and what that does to global climate. So, you know, in some sense, scientists have been raising the alarm for many, many decades. I mean, if you've seen the trailer for that new movie, the Don't Look Up movie with Leonardo DiCaprio, and, you know, essentially the climate allegory in which nobody's listening to the astronomers about the comet that is threatening to hit Earth. I mean, we all laugh in a very grim way because it is so true. The alarm has been put out there for so long. We know there's a huge problem. We know it's not just barreling at us. It's here now. It's affecting everybody's lives. So I think I'd like to ask Victoria first to talk, how do we maintain and even ramp up a sense of urgency when we're coming off, you know, the big international meeting that was supposed to have, you know, gotten us somewhere?
It is a difficult task because climate change does not exist in a vacuum, and it competes with other critical issues that world leaders are facing. Because at the end of the day, the individuals that can make our planet habitable in the future are just that. They are individuals. We can all contribute and advocate for them to make the right and just decision. But at the end of the day, it is a handful of mostly men who are making decisions about how much to invest and how much to partner with the private sector to get us to a carbon neutral world as soon as possible. How do we keep up that urgency? From an advocate point of view, we continue to advocate, right? We stomp our feet. We continue to tell them that this matters, that this is important, and we ourselves move into decision-making positions so that that agency of action is shared around the table. You know, what David mentioned earlier, that we are, as a world, now recognizing the strength and the importance of indigenous solutions, of nature-based solutions. They are still not the overriding majority of the conversation. There is now a small piece that has been carved out by strong indigenous leaders. It was not given, right? It was carved out. And I think that's really important to remember with urgency, is that we have to keep advocating not for us to feel the urgency, but for people in positions of power to feel the urgency. Like, they should not have a choice of what comes next. The only choice should be a habitable planet. And the other thing that I want to bring up is a sense of urgency, not just for mitigation, but for adaptation. We are still oftentimes stuck in this either or mindset of either we reduce our greenhouse gas emissions or we adapt to unavoidable climate impacts. Unfortunately, that either or option was extinguished 30 years ago. We no longer have the choice. It has to be yes and. Yes, we urgently need to reduce greenhouse gas emissions. And also, we need to invest hundreds of billions of dollars into adapting our systems in a just and equitable way. And that, I think, was the biggest disappointment out of COP26, was that urgency was certainly felt by advocates who were there, but not shared when push came to shove with how much large nation states were willing to invest in a not just habitable future, but an adapted future to a warmer world.
Yeah, that disconnect between many of the activists, including youth activists outside the conference center, and then what actually came out at the end of those 2 weeks. Alice, I wanted to ask, stay on this point of kind of rates of change with you. So you've studied, past cultures, rates of technological change, how long it takes societies to go through sort of fundamental transformations. I guess from that archaeological perspective, when you look at the inflection point we are now with climate, how urgently, how effectively are humans capable of making a rapid enough transition to a big shock in their environment? How adaptable are we, and how quick can we make those adaptations?
I guess I would say we are incredibly adaptable. In fact, humans and hominids are, an interesting analogy is we're like weeds. Weeds adapt in marginal environments. We consider them problematic because they get in the way of things that we want to do, but in fact, they're incredibly successful. So humans are kind of like weeds. So I think we are in fact incredibly adaptable and capable of changing very quickly. However, when you look at that at an archaeological timescale, what you don't see is all of the people that die in that process. And we're coping with this in our now phase where it's happening, year by year, decade by decade, and people are going to die as a result of climate change, and that kind of doesn't the longer term perspective occludes that completely. So the good news is I think humans can adapt extremely quickly, but the bad news is that might be in a way that we find unacceptable and probably should find unacceptable. And I think that is the sort of key to how we should move forward on this.
Thank you for that. And we'll move to Q&A shortly. So if you have questions for the panelists, please put them in the Q&A function at the bottom. And David, I wanted to circle back to you. There's been a lot of discussion today about humans being in their technological adolescence, with all the advantages and disadvantages that it brings. What role can working on climate change play in getting us out of those teenage years? I mean, how can tackling the climate challenge help us all grow up?
It's a good question. I want to respond quickly to what Victoria and Alice said, or your question about urgency, but I think it actually circles back to this question of getting over our adolescence, because it's tricky, the messaging about urgency, because with all this, we've wasted so much time trying to get over climate denialism rather than moving on to saying, okay, that's not the real interesting conversation. Of course, we're changing the climate. How do we deal with it? We've wasted too much time just battling, saying it's happening, it's not happening. But out of that, part of the unfortunate fallout of that is we've stressed so much the urgency and there is an emergency of a certain kind, but I've seen the reaction, especially among certain young people, to conclude from how intensely we've stressed that to say, well, so it's over. There's nothing we can do. And that to me is very dangerous, that kind of nihilism, and it's not true. So when we communicate urgency, we have to talk about what kind of emergency it is. And I actually think the asteroid being about, I haven't seen that movie you mentioned, I think the asteroid being about to hit and everybody ignoring it, that's a bad analogy. It's not accurate. It is accurate in the sense that the scientists see this threat and people are going about their business when they should be addressing it. But what's not accurate is with the asteroid coming towards Earth, we see its trajectory, we know what day it's going to hit, and then we either avert it or we don't, and then we go back to life as normal. With the climate emergency, there's not going to be any like, oh, okay, it's done, we can go back to normal. Rather, it involves a long-term change in our behavior and our the way we perceive our relationship with the world. And this gets to your question about getting over adolescence, because I even in my book, Earth in Human Hands, I have a section called The Twisted Gift of Global Warming. And like, why would you ever consider it a gift? But what I'm talking about is we as a species have to learn how to think long term and how to deal with the consequences of our actions. At one point, we didn't need to. When we were young and few in number and not that powerful, the world seemed infinite, and it was functionally infinite for us, but now it's no longer that way. And this requires a fundamental change in worldview. And if we solve the climate crisis, and I think we will, but not without a lot of loss and damage, and that's really what we're talking about here. I think that we will get through it. 100 years from now, we'll be post-fossil fuels, and we'll be living in a changed Earth in a different way. We'll still be here, or some people will still be here. But there will have been far too much loss and damage because we won't have changed our worldview quickly enough. But I think there's the potential for this to be the test that forces us in a certain sense to get over that kind of adolescence of not just like, an adolescent doesn't clean their room because they don't care about, they just want to do what they want to do now. That's sort of the analogy. It's a matter of maturity on a global scale of living with consequence. And that's why I think the adolescence and maturity metaphor is actually pretty good.
Great, thanks. Do either of you want to follow up on that? No? Okay, I think we're good. We are 15 minutes to the end, so I think, Dagmar, do we have some audience Q&A?
Yeah, we absolutely do. And before we get to them, I do have a kind of tricky question, I guess, that I couldn't help myself from asking. Because I was so fascinated in this panel. There's so much tension in this panel in particular, in the scale of analysis that you're all working on versus previous panels, right? Here you all kept stressing specific populations, local geographies, even specific species that are vulnerable to climate change or could adapt to it. And you're kind of resisting the idea of humanity being culpable, at risk as a whole, right? And of course, in other panels, there's no such hesitation to discuss all of humanity, our adolescence, right, being kind of an example of that, or to discuss, for that matter, habitability on very broad terms. So is there a lesson here that we can draw for SETI, right? That maybe we should start thinking, when we think about SETI, maybe at a smaller scale of analysis, not just at the species level? Or am I thinking, or am I wrong about that?
I think it's a really interesting question, because when we talk about finding extraterrestrial intelligence, we always tend to think of it as there's a civilization on that planet. They want to communicate, or they don't, with our civilization. And that outlook sort of implicitly contains the us as a unity and them as a unity. So maybe there are other planets with others with multiple civilizations, and then there'll be some that want to talk to us and some that don't, or some that want to talk to some of us. But on the other hand, this previous point we're making, that in some sense one could argue, and I've made this argument, maybe it's not good, but that to achieve a great longevity, that's the twisted gift of global warming I was talking about, that we have to learn this lesson to in some sense be a global unity, even if we also at the same time cherish our differences in our local, communities and cultures. I think there's a way to cherish that. And, just as we are multicellular organisms with a lot of differentiation, we're not just one uniform blob, but we see ourselves as individuals. You can make an analogy that maybe the long-lived civilizations that talk to each other have achieved some level of global unity. Nonetheless, it is interesting that we kind of do that bait and switch when we talk about the civilization and our civilization, where in fact, when we start talking about the details of our situation on Earth, now, we go like, oh, well, we're not really a civilization, are we?
Alice?
Alice, yeah.
Just thinking about this, I know there are some recent exoplanet studies which have been, and this just boggles my mind, have been able to actually identify particular kinds of topographies, which on exoplanets, which then kind of translates into a particular landscape and environment. And with the ability to do that, we surely have an ability then to kind of tailor attempts at communication that are meaningful at particular kinds of entities that are adapted to that smaller scale, that subplanetary scale of environment. This isn't really my field, so I don't know if this is something that can be done, but I think, yeah, we've been talking about those differences of scale, as Dagmar said, in responses to things on Earth. And I think there is something in that which feeds into how one might communicate or identify different kinds of natural or cultural identity on other worlds.
Victoria.
I acknowledge that I may be biased because I work from the bottom up oftentimes, but I think there is a real danger in zooming out too much and losing justice, because responsibility is not shared equally across our planet. There are very specific companies, there are individuals, there are societies, decision makers that share far more responsibility of where we are today than others. Equally, damage, loss, what comes next is also not shared equally across this world. I have incredible privilege being here in Washington, D.C., that my colleagues and friends that live in the Arctic, in the South Pacific, in the Gulf, on the Jersey Shore do not share. And that is important and often is lost when you zoom out too much. And the final thing, thinking about COP26, solutions and mitigating greenhouse gas is not shared equally. We need a unity of effort, absolutely. And also, we need the biggest greenhouse gas emitters on our planet to commit to stronger action than those who emit the least amount of greenhouse gases. So I think that inequality across all three of those lenses is really important. And the geographies are much more granular when you have to answer those questions.
Mm-hmm. The biggest greenhouse gas emitters now and the biggest greenhouse gas emitters historically. As well, right? Actually, your response takes us right into an audience question from Raymond Merrick, which is about population density. So the question is, how will population density change life for islanders and the world as a whole? And I think really the question is also getting at this idea, right, that overpopulation is a huge part of our problem and might actually be common to many intelligent species. This is obviously a long-standing issue going back many, many, many decades, a long-standing argument. I wonder if you could all engage with it.
Yeah, no, it's a great question. I mean, the question of population historically is fraught because a lot of concerns about population growth, especially I think when people, Europeans first started talking about it, earlier in the 20th century, when you realize, oh, there's going to be a billion, there's going to be 2 billion, there's going to be 4 billion of us. A lot of it has been conflated with sort of racist or ethnocentric terms historically, and so there's a sort of a uncomfortable association there. Yet it's undeniable that above a certain number of humans, you could make a reductio ad absurdum argument. We don't want 100 billion people on this planet trying to feed them all and trying to so population is sort of an uber problem, which if you just simply look at the number of people and the amount of resources they consume, and then above a certain level, we're in trouble. But again, as we've been discussing, it's so much more granular, and it's so much not distributed. Who is suffering and who's responsible for this. But nonetheless, I think if we're there's room for sort of the global perspective, and that there's sort of a glimmer of good news, and that you think of us on this sort of S curve of population, like the Petri dish, and it goes up and up and up, and then it crashes, and we're actually not on that curve globally. Population is, peak birth rate has already been reached, although peak population hasn't. And there is, a decent argument to be made that the best demographic projections show population leveling off and decreasing late in the 21st century for the right reason, not because of an increase in the death rate, because of a decrease in the birth rate, because people are feeling like, women in particular, and in developing countries are feeling like they have more choices. So, I think that's all well and good, but as a privileged white male, I feel like I have to be from the United States. I feel like I have to be careful here, because I find myself also sort of saying, so the solution is that these women in Africa have to behave in a certain way, and that can also be seen as a cop out. So it's it's complicated.
Alice.
Well, I think David's just articulated this very well, because we have and coming back to Victoria's point about scale, is we have the sort of global trends, but all of this comes back to the individual lives of women and their ability to be autonomous and control their own fertility, which is increasingly becoming a problem in European countries and the US as well. So if we're going to talk about population, we have to come back to how we make a difference in the lives of individuals. And I'm just going to say it, I think both this and the climate change will benefit from us dismantling the patriarchy properly this time.
Victoria.
I want to add an additional layer, because I agree, Alice, with you, and also with David, and kind of the complexity of the density conversation. But that's only part of the conversation around population and climate change. We know that climate-induced displacement, migration, relocation is a huge and under-resourced challenge that our world will face, but also this country, the US and US territories, is currently facing. And to think about that, not in the future, but again, today. In Alaska, there are 31 Alaska Native villages that may need to be relocated, and 4 of those are in imminent danger of being displaced. The United States does not have separate funding for climate relocation. It does not have support for those communities, or communities in Louisiana, Washington State, or the territories that are being actively displaced by climate change. So when we think about climate and population, it's not just a question of density, but it's also about climate displacement and climate receiving communities. How do communities that may receive climate migrants be good, supportive, and compassionate neighbors to new arrivals?
Alice.
Good. Yes, just to add to that, of course, Victoria has identified Pacific Island nations as particularly feeling the impacts of those. Likely, climate change refugees from that part of the world will end up in Australia. And I'm not even going to begin to attempt to explain our current situation with regards to these, but it's not good. It is absolutely not good. And I just apologise for Australia all round at the moment. We are not doing very well in this whole sphere, but that's something that at that national level needs to change, or we will not be responding to our responsibilities with our nearest neighbours. And I guess that will be the case for many, many other nations as well.
Yeah, for sure. Here's a question that I'd really like to get to before we finish, and I ask you to keep your responses super short. It's a question by Peter Steele. So I'm a 76-year-old retired middle management man who has been greatly affected by the issues brought to me today. I have and will vote for those candidates who support climate change. I think it's climate action. I donate maybe $50 per month toward those organizations that are related to the causes. What, if anything more, can I as a human do? So maybe we'll start with Victoria and then Alice, David.
I am so happy that you put vote for those who are acting on climate, because I think that is always the number one thing that you can do. The number two thing from my point of view is to tell 5 of your friends and 5 of your family members over Thanksgiving about what you learned here today. It is so important for us to have as many voices as possible advocating for climate action. It is not enough for each of us to do individual action, but together we can do so much more, and we could advocate and vote for so much more. So the number one thing, vote. The number two thing, talk about climate change every chance you can get.
Alice.
I completely agree. Voting is the most important thing. So vote and tell your mates.
That's great. David.
Yeah, I don't have too much to add to what Victoria and Alice said. You know, if you look at those projections of those curves that we've all seen with the climate, the temperature changing into the future, and it's either going to do that and it's really scary, or it's going to do that and it's not quite as scary. There's a big gap between those two. And that gap isn't mostly because of uncertainties in the science of climate change. It's a little bit because of that, but the big uncertainty is we don't know how to model what human civilizations, what we're going to do, how fast we're going to change our ways as far as our energy sources and so on. That's the big unknown. But there's something, you know, slightly encouraging there, in that it's not written in stone. It's up to us. And so, yes, vote. If you live in a place where you can vote. Unfortunately, a lot of people in the world live in autocracies or places where they can't vote, and a democracy, of course, is sort of under threat in the world, but nonetheless communicate. And I do think that, you know, that changes in worldview are things that we never see coming. We're linear thinkers. We always project into the future and think things are going to stay the same, but a massive change in the way we see ourselves in relation to the world is really what we need. And those changes in worldview come about through communication and education, and we can all, as much as we can, be involved in that.
Fantastic. First of all, thank you all so much. I mean, if I could have written a script, which I have no talent to do, for how a final panel would have, you know, tied up today's discussions and presented them in an impactful and passionate and manner that also conveys the sense of urgency that I think is still missing. I couldn't have written a better script than what you all did. I mean, it was absolutely brilliant, and I think you brought to the fore, you know, really again the urgency here. I think it's somewhat unfortunate, perhaps, that COP26 is called COP, as in cop out. You know, but you know, I think we're far away from our political leaders really grasping the urgency of this. So I couldn't agree more with this notion of vote, and vote often, and tell your friends. I think there's another thing that we can all do, and this came up in other discussions earlier today. And you know, what is the role of corporations, large and small, in all of this? And are we not now ready to get to a point where instead of the pursuit and the raison d'etre of corporations being return on shareholder investment, it's actually return on stakeholder investment, where stakeholders are the communities we live in, the planet, our human beings, our suppliers, our customers, everybody. And we don't operate that now. I think it's maybe time to rethink that and to support those companies that do, because some are moving in that direction. And I think, where the private sector can lead and governments follow, why not? We should undertake this. But anyway, I can't thank you all enough. It was absolutely spectacular. And I thank our audience for the brilliant and inspiring questions. And I'm sorry we have to end this, but I do want to, put this little suggestion out there and keep it in your heads, because you'll be hearing more about this later. We are planning a follow-on event that we dearly hope to be in person in Washington, D.C. at Georgetown University in the spring over a 3-day period. We'll maybe be targeting something around Earth Day, which might be somewhat appropriate. So the actual dates have yet to be determined, but we're working on a springtime event. And it would be wonderful to bring back all the amazing panelists and moderators we've had today to be part of this more comprehensive event where we can really take a deep dive and actually also be together in person. I really missed that opportunity to having been able to be with you all in person, and how inspiring this has been. And I do remind our panelists and moderators, those of you still willing and able, we have our own closed session now to talk about beyond the crossroads and where we go from here. So we have our own session in which we have to leave this Zoom and enter the other one. So I look forward to seeing as many of you there as possible. And again, I want to thank our audience for coming along, and all of you for just an extraordinary and inspiring day. Thanks so much. Dagmar, I don't know if you want to say a closing word or not too, but.
You did it better than I could. Thank you all so much.
All right. Take care, everyone.